Hopefully it's trending.
Hi, welcome to the Biogeochemistry Working Group session. Well, great, there's some slides. I'm going to start with the Code of Conduct from NCAR and CESM. So some ideas here to consider as we have hear some speakers and have a nice discussion, consider new ideas, offer constructive feedback, share the air, acknowledge teamwork, encourage innovation, and show appreciation. Just to keep that at the top of everyone's minds. So I'm going to start off with some biogeochemistry working group updates, and then also just some logistics. We'll be here. We're going to have a number of remote talks, which is really exciting, but that means we also really hope to engage the folks that are online, as well as the people in the room. We left a fair amount of time for discussion at the end of each of our pieces of the session. So we run until lunchtime today with a break in the middle, and we'll have discussion before the break and before lunch. We encourage you, if you're online, to put questions in the chat, and we will read them out in the room. And for folks in the room, we'll run a microphone around to you. So please think of things you want to talk about as we are thinking about biogeochemistry this morning. So I'm Abigail Swan. I'm from the University of Washington. I'm a co-chair of the Biogeochemistry Working Group along with Gretchen Koppel-Alex and Kristen Krumhart. Kristen's not able to join us today, but Gretchen is here. I've got a QR code up here for the BGC Working Group email list. If you are not on that, I know a lot of the email lists shifted, and so we haven't sent a lot out to this list, but it would, that's partly because there aren't a whole lot of people on it. So if you want to join the list, it would be a great way that we can communicate about some of these activities. Okay, so what is the Biogeochemistry Working Group? Well, it started from, I was talking about this yesterday, Biogeochemistry Working Group was born out of the efforts to fully couple the carbon cycle in earlier versions that were not called CESM yet, so back in the CCSM days, and they were able to fully couple the ocean biogeochemistry, land biogeochemistry with prognostic CO2 in the atmosphere. And that was when the working group was created for the flying leap. So this means that the Biogeochemistry Working Group is the group that covers the full Earth system coupling, which is not actually really directly covered by the other working groups. So I see that as a core activity here, that we're always thinking about the coupling between all of the systems together. In particular, thinking about that coupling with biogeochemistry, which means that when we're thinking about emissions-driven simulations, as was the sort of original intent of the creation of this working group, those are core BGC activities. So with that, I'm going to give you a little bit of updates on some of the activities that have been going on in this space. Oh, and one more thing to mention, we are hoping to run a short tutorial on how to run emissions-driven simulations as part of the winter working group meeting. So I know not a lot of folks have run CESM in emissions-driven mode, but that's something we'd like to get a lot more people used to doing. And we think this would probably be at most about a half a day. But a tutorial on that and maybe a little bit of information about thinking about the CO2 field in the atmosphere, which is sort of the one output field that would be different than what you might be used to already. So if you're interested in that, look out for opportunities to learn more about running emissions-driven. So Keith Lindsay shared that the new ocean component MOM6 is running globally with biogeochemistry. This is showing some plots of different biogeochemical aspects, the different plankton categories. And so good news, there's a long, stable simulation that has BGC working in the ocean. If you want to know the details, you have to ask Keith about them. And Kristen shared that there's also a global high-resolution simulation of ocean BGC. This is not fully coupled yet, but it has eddy resolving simulation in the ocean at 0.1 degree resolution, which is a really big deal. So it's the first time to have a very high resolution with biogeochemistry. And it calculates the anthropogenic components of carbon and other BGC aspects. So it's able to calculate sort of what would be the state pre-industrial and what would be the state with current atmospheric CO2, which allows you to estimate that anthropogenic component. And this is really novel relative to other modeling groups so far. And then this very high resolution simulation can be used to drive offline impacts models with a lot more detail about what's going on with the water chemistry and the impacts of that. And so Kristen has used this to force, so there's a little bit more about the simulation, and she's used it to do some applications. So it's forced by a JRA reanalysis. It's got 2 zooplankton categories, and then she's linked it with an offline fish model called Feisty in this paper that is in review. So really coupling the biogeochemistry state to impacts on other systems such as marine fisheries. And this output is publicly available, so something that one could get involved and analyze, as many of our working group activities fit that category. And so she's showing here the impacts of on this bottom panel, the impact on fish biomass of the blob heat event in the North Pacific in 2015. Another biogeochemistry working group activity is the CESM HOPE project, which is the highly optimistic projection ensemble proposed last year at this meeting, or just after this meeting, by Nikki Lewandowski. The idea here is to think about decarbonization futures, and to run an ensemble of CESM to look at how the system behaves under those lower carbon futures. And so this would be in an emissions-driven mode. The hope is, I think, to do about 10 simulations. That was the plan previously anyway. And so the other CESM large ensembles are at much higher emission scenarios, and so they're having a lot more warming and a lot more forcing going into the system in that way. And so we really want to understand what happens not just to biogeochemistry, but also to all of the physical components of the system under decarbonization. And so it will be very, very useful to have a number of simulations looking at that. So the status is that we'll hear from Peter Lawrence later today about getting the emissions-driven version of CESM2 running. And when that is going, then it will be possible to start this ensemble. So this is an exciting new thing that there will be to look at in the biogeochemistry space, and also thinking about these lower carbon futures. So CMIP7 will have more emissions-driven simulations than we've had in previous CMIPs. And we'll hear from Ben Sanderson about some of those plans. CMIP6 had a limited number of simulations as part of C4MIP. Actually, so did CMIP5 and CMIP3. Worth pointing out, we've actually had emissions-driven capabilities going back to CMIP3. Again, part of the initiation of this biogeochemistry working group. But if we look at the CMIP6 simulations, this plot from the IPCC, we see that we got a number of different concentration outcomes of these models at high emissions scenarios with a spread of about 250 parts per million in the atmosphere. So we know that these fully coupled systems will evolve to slightly different states when we allow the carbon cycle to respond. And so the hope is that this will be the primary mode that many CMIP7 models we run in, I hope for CESM as well. And we've heard from other modeling centers that this is their plan to go forward with emissions-driven as their primary mode. This is likely to bring more spread in the outcomes in the future, but I think this is real uncertainty that we have not recognized previously, sort of in the mainstream of how climate projections are analyzed. Even though these runs have existed, they really haven't been part of the primary physical science analysis. So some key metrics for looking at those future outcomes will be these two acronyms. The first one is the transient climate response to emissions, which is the emergent relationship that we see in models between cumulative emissions on the x-axis and warming on the y-axis. And so this is just another IPCC figure showing that we see a relatively linear relationship between cumulative emissions and how much warming is experienced. The second metric is the zero emissions commitment. This is the amount of warming that the system experiences following the reaching of net zero emissions. And so when emissions are dropped to zero, this is the assessment from the last IPCC report showing that models are sort of centered around zero. The best estimate was zero with a range of plus or minus 0.3 degrees. So we have some amount of warming we expect for a certain amount of emissions, and we have some amount of adjustment to that warming after the fact, which could obviously be assessed at different times. So to assess this, there will be a new set of experiments, which we'll hear more from Ben Sanderson about, called Flat 10, where it's a simplified protocol of constant emissions at 10 petagrams per year, which drop to zero in this orange experiment, and in the blue experiment, linearly decline to negative 10 emissions. So we have a CO2 reversal, or CO2 removal. These result in these cumulative emissions on the right. So some early results of what this looks like across a couple of different climate models that have done these experiments, including CESM2, is that we see this now looking again at that transient climate response to emissions. We have cumulative emissions on the x-axis, temperature increase on the y-axis, and we have they're going up at different rates, but they're increasing in temperature relatively linearly. These dots over here on the right show then adding the ZEC onto the end of that trajectory. You can see many of the dots of the same color fall below their lines, meaning they have negative zero emissions commitments, but some are positive. So there's some spread across this small group of models so far that have done this Flat 10 experiment. We can also guess that there might be even more spread that we will look for. Now I've changed the axis on this plot on the left to be larger to match the similar plot from some CMIP3 era simulations from Ben Booth, who we'll also hear from this morning, looking at these are now A1B scenarios, so pulling way back. But we can do the same kind of plot where we look at cumulative emissions versus temperature change. And we see that this range, this is a single model running different land surface parameters. So a perturbed parameter ensemble of different assumptions about land. We're seeing at least a biggest spread across a single model with different assumptions as we are across this group of different models that have so far run flat 10. So I would encourage us all to think about how we can capture this additional uncertainty, what are ways that we could sample that with model experiments. So I'll show you just a couple of plots of what it looks like in these flat 10 experiments. First, just noting that just very high-level notes, nothing very sophisticated yet, but that we have a diversity of responses of land and ocean sinks across these different models. So what we're looking at here is time on the x-axis and carbon flux for the ocean in the top plot and the land for the bottom. So emissions is constant at 10 petagrams per year and then drops to 0 here, this black line. And you can see that there is a diversity of how quickly these models draw down CO2, how much variability they have, in particular, a larger diversity over land, not surprising. And you can see there's also a correspondence somewhat between how much land uptake and ocean uptake there is. Digging in a little bit to what's happening to vegetation carbon on land. This is now looking at the emissions phase. So we have, again, time on the x-axis here, latitude on the y-axis. And so we're looking at where the carbon is going into the system as we emit CO2 into the atmosphere. And this is all relative to the beginning of this flat 10 experiment. So we see the green colors are accumulation of vegetation carbon. In this particular model, you can see it's happening at a variety of latitudes, a lot in the tropics, also quite a bit at mid and high latitudes. If we move to the zero emissions part of this, we can see that these colors get a little bit more faded over time. That's not super obvious. I can show you another plot of that. But basically, the land does start to lose carbon as the system progresses. This is under zero emissions. And then if we look instead at this carbon dioxide removals, this is sort of an alternative to this middle plot. If we start from this experiment, you can jump to this one and see what happens as you remove carbon. And we see that many of the models, we actually get lower carbon in the land system when we get back to net zero cumulative emissions. So I think there's a lot of rich information here to figure out. I'm just going to show you all of the models to make the point that they do very different things. They put the carbon in very different places, and they put very different amounts of carbon in different places. Those of us familiar with land carbon cycling won't be surprised by the fact that models differ a lot in what they think will happen with land carbon, but I'm excited to figure out more about what's happening here. This one over here is CESM, tons and tons of tropical carbon relative to some of these other models. Just one final plot looking at the change in carbon during the zero emissions phase of this experiment. So now we're looking at the difference from the beginning would be when we stop emitting carbon, we get to net zero, and then what happens as it progresses in time. And you can see here that there is some loss of carbon happening, but again, a diversity across models of when that loss is happening. Okay, so just another reminder, we're going to have discussion before both breaks, so think of questions. If you're participating online, please type questions in the chat. We'll get those read out in the room, and we can pass it off to the next speaker. Oh wait, I should introduce. Sorry about that. I should introduce. Our next speaker is Ben Sanderson. Go ahead, Ben.
All right. Hi, can you hear me?
Actually, hang on just a second,
no.
Ben. We're still getting your slides up on the screen in the room.
Yeah, I think I'm going to have to ask you to share my slides. It's I have a security sharing issues on this side.
Working on it.
you seeing that, actually?
Sure. No, I don't think so. We're still sorting things out in here.
You see that now? Or
on Zoom, we can see it.
Ah, yes.
Yes.
You're up on Zoom now. Great. Go ahead, Ben.
okay, cool. If I'm driving, then great. Okay, so I'm going to talk about CMIP7 and some discussions which have been happening in various forums about the role of emissions-driven simulations in the next round of coordinated simulations. So, firstly, thinking a little bit about where we stand in the timeline. We're now sitting here in the middle of 2024. At this point, the historical forcings are near finalization, and the discussion on scenarios for CMIP7 is well underway, with a paper due to be completed over the next month or two. And so that leaves us looking at like mid-2025 through 2027 for the scenarios and the fast-track simulations. And so I'll talk a little bit about what the fast-track simulations will be. And so this has been a product of a lot of work by the CMIP panel, and then a number of task teams and people who've helped the task teams. And so a lot of the work that I'm going to talk about today has been with the Strategic Ensemble Design task team, which Isla Simpson co-leads with me. So this is the current fast-track simulation. So this is in addition to the deck. So whereas the deck, as in CMIP6, is a requirement, like the entry card for CMIP7, the fast track will be a set of high priority simulations which have been iterated upon with various different MIPS as being of particular significance for rapid simulation for use in assessments, in particular the IPCC assessment. And so within those of note are a set of new scenarios where the requests will be preferentially for emission-driven scenarios. An ESM historical simulation, which will be in the deck as well, and these new simulations in the C4MIP request, which are flat 10 and their two variants, flat 10 ZEC and flat 10 CDR. So broadly we wrote with a lot of co-authors, many of whom were in the room, a perspective on like what the advantages and challenges would be with moving to a sort of a more default emissions-driven design in CMIP7. Clearly, this inflates the potential uncertainty which will be communicated in the final products as seen in the time series which are used in assessments, because we're seeing the combined uncertainty from the carbon cycle response and from the climate response. And the argument goes that we've already applied this thinking in CMIP6 to aerosol simulations, or to aerosol representation, which has, depending on the model, the model complexity, has had the option to be emissions-driven for aerosols. And really, we're just extending that in CMIP7 to the carbon cycle with then the ultimate aspiration to have other forces like methane and nitrogen resolved in future in future iterations. So this will have its challenges, and so one of those is the calibration and the spread of the coupled system. And so here we're looking at the global mean temperature relative to late 20th century levels, evolution in the historical and in the ESM historical simulation. The point is there's a bigger spread in CMIP6 in the ESM historical simulation, and so this means that in CMIP7 that the importance of calibrating the coupled historical response will be coupled, as in carbon climate coupled, will be of greater consequence. But also we can expect to see more spread in the ensemble, and then that needs to, there's challenges in the communication of that in assessments and to end users in recognizing that we have a new source of uncertainty represented there. One thing which has come across is different centres have different preferences as to what they want to do in CMIP7. And so we have some centres who really want to stick to the CMIP6 model and are primarily going to run concentration-driven runs. We have some centres who want to do both concentration-driven and emissions-driven runs, and some centres who want to focus on emissions-driven runs. And so it's been a little bit of a challenge to design a DEC protocol and a spin-up protocol which kind of keeps everyone happy. And where this sits at the moment is that there will be an option for those centres who want to major on emissions-driven simulations, that a PI control, a short PI control, can be branched from ESM PI control at the model's own equilibrium pre-industrial CO2 concentration. And so that removes the necessity of doing a long, separate PI control spin-up, and allows you to do the DEC experiments like above 4x CO2 and 1% CO2, which remain in the DEC, but without a huge computational burden. So this has been a long, iterative effort to try and keep everyone happy. So one issue which remains open and kind of fairly high priority for this community to engage with is carbon, is CDR and carbon removals. And so as it stands at the moment, the scenario emit protocol for CMIP7 is unlikely to request process-driven BECS from the Earth system models. But there is, we've had a lot of feedback that there is high desirability to have at least a satellite MIP which does this. And so this is where the integrated assessment models pass over some variables which indicate the fraction of bioenergy crops, for example, which are going to be sequestered in long-term storage. So this requires BECS parameterizations in the land surface models, of course, but rather more urgently than that, it requires a community decision on what those coupling variables are going to be. So how is the information on where BECS happens and what crops it applies to and how it's stored? How is that going to be transmitted from the integrated assessments models to the Earth system models? So there's a European project called Rescue, which we're probably going to borrow the version 0 protocol from, but this is not final. And so what we're trying to organize is a virtual workshop in the fall, which all of this community is very much encouraged to join on BECS implementation in CMIP7 in general. So further thoughts on that are welcome. So this is a picture as it stands, a snapshot of the scenarios as they're going to look, and the extensions in CMIP7. There's no direct correspondence with CMIP6 scenarios. We have a more dense exploration of the low space, and so there's a 1.5 degree small overshoot and a 1.5 degree large overshoot. There's a 2 degree scenario, the low scenario, and then 2 current policy scenarios. And what we've done with the extensions is use the opportunity to have more than one extension branching from the same end in 2020 in 21-25 of the conventional scenarios. So the conventional scenarios will now run up until 21-25. And so we have, for example, a high overshoot extension which starts from a very high warming level and then simulates a multi-centennial carbon removal effort, which ultimately would get back down if the carbon removal was successful to Paris-compatible scenarios by the year 2450. But then also there's more moderate scenarios, more sort of policy-relevant scenarios, a medium extension, a medium overshoot, which assumes a current policy until 2040, and then a large pivot towards high mitigation. And then a very low overshoot scenario, which is a climate restoration scenario, which aims to produce pre-industrial temperatures by the year 2020, by the year 2250. Abby's already mentioned flat 10 MIP, so I won't talk over the basic design. We have a very simple experiment where we have 10 petagrams of carbon for 100 years. And the nice thing about this is that you can read off the TCRE in year 100 because you've emitted exactly 1,000 petagrams of carbon. We'd have to have 2 branch experiments from this, one which shuts the emissions off, the second one which linearly ramps down the emissions from 100 petagrams of carbon to 0 in year 150, and then minus 10 petagrams of carbon in year 200. So this is an idealized net zero transition. We have a mini MIP with 7 ESMs have participated so far. We're hoping to get 8 before we submit the paper. And so in this, we can see both a big spread in reversibility amongst the ESMs, but also potential biases, which we see in the simple climate model ensembles, which as they using the ensemble calibrations of the simple climate models, which were used in the last IPCC assessment. So, for example, the Magic C and Cicero SCM models probably overestimate the degree of climate reversibility compared to the ESMs. So you can see that here with the violin plots for the in simple climate models, assuming predicting cooler temperatures than our ESM results. We see a big difference in the timing of peak warming relative to net zero in the ESM simulations. So net zero happens in year 150. Some models exhibit peak warming some 25, 30 years before that. Some models simulate peak warming later than net zero. And then you can look at how that is manifested in the carbon sinks, both in the land and the ocean. What you see is that there's huge differences, as you could see in Abby's plots, in the land sink timing and amplitude of response. And so you can get peak. In some models, you actually get peak land sink during the flat 10 period, so even before you start removing emissions. In other models, the peak of the land sink is sometime after net zero, whereas the oceans are all slightly more in agreement. We see they differ in amplitude, but not in timing of the uptake. Interesting differences in reversibility. So this is a plot of the classic plot of cumulative emissions in the top left here against surface temperature. Some models are very much straight up and down, perfectly following that sort of TCRE line. Other models show hysteresis. Other models show a change in behavior which comes in later in the simulation. So CESM 2 is one of these, where we see there's an ocean dynamical AMOC response, but that only begins to manifest towards the end of the simulation. And so you see this orange line here pivoting away from the cumulative emissions trajectory, which it was following towards the beginning of the experiment. So yeah, as Abby said, there's a lot to unpack here. Charlie Coven helped come up with a bunch of metrics which we can use to sort of diagnose the properties of the overshoot. And so this is a idealized representation of the temperature response to the flat 10 CDR simulation, and we have these metrics which represent the degree of reversibility and the timing of net zero relative to peak temperatures, and the difference, the degree to which we come away from the cumulative emissions line during the flat 10 CDR experiment. And so we can look at this in a higher dimensional space. We can see where we see relationships between these diagnostics in the simple climate models, which are the contour lines here, and then the ESMs. So anytime you see a dot, which are the ESMs, which lies outside of the contours in the simple climate model ensembles, that's kind of indicative that we're seeing behavior in the Earth system models, which is not represented in our current simple climate model ensembles. So there's really there's potentially an opportunity here to learn from the additional diagnostics which we're seeing from the flat 10 experiments and get them to be represented in the simple climate models in the next assessment. So to round up, so CMIP7 will contain a lot more options for emissions-driven simulations and several more interesting experiments. The protocol is flexible, so it allows centers to without a huge computational burden, to focus on emissions-driven or concentration-driven experiments. but with a core deck which is common between the two. We've added these flat 10 experiments which provide this clean assessment of TCRE, ZEC, and climate reversibility. This will come with some challenges on the calibration of the coupled carbon climate system, which will take on a greater significance in the next round. And there's still a big question mark about BECCS, whether we can implement it in CMIP7, BECCS, and other forms of CDR, and how it gets implemented. And so, yeah, hope to get this community engaged in that question. That's it. Thanks.
Great. Let's take a question for Ben, and then maybe we could switch the slides over to our next speaker while we're doing that. Does anybody have a question? I'll bring you the microphone.
Thank you, Ben, and thank you, Abby, for the introduction before. I was curious about the plans on emission-driven runs, and I wondered about, now as you, Ben, also showed that there is quite a difference in characteristics concerning reversibility between the simple climate models and the full ESMs. I wondered how, or maybe for which diagnostics and characteristics of the whole system is it important to run emission-driven runs in the ESMs, and where is it maybe sufficient to run concentration-driven runs of different concentration paths generated by simple climate models?
Yeah, I think it's a valid question, and certainly one of the goals with the flat 10 experiments is to provide a clean calibration target for the simple climate models. So the hope is by the next round we will have simple climate models which can represent the diversity of reversibility which we see in the ESMs. I mean, a number of centres and a number of MIPs will still require some concentration-driven experiments. And so, for example, in DA MIP and RF MIP, for example, there's big. It's a conceptual challenge to think about how to design these things in emissions-driven mode. So I think in reality it will require some degree of both. But it still remains true that the outputs of the ESMs and how they get into those summary plots in the IPCC has outsized influence. And so I think there's still an argument to have some emissions-driven scenarios there produced by the ESMs as well to supplement the SCM results.
Okay, I think we should move on to our next speaker, but I'll remind everyone we have some time for discussion at the end. So if you have more questions, save those for before the break. Next speaker is Ben Booth. Ben, we've got your slides up on the screen. We don't currently have your video. I don't know if that's I think we're getting that from the back of the room.
So fantastic. So is my video there now?
I think it's on our end that we're still getting you up on the screen. There you are. Great. Go ahead.
So thank you for having me. So good morning, everyone. So just a bit of background. I'm Ben Booth. I work on national climate adaptation in the UK for the last 20 years, and I've been very interested in uncertainties and how you capture and expose those uncertainties to adaptation planning. And so I'm also part of the climate of the CMIP7 task team that both Ben and Abby are on. And so what I'm here today because I want to open up a conversation about how we might do better at capturing some of the wider Earth system modelling uncertainties and expose them down to adaptation and mitigation questions. So I'm just going to start with a couple of slides to kind of motivate why this is important. So what I'm showing you here is global CO2, global temperature, regional temperature, which in this case is European, pan-European, and a local winter rainfall change out over the next century. And the ones to focus on are the yellow plumes. So the yellow plumes are the available regional simulations, Cordex, and they underpin in this context all the European climate and national scenarios. And so the red plumes are the concentration-driven parent GCMs. The green plumes are emission-driven ESMs of the same generation, and the blue is the original lens large initial condition ensemble. What you can see is that the Cordex doesn't capture the wider spread of responses from any of the GCM. It captures in regional European case, it captures roughly half the temperature change of the concentration-driven runs, and really doesn't capture the wider range of the emission-driven runs. So they're perhaps a very good starting point for non-risk adverse climate adaptation or impacts, but for a subset of users who are really risk averse, it really doesn't expose the range. And I can show that in another way in the next slide. So this is an alpine example looking at climate change up to mid-century, and all the red square crosses down here are convective emitting regional models, so state-of-the-art in terms of resolving the resolution. They all show neutral to moist conditions up to mid-century and central to modest warming. Because the driving GCMs, the green circles, all produce neutral to modest moistening and central to low-end temperature changes. So there's they're not able to capture the potential of the winter may be dry, or that the winter may be warmer than expected. And this is important from an adaptation point of view. If you think about water resources, there's a very clear drying signal in the summer in this region. So the ability to recharge reservoirs in the winter is key, and so current adaptation to planning on available convective emitting simulations ignores potential that you may not recharge reservoirs as much in the winter, and actually there may be much less snowpack, and so less spring river flow than those simulations that you're making a decision on capture. And the point to make is there is a much wider GCM range, so that you can have chosen different GCMs, and natural variability plays a very big role. So this is the lens ensemble, but this is just trying to illustrate why it's so important to kind of be able to capture that wider range of potential changes if you are to inform more robust adaptation planning. So just a couple of brief points before we go on to modelling uncertainty, which is what I really want to talk about. So I think we've done really well in terms of in working group 1 in terms of synthesizing multiple strands of evidence. So the TCRE, the transit response to emissions, is a really nice example. It's pulled on results from scenario MIP and from C4 MIP experiments, and they kind of synthesize those strands. But it's a broad brush, and it's not wholly true. There are energy balance and pattern scaling ways we can do it, but my broad brush statement is that if uncertainties are not represented or captured within scenario MIP, effectively they do not exist from an adaptation or particularly from an adaptation and climate impact perspective. And so I think CESM is moving in the right direction. So Ben Sanderson's already talked about this. There is a strong desire now to have a much larger emission-driven components to scenario MIP, and this will help mitigate some of the challenges we have. The current climate impacts and adaptation are not exposed to. So I think CESM is definitely moving in the right direction. So the emission driven is very important, and we're making progress on that. The internal variability, we should be in a much better position. There's a lot of buy-in in terms of sampling internal variability in large ensembles now. So what I want to talk about is, can we shift the CMIP context to better capture model diversity? And so what I mean by that is that there's, I will unpack the right panel, the carbon cycle in a tick, but just taking the left panel here, CMIP represents flagship models, snapshots of potential model responses. And within modeling centers, we often are aware there is a broader range of potential climate feedbacks consistent with how we formulate our model. But we're not really able to expose that and capture that. So really the question is, can we think about how we could do that? So just to think about the physical feedbacks briefly, the blue points are CMIT3 and CMIT5. They show a relationship between, in this case, in this example, lower tropic stability on the horizontal axis from the Sherwood et al. 2014 paper, and climate sensitivity. So models with a higher tropospheric stability metrics tend to have larger climate sensitivity. And you can compare that to observations, which points to larger feedbacks in this case. But if you look at the red dots and the grey dots, these are two large parameter ensemble of CAM3, done by Ben Wagman, and our own model Hadgen-3, and they show there's a much broader range of relationships between that stability metric and climate sensitivity. And so we're not capturing that in current CMIT frameworks. So I'm going to skip through these in the interest of time and maybe a bit of a discussion, but perturbed parameter ensembles are a way to expose that. I know that in the CESM group, there's a lot of, you already think of it in this framework, but they're a great way to expose a broader range of potential feedbacks within a particular modeling framework. So I'm going to show you some results now from our own UKSM land surface model. So what we've done is we've perturbed on certain parameters that are important for the response, and then we've ruled out implausible combinations, and we've looked at the range of past and future changes that are consistent with those metrics. So this is very busy. So this is over 1,000 different joules simulations. We've used MBP, NPP, soil carbon, veg carbon, observational estimates, and cumulative NBP. And we've also used bare soil to roll out models which aren't able to reproduce vegetation. So this gives us the light blue, grey, cyan, teal colours on simulations which we deem not to be not implausible. So we're looking at NPP, NBP, soil carbon, veg carbon, LAI, respiration fluxes, land carbon fluxes, and so on. So what does this mean, and what does it tell us about CMIT6 in terms of the range of feedbacks it captures? So all those simulations I just showed you include our nitrogen cycle. The lines here with coloured dots are the change in future land carbon storage from CMIT6. So you've got ECF at the bottom here. The blue one at the top is CNRM, and then CAM ESM5, which overtakes it at the end. So there's a range of CMIT6 land carbon uptakes. And then the light teal colours are the range we get from our own perturbed parameter joules runs. And you can see that we span much of the CMIT6 range. And talking to Roland, he thinks that by including additional harvest fluxes, this kind of brings their own runs down to something closer to the NORISM response. So we can argue about how well we capture the range of CMIT6, but the important point about this plot is that there is a whole range of potentially plausible simulations that suggest that less carbon could be taken up in the land by the end of the century than is captured within the current CMIT6 simulations. And in fact, there's quite a number of simulations that suggest that land may become a net source of carbon by as early as mid-century, which again is not captured in CMIT6. And so this has really got me thinking about, can we do better? Can we ensure that CMIT7 is able to capture a broader range of potential changes? And I think, hopefully, I've convinced you that that's important for us to do if we go to shift adaptation to more robust, a more robust footing. So we've been spinning up our own models. This is UKSM Fast. So I've got 29 different model combinations spun up now, and it's something that we have an appetite to submit somehow to CESM, but we need, I think, a wider international buy-in. So in our case, we don't span the full CESM6 range. I showed you this in terms of carbon, but in physical feedbacks, all our models, no matter what we perturb in the atmospheric parameterizations, all our perturbed physics variants of UKSM have very strong climate feedback, so high climate sensitivities. So if we have any chance of kind of exposing the wider range of climate responses around the flagship CESM models, then it's going to need some kind of international buy-in and engagement to do that. So that's kind of that's kind of my pitch, if you like, to start a conversation. And so my two questions are thinking about, can we shift CESM to be better being able to capture the model diversity? So there's an idea to run a PPMIP as part of CESM7, and this could be a vehicle that we could collaborate and look at wider diversity in underlying feedbacks within particular models. And I'm really keen to explore that if there's interest here. But thinking back to that earlier statement of mine that if an uncertainty or feedback isn't represented in scenario MIP, then for many adaptation decisions, it effectively doesn't exist. Are there other ways we can think about getting some of that model diversity into scenario MIP so that we can inform that adaptation? And we can't do that for more than, it's very hard, it's computationally hard, but can we be imaginative about that? Is there any appetite to submit a high or low climate sensitivity variant of our own bottom-up CESM7 configuration? So those are my questions for you. Hopefully I've got some time.
Great. Ben, if you could stop sharing your slides, maybe we could do this, try to ask a question while we're doing the transition to the next speaker's slides. Do we have any questions?
Great.
For Ben?
Thanks, Ben. This is Dave Lawrence. Yeah, so we're definitely thinking along the same lines. So you maybe have heard that from others, and I'd like, if possible, one that sampling both ECS variants and ECSM variants in the land and maybe ocean carbon. The question I have there's a lot of questions, right? Is can we do it computationally? And for us, it's a spin-up problem, which is the barrier, and our model's more expensive. But to what extent are you envisioning something that's like controlled by a centralized body like CMIP versus just like whatever any modeling center can kind of do, right? We all come up with our own design, and I'm curious what your thoughts are about that, because we may not have the ability to be that flexible in what we do. So
a design experiment is always wonderful, but I think we have to be incredibly pragmatic. I mean, we're thinking about CMIP7 now, so this is the data which will underpin global adaptation for the next 15 years before CMIP8 comes online and starts really influencing that. And I think anything we can do to kind of broaden that diversity is going to have value. So if there are, I think we need to be really open about what the challenge is and be really welcoming. If we can broaden the kind of range of feedbacks we capture in CMIP7 over what we did in CMIP6, include plausible changes, I think that has to be a good thing in terms of adaptation.
Thanks so much, Ben. We should move on to our next talk. So next up, we have Sandupal Dutta. Oh, great. We see your picture, and we're still working on slides.
Oh, can I share my screen?
Yes, you can share your screen.
Okay, that will be good. I hope you can see my screen. Is it visible?
It's not in, yes, now you're in presentation mode. Great, go ahead.
Okay. Okay, thank you. Hi, good morning, everyone. So my talk today is about using machine learning techniques on understanding the phytoplankton size classes and relationships with the environmental drivers. So first of all, let us have a look at why we need to use machine learning techniques. So there are, when it comes to relationships the relationships between environmental drivers and phytoplanktons are basically can classified into two kinds of relationships. One is intrinsic relationship, which are basically the relationship which we see in a laboratory or controlled settings, where one input is varied at a time, whereas other inputs are kept constant. So an example of such a relationship can be seen in the figure on the top corners between phytoplankton biomass and light and an orbital nutrient. However, in the natural environment, these inputs can interact with one another and give rise to something called apparent relationship, which we can see in the green curve in the central figure. So these apparent relationships are nonlinear and difficult to interpret, and this is where machine learning techniques can be helpful because machine learning techniques are good at understanding nonlinear relationships. So now let's have a look at the methodology that we use. So I have taken observational data sets from satellite products like CFS, Copernicus, and MODIS, and the input drivers I have taken from various sources, including climatology, reanalysis data, and ensemble average CSMs. Thereafter, what I did was I trained a random forest regressor to predict the size classes and used explainable AI techniques like permutation importance analysis and median replacement anomaly analysis to understand the relationship that is being mapped by the random forest regressor. So the same technique I used for the CSM for analyze the CSM2 data sets. So now let's understand a bit about what is random forest. So random forest is nothing but they are an ensemble of decision trees. A decision tree is a supervised learning algorithm which learns by splitting the target data set along an input feature that captures the maximum amount of variance. For example, here, if we plot the phytoplankton biomass against inputs like shortwave radiation, iron, ammonia, we can see here that the split on the shortwave radiation captures the maximum amount of variance. So here, the decision tree will select the shortwave radiation as the first feature to split the target variable. And this process is sort of repeated recursively for all the input features. So now let's have a look at how the random forest is performed. So this is the bar graph showing the normalized RMSE, which is basically the root mean square error divided by the standard deviation of the data set for all the observational data sets. So here it depicts all the random forest regressor, how it is performed across various phytoplankton functional types from observational data sets. We can see here that the normalized RMSE has been around 0.3, which is pretty good. Also, the R2 score which we obtained is around 0.87 to 0.92 across different observational data sets, which sort of that explains 87 to 92% of the variance of the data, which is pretty good. So coming to the random forest, how it has performed for the CSM2 dataset, we see again the normalized RMSE in fact are lower in case of CSM2 dataset, which goes on to show that the random forest has performed even better than the observational datasets. The R2 score we obtained here is between 0.98 to 0.99, which goes to show that random forest regressor has been able to capture 98 to 99% of the variance in the dataset. So let's understand what is basically explainable AI techniques that I used in the analysis. So the first technique that I used is the permutation importance analysis. So here what we do essentially I have done is that we take each input feature at a time and randomly shuffle the data across the entire data set of that particular input. And now we give this to the trained random forest regressor for prediction. Naturally, we expect a worse prediction. So we expect the error to increase because now the information contained in that particular input feature is no longer available to the random forest regressor for prediction. And the difference with the original prediction with the actual data set is basically a measure of the importance of that input. So larger the difference, the more important is that input for predictions. So looking at some of the key results that I have obtained using this analysis, we can see that if we compare Copernicus and chlorophyll A data from Copernicus and MODIS, we see that shortwave radiation comes out to be one of the most important, followed by sea surface temperature for observational data set. For CSM2, again, we see that shortwave radiation is the most important and sea surface temperature is the next in line. However, coming to the observation data set, we find that iron takes a lot of importance in prediction in case of observational data sets, which is not reflected in CSM2. Here, nitrate becomes the third most important factor for prediction. The next we look at the same results from diatoms, for Copernicus, and from CSM2. We again see that though the first two, that is short-wave radiation and SST, are still the topmost, but again, nitrate comes out to be very important for the models, which the model gives a lot of importance for nitrate for prediction, whereas the same importance is not seen in the observations. So that is another key difference I found. And for picoplanktons, again, when we compare Copernicus and CSM2, we find that here the SST comes out to be the most important case of phytoplankton is in observations, and followed by shortwave radiation, followed by iron. However, the same trend is not seen in CSM2, where light is the most important, followed by SST, but then iron is one of the key differentiator, where iron does not gain the same amount of importance as we see in the observational data sets. So the next analysis, what I did was the median replacement anomaly analysis. Here is the process is more or less same, but here instead of randomly shuffling an input variable, what we replace that a particular input at a time using the median value of that input, and then we use the again give this altered data set to the trained random forest replacer for prediction. Again, we expect to see a fall in the prediction because now this input, the information contained in that particular input is no longer available for the random forest to do prediction. And the measure of the difference from the actual prediction is basically the measure of the input importance. So here we look at some spatial plots from this analysis. The key thing to understand here is that the brighter colors, the brighter red and the brighter blue, the brighter red indicates that the random forest, the original prediction of biomass was higher than when you replace that a particular variable, in this case iron, with the median value of iron. And the blues indicate that the median prediction was higher than the original prediction, random forest prediction. So therefore, we can see here that, as we have seen in the permutation importance analysis, iron was important for observations for Copernicus and MODIS, and this is reflected in the median replacement anomaly also here, because we see the bright reds and the bright blues, which is sort of absent in the case of CSM, which indicates that CSM does not actually give more importance to iron for prediction. Similarly, we have a look at, if you remember in the permutation importance analysis, we saw that nitrates came out to be very important for the CSM2 for prediction, which was not sort of reflected in the observational data set. So in the median replacement anomaly analysis also, we see that the bright sort of blues indicate that nitrate was indeed important for CSM2 prediction, whereas the same importance is not seen in the case of observational data set. Similarly, for picoplanktons, and which I compared with the small plankton for CSM from CSM2 dataset, we see that for pictoplankton, both from the Costodinov dataset, which is basically the MODIS dataset, we see sort of relatively higher importance for iron, and also for Copernicus, we see a relatively higher importance of iron, whereas that is not present in the case of CSM. Especially in the northern hemisphere, the higher importance given to iron is not captured by the model. So these are some of the results that I obtained from my analysis. So the first thing is that random forest was effective in simulating the biomass in observations and CSM2. Generally, short-wave radiation and SST was found to be the most important across various phytoplankton functional groups. Iron was important for the total biomass and also for picoplanktons in observations, whereas the model was not able to capture the effect of high iron in the northern hemisphere. Nitrate came out to be important for model predictions for diatoms for the model, but was not seen to be important for observations. My future roadmap comprises of doing this kind of analysis for other ESMs and comparing with CSM2. Also use more explainable AI methods like Shapley, additive explanations, and local interpretable model agnostic explanations, and compare with phase data. This is one of the key data sets that most data sets that I can lay my hands on. And also the end idea is that to improve the prediction of ESMs using this kind of information. I would like to acknowledge my guide, Mr. Anand, the NOAA grant which funds my research, and Dr. Krish Holder, whose research I have extensively referred to during my analysis. That's all I have. Thank you.
Okay, thank you. Let's take one brief question while we transition over to our next speaker. So Rosie, if you want to try to share your slides while we're transitioning, that would help us stay on time as much as possible. Any questions?
I thank you for that interesting presentation. I have a question seeking clarification. When you did the sensitivity studies with CESM, was that modifying the inputs to the actual CESM model, or was this modifying the inputs into an ML-trained emulator on CESM? That I wasn't quite clear on that.
I don't know whether I've understood your question rightly. What I did was I took the inputs which was there in the CSM2 model product from the model itself. I have not done any sort of alteration to those inputs. Does that answer your question?
Great. Okay, thank you so much. I think we'll move on to our next talk, and so we can save some time for discussion at the end. Our next speaker is Rosie Fisher. Go ahead, Rosie. Your slides are up on the screen, as is your photo.
Hi. So can you guys all see me? I'm here in Oslo with Danica, who's visiting me.
Yes, we can.
So,
we can see and hear
see
you.
all virtually.
You can see you in the room.
So I'm going to talk about calibration of CLM fates. Of course, this is the work of lots and lots of people, in particular Adriana, who's built lots and lots of this calibration infrastructure and done this SP calibration beforehand, and the Fates Core team, CLM5 PPE team, and the NORISM land team. So why should we care about model calibration? So I'm just going to air a little bit of dirty laundry. These are the land surface model predictions from Earth system models in Trendy, and these are GPP predictions. This is the benchmark on the top left. That goes up to about 6 or 7 grams of carbon per meter squared per day. We typically get biases that go above or below Mach plus 2 grams of carbon per day. For that, so that's a large number. Lots of these plots saturate, obviously. The story for LAI, which goes up to about 5 in real life, and we get at least plus or minus 2 errors there. And then similarly for biomass, maximum biomass is about 15 to 20 kilograms per meter squared, and we get biases of plus or minus at least 6. And so we're not actually doing all that great in general. And so why does that matter? So inaccurate simulation of present and future carbon density precludes accurate estimation of carbon climate feedbacks, obviously. And so it also sort of inhibits us from making sensible assessments of the impact of land use change if we don't know what the carbon density is on the land surface in the present or indeed the future. And so basically, we all know why this is. Models are biased because historically we've not been able to objectively calibrate them. With some notable exceptions. And the interesting thing about now is that these two different approaches of history matching and emulators and data assimilation are emerging as these promising approaches across the different land surface model teams internationally. As you probably all know by now, this meeting in the sort of CLM space, we've been concentrating on this history matching, emulator-driven history matching approach. This is Linnea's slide, which is really nice, which illustrates that what we do there is this parameter ensemble, and we train emulators to predict the ensemble results, and we use observational metrics to constrain the parameter space. And we do that again if we have to, and so on. I'm going to talk about CLM fates. CLM fates, like all land surface models, has many intersecting process domains. It's obviously a little more complicated than CLM, and so this problem of how to calibrate it is more acute. And so we've been thinking hard about how we can kind of divide and conquer the parameterization process in CLM fates. And so to do that, we've introduced this thing called this calibration cascade. And what that does is we run the model in a series of increasingly complicated modes. And so we start off in the kind of classic satellite phenology SP mode wherein we prescribe the LII, the biomass, and the PFT area as boundary conditions. So we tell the model all those things are unbiased, and we calibrate the parameters related to photosynthesis, hydrology, surface energy, fluxes, and so on. And then at each of the latter stages, we make more of these things prognostic. So the next stage in our cascade is called no competition mode. And in that mode, we predict leaf area index and biomass. And so we use these to test the model rather than as inputs. And so each of these stages calibrates different set of target processes against a new set of observations. And so the interesting thing about this is that the kind of like there's the possibility of objective calibration kind of changes our paradigm of model testing. And so in the old world, we would get parameters from the literature or whatever and kind of run them through the model and predict some kind of variable which we would compare to a data product, GPP, LAI, etc. And then if it matched, we would be happy, and if it didn't, we wouldn't. Sorry, this is kind of advancing with some kind of timer. And our new paradigm is different, interestingly, in the sense that in our new paradigm, we use the data to calibrate the model, and the output are the parameters. And so what those parameters are is now our primary means of validating whether the model hypothesis or structure is sound. And so in the Fates world, a few things have happened, a few examples of this process have occurred during this calibration cascade effort. As we talked about this before, but I'm just going to kind of reframe them in the sense of that was what's going on. So the first thing that happened is that when we introduced this Fates SP mode, where we could drive it with leaf area, what we found was that we had a big albedo bias on our old Fate radiation scheme, which I wrote, and which was based on the Norman scheme, which is this multi-layer thing, which we subsequently realized had a high albedo bias. And so what that meant was that when we calibrated it, the leaf reflectances were outside the observed range. And so obviously we slightly panicked about that. But then Ryan Knox, who was a hero, wrote a new surface radiation scheme based on the two-stream approximation, which has this kind of multi-layer sort of heterogeneous canopy that we need in Fates. And so when we introduced that, the radiation bias went away. So that was an example of us using our parameter estimates to say these parameters are not reasonable, so we'll have to make a structural change. Then we move on to photosynthesis. And so Adriana showed this slide at the winter working group, so I'll just revisit it briefly, is that when we first did this photosynthesis calibration, what we found is that all the model ensemble in gray was like higher than the observations in red. And so we went back and scratched our heads, and we reverted to a non-acclimating photosynthesis scheme, based both on this and on some kind of philosophical sort of thoughts we had in collaboration with Abby's group, actually. And when we did that, we were able to calibrate the model with VC maxes that were reasonable. So that's good. So now we move on to the no comp, because we think we have photosynthesis more or less right if the leaf area is right? So now we have to get leaf area right. And so we take the parameters from the SP calibration, which Adriana also showed in the winter working group. We feed these into the no competition model. And so the first thing I did here was a one at a time parameter ensemble to figure out which are the top parameters to put in the subsequent Latin hypercube. And so these are the top rank parameters for LAI, and these are for NPP, and these are the two variables I'm going to concentrate on more or less. And so then I chose from those top parameters for the LAI and NPP, I chose as after a bit of iteration these 10 parameters to do the Latin hypercube on, because I removed a couple that had very kind of lots of equifinality in their responses. I'll put a little more if you want. I did a 500 ensemble member a Latin hypercube with these 10 parameters. And so that looks like this. So what's happening here is that the ensemble is in gray, the MODIS and AVHR LAI estimates are in red and blue, and for each of these plots is like each of the grid cells in the sparse grid configuration, which are dominated by that PFT. So there's not 12 because there's not some grids, some PFTs are never dominate anywhere. Take home message here is that the ensemble covers the observations, so that's good. That doesn't always happen. And then I did the same thing for carbon use efficiency, and the observations here are from a meta-analysis by Alessio Calalti and Colin Prentice in 2021, and this is plus or minus 1 standard deviation of what they found for the carbon use efficiency, which is NPP over GPP. So let me move on to the kind of emulation stage, having done a lighting hypercube. An interesting thing I found kind of in common with the last speaker a little bit was that when I used the Gaussian process emulation, it worked okay for lower dimensional ensembles, but the higher dimensional ensembles that I did, the random forest method worked out of the box way better. And so these are the LAI surrogate models. These are the carbon use efficiency surrogate models, and these are GPP. And so what's happening here is for each plant functional type, I'm emulating the mean of the annual of these things. So I'm just going to look at this parameter space in a little bit more detail. This is my 10 parameters I'm changing. This is LAI of broadleaf evergreen tropical trees, the mean of those grid cells. And what you can see here is that LAI is dominated by these 3 parameters, right? So we have SLA top, how many leaves you get for a given biomass. This is the crown area coefficient. So this is the thing we have in FATES, but not in CLM, which is how many leaves we can pack into a given tree canopy. And then this third thing is this maintenance respiration scalar. And so this is interesting because what we found, Jessie Needham from LBNL, she introduced this scalar because she was finding in a kind of quite detailed analysis of the carbon economy of the vertical profile that observations supported a reduced maintenance respiration through the canopy. And we need that in FATES to maintain a high LAI in tropical forests. So this is another example of saying, like, well, our current model structure, in the presence of the correct GPP and carbon use efficiency, we can't calibrate it to have LAI which is high enough, effectively. And so we introduced this structural change response to that. So this has been a kind of like a nice process of at each stage kind of like reconsidering what model structure is reasonable. This is the same plot. I should have explained that latter plot better, actually. What's happening here is that the purple line is the LAI observations. So the purple line here is where our observations pick out the parameter space. This plot is the same but for carbon use efficiency in orange, right? So where the purple cloud and the orange cloud intersect is kind of the sweet spot for getting LAI and carbon use efficiency right. And so you see for lots of the parameters, the observations don't constrain the parameters at all, basically. But here, for example, interestingly, SLA top is the low values are rejected by the leaf area index calibration. And further, we can also test our assertion that if we get the LAI right, we should get the photosynthesis right. So here the blue are the blue cloud, the observational uncertainty for photosynthesis, and the purple is for LAI. And so basically, when we're getting LAI high, we're also getting the GPP high enough. So that's nice. This is a different plant functional type, right? This is needle-leaf evergreen next tropical trees. We see the same 2 parameters having an effect there, SLA top and crown structure. The maintenance respiration doesn't matter here because we're in a cold place, so maintenance respiration is less of a big deal. And then just one more with C4 grass. None of those things made any difference. The only thing that matters for C4 grass is the turnover rate. It's actually the inverse of turnover rate in FATES for a weird quirk. But we have to make very high turnover rates to get the C4 LAI down to the purple observations. So this is what the parameter space looks like, the top parameters that control LAI for the 6 plant functional types. You'll note that none of the C3 grasses come out here, so this is something we need to revisit. This is what happens if you constrain it with carbon use efficiency as well. So just toggle between those, you can see the cloud gets like smaller. And so this is where we're at. Basically, the next step is to like sample this parameter space and run that back through the main model. I tried to do that before this talk, but I messed it up. So yeah, that's to be continued. And so in summary, the FATES calibration cascade enables us to sequentially resolve model biases and structural issues. And the random forest models significantly outperform the Gaussian process emulators. Division of this calibration task across domains I'm still really into because it allows us to reject model structures that give unrealistic parameters, to simultaneously work on different areas of the parameter space by different people, and have higher confidence at the end of the day that we're getting the right answers for the right reasons. And the next steps are test simulated predictions correctly, then move on to kind of calibrating biomass. We're hoping to targeting some trendy simulations over the summer, and then we'll move on to the nutrient calibration, hopefully in the presence of a reasonable carbon cycle in the fall, and then hopefully we'll have sail and fates being the land surface at NOR-ESM in the end. So yeah, that's all I have.
Great. Thanks, Rosie. I think in the interest of time, let's move on to our group discussion, and folks can ask questions of Rosie or of any of the other speakers. I think we're going to get all of the speakers' pictures back up on the screen if you want to share your video again. So we had some good discussion in the chat. I will welcome either bringing those issues back up to the floor here or additional questions that people have. So I think Gretchen is monitoring the chat here. Do we have any questions in the room to start with for all of our speakers? Yeah. Oh. Okay, well, maybe Gretchen could, will share some of the discussion that's been happening so far. I think Will has it open also. Yeah, Dave.
I'll start with one for Rosie. When you did the calibration with the LEI, after you calibrated for photosynthesis, did you use any of the same parameters, or did you like exclude the original parameters that you calibrated for photosynthesis? And then if you, how do you deal with the fact that that could be some cross dependencies?
You're muted.
In this case, I fixed the parameters for I fixed the satellite phenology specific parameters. And the reason I did that is twofold. The first is just to make it easier, because obviously adding more parameters to the Latin hypercube makes it more complicated to emulate. And the second, well, actually, there are three reasons. The second reason is that at the end of the day, we actually only want for this. The reason I'm doing this is to get like a trendy calibration right now, and for that we want one parameter set. Right, we don't actually want like a mini ensemble. That's at the present time, that's our goal. If our goal was to have a mini ensemble, we would propagate the uncertainty through this process, right, from that's SP through the Latin hypercube. And the third reason is that I kind of feel like, you probably shouldn't be constraining the photosynthesis parameters with LII observations. Like, that doesn't make any sense. Like, you should really only be calibrating parameters with observations that are relevant to those processes. So yeah, but I mean, obviously there's equifinality in the space of the Latin hypercube from the SP runs as well. So it's kind of interesting to think about, what it means to propagate that uncertainty through the cascade. And I have done some ensembles with the GPP parameters in them. But yeah, given this is our first go for this process, it's easier to do it like this.
Bill, would you be willing to pose your question about usefulness of PPEs? What? Oh, you have a different question. Sure.
This is another question for Rosie. I like your framing of kind of inverting the calibration procedure that we're going through, and as opposed to, can you hear me okay?
You talk a little louder.
Sure, I'll try. I like your framing of the calibration cascade as kind of inverting our calibration procedure now is kind of inverting the way that we think about model calibration. And I'm curious, and kind of given this idea of a wide parameter space that you're still looking at with LAI, could you use biomass as another constraint on the parameters that you're already exploring now, or do you not have the right Fates parameters in your ensemble to really do that correctly?
Question. So, my plan is to do biomass next, but the thing is that what I want to do is get the NPP in the right ballpark, using the kind of this particular phase is kind of like the NPP and the LAI at the same time, and then I kind of want to do the biomass calculation in the presence of a reasonable NPP, and then kind of target like the turnover parameters, both the tissue turnover and the mortality parameters in that later calibration. The other thing is that biomass calibration requires you to do much longer runs, right? So the moment I'm doing shorter runs to get to LAI equilibrium, roughly, and I'd have to do like 100 or plus years to get to biomass equilibrium, and so there's a kind of efficiency to be had in kind of constraining this sort of LAI stuff before I get to that point.
Yeah, it's really exciting to see that this is working. I guess I saw that, so the SLA, which we know is a really big, the SLA top, we know that's a big lever in FATES, but we could potentially calibrate that with data, right? Like, and similarly with some of the other allometry parameters. So I guess I'm wondering, yeah, like maybe we don't really need to calibrate, well, we do need to calibrate biomass, but I guess I'm wondering, like, how many of the parameters that we know are really big levers do we want to calibrate with observations, like before we run the model, and then like really constrain our parameter space? And how many do we want to treat as like, we're kind of like, oh, I don't know. What that is.
Yeah, no, it's totally, that's the thing, it's been kind of like higher and higher in my consciousness. Like, because some things you're like, well, okay, I can get this right if I just like yank up SLA, but you know, like at the end of the day, SLA is not that broad of a prior, and so what makes sense, and I think a good approach actually to narrowing the parameter space is to say, actually, we don't want to tune leaf area index with this parameter. Actually, we want to tune leaf area index with parameters that are a little bit less well constrained by the observations. So there's kind of more work to do, right, in figuring out what is the minimum crown area, for example. Like, that's a thing we should be able to know, right? It's not necessarily just a tunable thing. And so it's kind of interesting that this kind of highlights things that we might need to, like, where you might need to work harder at the priors, for example, or indeed, like you said, just say we don't want to tune that anymore. So yeah, we need to. It also, that would make our life easier, right? If we could do that.
I have a big picture question, directed to Booth and to some extent Sanderson. So CMIP6 actually widened the range of ECS compared to CMIP5, whereas IPCC AR6 narrowed it. And I'm sympathetic to the goal that you want to widen the uncertainty, but there seems to be a push to reduce uncertainty. And there was a speaker from the Hadley Center on Monday who said they're going to pick parameters so they fall within the very likely range of ECS. So there seems to be a conflict. The stakeholders want to reduce uncertainty, and scientifically, I think we are underestimating uncertainty. So how is that going to be resolved?
Yes. Yeah, and I speak to that a little bit. I mean, it's a good question, and I think there's a few different responses to that. I mean, firstly, we need to think about like what the role of the Earth system ensemble, is in assessments. Do we, like in CMIP5 and before, it was used as the MME was used as a proxy for uncertainty. In the last assessment, less so, and the Earth system model ensemble was used more as increasingly more as case studies, which then inform general assessments, which may be sent through simple climate models or just used as storyline approaches. And so there's some questions around that, like, to what degree do we expect multi-model spread to represent our uncertainty? But also there's a question of whether we went too far down the line of over constraining the assessments in CMIP6. I mean, or in AR6. Certainly in terms of climate sensitivity and the response that we've seen over the last couple of years in terms of global mean temperature and relative imbalance. I think there's at least there's grounds to revisit the AR6 assessment of climate sensitivity and ask questions as to whether that was too tight. And I think we can learn from the discussion which we had about climate sensitivity in AR6 and in CMIP6, and to prepare us better for how to address these coupled system climate carbon feedback questions in AR7. I think, however we end up ultimately approaching this, we need to see Earth system models as being one pillar of multiple lines of evidence which can inform our general assessment of climate. And in that context, how important, what does spread mean, and what are our requirements for calibration of coupled systems, and how do we tune our experimental design so that we get that trade-off right between coupled process representation on one hand and feasibility of being able to do fully spun up meaningful experiments on the other. This is the discussion we need to have. I'm aware I haven't fully answered your question, but Ben, I'm sure Ben has something sensible to say.
So it is a good question. I think there's a human element to this. So you heard from someone on Monday, I think, talking about tuning down. So we will submit our bottom-up configuration for CMIP7, which has a very high climate sensitivity, so it's 6.4. It's very on a sort of an emotional level, which is perhaps not how we should ever do science, but we've kind of feel very proud that we've had models that people have consistently through different CMIP eras wanted to use to do downscaling, for example, to look at impacts. They're seen as they do regional processes really well, and suddenly we're in this uncomfortable situation where we're asking funders to fund billions of pounds of supercomputing and running flagship runs that we fear would be dismissed before they're even online. I would like to feel that those kind of social elements don't come into our thinking, but there's an element to that. And I think thinking about how we can more safely expose a breadth of feedbacks, I think moving away from the idea of submitting just a flagship can be very helpful. I'm conscious that if you look at CMIP5 to CMIP6 biogeochemistry, the carbon cycle feedbacks actually reduced. So they largely saw a big step change in the number of models, including the nitrogen cycle between CMIP5 and CMIP6. But I also think that modeling groups were aware that their climate sensitivity was going up. And so they might have been a bit more conservative about how they tuned their carbon cycle. So your TCR looked like it was respectable. Whether or not that happens or doesn't happen, I think being able to more openly capture and expose that uncertainty without, I think it helps if we can move somewhat away from that flagship model where we say, as a Hadley Centre, this is our take on past and future change. We can be more honest and say, look, there's a range of past and future changes that are consistent with our understanding of those processes.
I have a question perhaps directed at Ben Booth. Some of the users of our CMIP runs want us to run at higher resolution so that we resolve more physical processes. Some want us to run more ensemble members so that we get a bigger spread of internally generated variability. You're talking about running more ensemble members with different varying parameters. You get a combinatorial explosion of number of experiments. How do you balance all of these? Do you have thoughts on how to balance all of these objectives when we have fixed computational budgets, fixed storage budgets, fixed personnel budgets?
It's hard, isn't it? It's really hard. There's a really big push around Eve and high resolution modeling, and I think we will learn from this. I think we will learn, does resolving two-way interactions where you can resolve convective scale processes change climate projections? And I think that's really important. Thinking back to that's my second slide I think I showed, where looking at convective permitting regional runs, they're probably teaching us a lot about climate change on the regional scale, that convection shifts into the autumn, which we would not have known if we hadn't run them. But there is that wider context in that they in that case, they don't capture drier winters or warmer winters. And so I think we do need all of those strands, and how we resource that is challenging. Maybe as a global community, we need to agree that we share that in some way. Maybe we all certain groups will want to lead more on one or the other. As long as that collective organization can capture the resolution and the complexity and the ensemble size, I think, I don't know, I'm sure that Ben and others have thoughts.
Go ahead, Ben.
Yeah, just briefly adding to Ben's thoughts on this. I mean, this came up in the chat a bit as well. Like with PPEs, I think we need to think, like, obviously the Met Office have done an amazing job in being able to produce coupled carbon emission-driven PPEs, but there's still a lot of value in subcomponent PPEs in terms of putting the results of the fully coupled flagship model in context. So AMIP simulations, land-only simulations, where we have some sense of what the carbon feedback uncertainty and the sort of like land coupled, the land atmosphere coupled process uncertainty is, would, especially if those are used in parallel with emulators and simple climate models, which are able to translate some of that like single component uncertainty into coupled system response. It's not ideal, but I think we have to think like what all of the potential tools are, especially if a CMIP, some sort of coordinated CMIP7 PP MIP exercise can happen. I think thinking about how that can be done in a computationally tractable way might involve thinking beyond huge ensembles of fully emission-driven spun-up models.
Great. We are out of time. It's time for us to take a break here, but thank you to all our speakers. One more round of applause for everyone. And we are reconvening at 10:30. Someone want to check schedule? 10:30. We'll reconvene at 10:30 for another round of talks.
Thanks, everyone. Bye.
folks are coming back into the room here, I wanted to invite our first speaker to bring their slides up on the screen so we can get that out of the way.
Can you guys see that?
Hang on just a sec. Still, yes, now we are able to see it.
Okay, great.
Okay, so welcome back from the break, everyone. Thanks for a good first session this morning. We are back for another one now. We are going to start with, again, we'll remind you that we have some time for a discussion at the end. So similarly, welcome folks on Zoom to put questions in the chat, and we can read those out in the room or bring them back up in discussion. And we are going to start today with Andrew Wilson. Go ahead, Andrew.
Hi, everyone. My name is Andrew Wilson, and I am working at Oxford with Samar Kadawala on Earth system model spin-up. So I'm sure that you are all very familiar with the spin-up problem. Just as a reminder, Earth system models need to be spun up to a steady-state pre-industrial equilibrium, and this can take a really long time because of the timescales associated with the deep ocean and the terrestrial carbon cycle. So the standard approach is to just run the model in time until it equilibrates. In CLM language, this has been called native dynamics. Today, I'll probably refer to it as direct integration because you're just integrating the model in time. And because I come from a math background, I also will call it a Picard iteration. And a natural question is if there's a better way, which hopefully I can answer today. So as I mentioned, I come from a math background, so just bear with me a bit as I kind of motivate the spin-up problem in a mathematical sense. Essentially, we are trying to solve a fixed point problem. So what is a fixed point problem? Well, it's defined here in this top box. If we have some function g of x, then a fixed point x of g is an x such that you apply it and it stays in the same place. So g of x is equal to x. And the most basic way to solve a fixed point problem iteratively is through a Picard iteration, where you define your iterates by xk plus 1 is equal to g of xk, which gives you this slowly converging sequence that hopefully eventually will make it to a fixed point. Now, when thinking about Earth system model spin-up, you can actually think of it as solving a fixed point problem. So if you define the function g, the fixed point function g, as running the Earth system model for 1 year, then a spun up state is a fixed point of that system. Because if you run the model for another year, you've stayed at exactly the same place. You're at a fixed point. So what we do is we try to use sequence acceleration methods for solving fixed point problems to find a spun up state faster, essentially. And specifically, we're using Anderson acceleration, which uses past iterates to help kind of form the best next guess at what the spun up state should be. So again, bear with me through a little bit of math. This is the last slide with that, I promise. But if we had before this kind of slowly converging sequence where x2 was g of x1, x3 was g of x2, now instead of just applying g, Anderson acceleration uses a linear combination of the m previous iterates to form your next iterate. And here m is often called the memory parameter because it kind of says how much of the system's past is included in making your next guess. And the coefficients of this linear combination alpha are found by solving a small constrained least squares problem where we're trying to minimize the residual g of x minus x. And again, remember that if x is a fixed point of g, then this residual would be 0. So what we're doing when we're finding this linear combination is trying to force x to be as close to the fixed point as possible. And what we found is that if we use a memory of about 50, that works well for ocean models, and a memory of about 10 to 15 works well for land. And it's important to note as well that solving this least squares problem has a very low computational overhead, especially compared to actually running one of these Earth system models. So we're kind of able to do this acceleration almost for free in the scheme of things. Now, one of the biggest benefits of our workflow is that it's really quite simple compared to a lot of other spin-up acceleration techniques. Mainly, there's no real modification necessary of the underlying Earth system model code. It's essentially entirely black box. The Anderson acceleration code is written in Python and sits in a wrapper outside of the model. And this wrapper handles running the model itself, and then utility functions that we've written in Python handle read-write operations on the model restart files. So the way this works is that the Anderson acceleration code will tell the model to run. Once it's completed, it reads the state of the model from the model restart files. Then within Python, it solves that constrained least squares problem and kind of creates basically the next iterate, which is kind of what the next state is, hopefully closer to the fixed point. It then writes that state back into the model restart file and we'll call the model again. And kind of that's how the iterations work. So from the model's point of view, everything's running as normal, right? It's just reading restart files, writing restart files. But what we've actually done is change the state of the model to be closer to that steady state equilibrium. For ocean models, we're running one instance of Anderson acceleration for the whole ocean. And for land models, we run one instance of Anderson acceleration per soil column because they're independent. And as I said, it's pretty simple. So I've included this kind of screen grab here of some Python code. I wouldn't expect you to know exactly what this all does, but this actually is what handles calling Anderson acceleration for each individual column for CLM. And, you know, it's possible in only like 10 or 12 lines of Python. It's really quite easy once it's set up. So we've already had good success with this. We've applied it to joules and seen a 10 to 20x speed up compared to standard direct integration approach. We've applied it to a few different ocean models, Nemo Piscis, Nemo Medusa, and MIT GCM Bling, where we've seen 7 to 10x speed up. In all these plots here, the red is the accelerated spin up and the blue is kind of your standard spin up. So you can really see like how much faster it's getting to that spun up state than the normal approach. And some really important plots here as well are these ones here in the bottom right, which is a point-by-point comparison of the Anderson accelerated spun up state with the standard method spun up state. And so the one-to-one correlation means that we are getting to exactly the same final state as you would with a traditional spin up. So I understand that some of you might be uncomfortable with manually adjusting restart files, but at the end of the day, we get to the exact same place even with our method. What we've been doing most recently is applying this to CLM. So right now we're working with a 3 grid cell setup with points in Alaska, Illinois, and Brazil for varied dynamics. We ran 50 years of accelerated decomposition spin up, followed by 50 years of standard spin up just to perturb away from an initial condition, and then turned on our Anderson acceleration. We are using GSWP 3v1 forcing and repeating only year 1901 to ensure periodic boundary conditions. So here I've got 2 different columns, one from Brazil and one from Illinois, where we have the soil 3 CVR. Each of these lines represents one of the 25 layers of the soil. And, you know, again, it's really pretty exciting initial results. Within 100 years, we're basically at a steady state. Whereas, you know, the direct integration, even at 700-800 years, is still very slowly adjusting. In fact, I haven't even had full time to run out the standard spin up yet. So that's something that'll come a little bit later, but it looks like they're going to the exact same place. This is, again, you know, I'm running at the column level, and because of the way that CLM breaks down the columns and the PFTs, the number of PFTs is obviously non-constant. So that's not a problem for us. You know, for this column in Brazil, there's only one PFT, so we have one value of leaf carbon, and that's doing really well. For this column in Alaska, there's 3 different PFTs, and all 3 of them are getting to the right place. So again, really exciting results at the PFT level as well. Finally, looking at some grid cell and global diagnostics. On the left, we have yearly average net biome production, and on the right, we have yearly average total ecosystem carbon for each grid cell. For the total ecosystem carbon, again, really good acceleration, similar to what we saw before after about 100 years of Anderson acceleration, we're pretty much at a steady state, whereas, you know, at 800 years, this point here in Brazil still has a long way to go. For net biome production, that's maybe not the best diagnostic to look at for a 3 grid cell setup, but it seems to be used a lot in global convergence criteria. So I wanted to include it just to kind of show that we're seeing some pretty promising results here. But, you know, once we move to a global sparse grid, I think we'll have a better way to compare that to the standard method. So this isn't all perfect. You know, we've had some really good results, but we've also uncovered some rather odd behavior in the model, if I'm being completely honest, that I can't totally understand. So the first one that I want to point out are these oscillations, which is happening in this point in Brazil. There's just totally periodic oscillations. There's also this behavior where it almost looks like some kind of thresholding that's happening in the model. And this is really difficult for Anderson acceleration to handle. As I mentioned, it's a method for solving a fixed point problem. And this is obviously not a steady state, so it's not a fixed point. So there's no real way that we could expect Anderson acceleration to work on this. So that's something I would love to kind of maybe dig into a bit more with some of you who might know more about the underlying BGC code, but I can't really think of a reason why this would be happening. Also, there's a few columns where there's some noise in the tracer values, like this one in Alaska. It hasn't been as big an issue for Anderson, but again, that's not a true steady state, so it does add some difficulty for the method. For future directions, then the immediate next step is really algorithm tuning, and then we'd like to get onto a global sparse grid to try and test this at a global scale. And I think once we get to a global sparse grid as well, that'll help us with determining what convergence criteria we're going to use. Ultimately, I think that there will need to be some sort of a short standard spin up after we turn off Anderson acceleration to let everything kind of settle. But that's a little ways in the future. And right now we don't have the carbon isotopes in the model, but that should be easy to add. And we don't, you know, from a method point of view, it's very easy to add, and we don't expect it to have much of an impact in the performance at all. So with that, I will open it up to questions. I know this was really rapid fire, and I kind of went through a lot very quickly, so I want to leave a little bit of time. And I've also got just some papers that could be helpful if anyone's more interested on their own. So yeah, with that, questions, happy to dig in anywhere.
Great, thank you. We have time for a question.
Hi, I'm wondering about the ocean problem, and as we and the case where we're beginning to resolve chaotic parts of the motion and don't expect the solution to be steady state or even cyclostationary, is it possible to define a filter so that you're converging the larger, slower scales while letting the chaotic scales to evolve naturally?
Yeah, so we haven't gotten into anything with like eddy resolving or chaos models yet. Right now, we're like most of our ocean model testing has been done at 2 degrees. We expect it to work well at 1 degree, and there's, you know, immediate testing that we're doing kind of in the next month or so with Nemo Medusa at 1 degree to just ensure that that all works as it should. Eventually, we would like to do some testing with something like a 1/12 of a degree model, but that's just right now a little bit further ahead, and so we haven't quite gotten there. So, short answer for your question is I'm just not sure if it's going to work at that level yet, but it is something we'd like to test in the future.
Go ahead and bring your slides down, and we'll move on to our next speaker. So Greta, we see your picture, and we're waiting for your slides. Excellent. So next up is Greta Shum.
Great, thanks. Yeah, hi. I'm excited to share this project I've been working on as a graduate student in atmospheric sciences at University of Washington in Seattle. So we've been trying to understand what aspects of model structure in simple climate models exert control on carbon sinks and how that influences carbon budgets for climate mitigation. So this is all in the context, of course, of predicting future carbon sink behavior as we decarbonize, and how that's contingent on our ability to represent ongoing carbon fluxes in the context of decreasing net emissions through changes to anthropogenic emissions themselves or to changes in the land or ocean carbon sinks. So we're specifically interested in simple climate models or climate model emulators, depending on the specifics of the model. And here on the right is a model structure of FAIR, which is an example of an SCM. And we're running FAIR with CO2 emissions to get concentrations and goal mean temperature. And to do this, FAIR assumes 4 characteristic lifetimes of CO2 in the atmosphere, sort of abstracted from the processes themselves, and about 1/4 of each annual emission of CO2 is then allocated to each of these lifetimes or timescales of removal, and then they're summed up as a cumulative sink. But the SCMs were largely built and tuned by fitting their various parameters that represent processes in ESMs to ESM output for historical simulations, idealized simulations, and also CMIP scenarios, as well as observations. But because these SCMs are so lightweight, they've been used in a lot of policy context for their explanatory power or just to make assessments of mitigation. You might recognize a few of these examples. So first, if we sort of look across SCMs to see how they behave in a decarbonization setting, we took 3 operational SCMs that were used in those examples I just showed. And these are schematics of the carbon cycle modules within each model with their atmospheres in pink and their various sink components below. You can see that Magic Sea and Hector contain some form of a land carbon cycle in green and ocean carbon cycle in blue, but they vary in how they represent that ocean, with Hector representing explicit circulation, whereas FAIR having those more removed from processes level sinks. So these 3 models do a great job reducing our record of historical concentrations from historical emissions. And we can even compute a remaining carbon budget that's fairly consistent with some threshold of warming. In this case, I set a warming threshold of 1.5 C increase from pre-industrial, considering warming up to 100 years after emissions cease. So you can see that the models vary by about 100 petagrams in how much carbon can be emitted from 2021 in order to stay below that threshold due to differences in both the transient response to warming and temperature change after emissions, or the ZEC. In this case, all of the models exhibited a cooling after emissions cease, or a negative ZEC. And for context, we're emitting about 10 petagrams carbon annually. And we can translate this RCB to an implied linear ramp down in emissions to illustrate this mitigation application. And the models vary by about 20 years in when net zero would have to be reached to stay below that warming threshold, but all are before 2050. So to find out what's sort of controlling the evolution of atmospheric carbon and temperature, we replaced the gas cycle module in FAIR with a new carbon cycle model that's sort of on the opposite end of the process representation spectrum from FAIR. This model uses a 9-box land carbon cycle with 3 vegetation boxes representing leaves, litter, and soil. Leaves, litter, and soil with various pools. So leaves now contain wood and roots as live pools. And if you're familiar with the CASA or Century models, that's what this model is based on. And the ocean, it has 7 boxes with 4 surface boxes and prescribed circulation. So this is based on the Togweiler 1999 ocean box model. So I'm calling this new carbon cycle module within FAIR BGC, and its explicit representation of the carbon cycle process allows us to distill what's actually driving changes in carbon sinks and temperature. So we perturbed the parameters in both versions of FAIR to sample across different carbon cycle feedbacks. And in the default version of FAIR, this consists of 3 parameters that influence carbon cycle feedbacks through the alpha lifetime parameter, if you're familiar with FAIR. And we also vary 11 parameters in the energy balance model that using ranges determined by the calibrated constrained ensemble that's reported with FAIR. And then in FAIR BGC, we perturb 5 carbon cycle parameters that characterize important feedbacks. I want to call particular attention to this size scalar parameter, which is an ocean circulation scaling factor that uniformly adjusts transport between the ocean boxes. So we set up 1,000-member ensembles using Latin hypercube technique, making changes to all the parameters at the same time. And then we constrain each ensemble to observe CO2 and temperature change. And this is what we get for our various carbon budgets compared to the global carbon budget on the left. In the middle is fair default with this atmosphere in pink, and the longest lifetime, that billion-year timescale, never becomes visible, meaning the carbon that's allocated to the longest timescale actually never leaves the atmosphere. And then on the right, you can see the fair BGC model, where you see the land is taking up more. This is carbon flux in the ocean for the whole time period. And on the whole, these models are producing the same atmospheric carbon pool as a balance of very different fluxes of carbon. And we can run that same step function emissions trajectory where we set emissions to a constant 10 petagrams carbon per year for 100 years, at which point we reduce emissions to 0, or the ESM flat 10 ZEC. And this is nice because it cleanly calculates the TCRE and ZEC. And the histogram here shows you the TCRE times 1,000 petagrams carbon. And you can see that the distributions overlap very well, and both ensembles include just a few higher TCREs, but they're about the same. And if we look at the evolution of ZEC, we see that the temperature change we see after emissions cease. You can think of this as like the delayed response of temperature. There's a slight difference in their long-term temperature, with fair default showing a generally positive ZEC, and then fair BGC showing a mean negative ZEC. And so to characterize and compare the total sink rates shown in yellow, this would be both land and ocean added together, we fit exponential lifetimes of carbon in the atmosphere to emissions, which is shown in the dark blue, with models of 1, 2, and 3 timescales of removal. So the fitted models with the 3 lifetimes of carbon uptake sort of resemble fair default itself as it comes naturally. And each have something like 330 and 300-year timescales of uptake for tau 1, tau 2, and tau 3. So this allows us to look at how each of the parameters we modified within fair BGC influences the diagnosed timescales of uptake in fair BGC. And we see like a nice correspondence between the processes that we think should be operating on shorter, long timescales. And you can see in particular that size scalar, which is the ocean circulation scaling, has the strongest influence on the tau 3, which is the longest century scale lifetime. But if we ask what the explanatory power of these taus is on our metrics of warming, TCRE and ZEC, we see that the explanatory power is very small. For context, in C4MIP, this is sort of a different method, but you can see that at least some of the carbon cycle response to CO2, some of the TCRE is explained by this carbon cycle response to CO2, but the largest contribution was this sort of climate feedback response. And by comparison, the same thing, we can look at our explanatory power of energy balance model parameters and see that the climate feedback parameter can explain almost 50% of the variance in TCRE and contribute strongly to ZEC as well. And the other 2 parameters that contribute strongly are kappa 2 and kappa 3, which are these coefficients in FAIR's 3-layer energy balance model. Kappa 2 regulates heat transfer from the atmosphere to the mixed layer, and kappa 3 regulates heat transfer from the mixed layer to the deep ocean. So this makes sense considering the structure of FAIR and the fact that the EBM is what's directly controlling temperature, while carbon cycling is sort of removed from temperature. But one thing you might notice is that there's no structural link between what controls carbon cycling and what controls energy balance, so the parameters that control those processes. When we think about the processes that those parameters are trying to represent, you might realize that one thing that should influence both is physical ocean circulation. So the ocean circulation will affect both, heat uptake and carbon uptake transport to the deep ocean. So if we exogenously correlated the parameter values that we generate for ocean circulation scaling and heat transport to the deep ocean, processes we know should be linked, would we change the influence of ocean carbon climate processes on the timing of warming? We went ahead and generated a new Latin hypercube ensemble for the FAIR BGC model with those correlated parameter values you see here. And again, we constrained to historical CO2 and temperature change. And if you recall the distributions of TCRE from our initial PPE, the new correlated FAIR BGC experiment had stronger TCRE values, that is the transient response to cumulative emissions. And what about ZEC? Here I'm showing you the original ZEC response over time, and we see adding this connection increases the spread in ZEC, but we also see slightly more negative ZECs. And just sort of stepping back to look at what we did before we correlated any parameters in a historical scenario. For some pulse of emissions, if you had a sluggish ocean circulation, you get a slower sink and an enormously high CO2-driven warming response to emissions, and the opposite for fast ocean circulation. And when we constrained the observed CO2 and temperature change for this emissions period, we end up selecting for values in the EBM parameters that compensate for those carbon-driven forcings. And then when we correlate circulation and ocean heat transfer, we insist on a corresponding ocean behavior that affects climate separately, leading to a different tuning for our other EBM parameters when we constrain for ensemble members that match CO2 and temperature. So that's exactly what we see when we look at those parameters. In particular, we see a shift in the constrained values for the climate feedback parameter, which has an inverse relationship with climate sensitivity. So in our correlated ensemble, we end up selecting for lambda values that give us a stronger temperature response for a given forcing. And it goes the other way too. So the correlation with ocean heat transport now has a circulation leading to a different compensating land carbon cycle feedback. So we see a shift toward lower CO2 fertilization, meaning a dampened land carbon feedback. And this sort of can even be taken to the remaining carbon budget. I'm showing you fair BGC in green has a similar remaining carbon budget to fair default. But when you look at the remaining carbon budget for this correlated ensemble, the RCB is so small that it actually has a required ramp down by 2023, which did not happen, of course. So what we're finding is that connecting carbon and climate dramatically changes the decarbonization rate needed for mitigation through changes to the assumed relationship between thermal processes and future temperature change, even though both may have been consistent with our observed climate. So there are implications for the CESM community. There's a lot more to understand about what these connections should be, but we're going to have to use ESMs to see the range of behavior as driven by explicit BGC processes, not just fitted parameters. Maybe we could even use the sensitivities of these SCMs to guide the calibration cascade or the format of any carbon cycle PPE that might enable us to sample across the specific realizations of these trade-offs. So that's all I have, and thanks for listening. Take any questions.
We have time for a question.
That's great to see this work. I'm curious about your last bullet point and like what's the handoff that needs. It seems like there's a lot that could be, but you could say more about your last bullet point about what's the handoff between PPEs and this simple model.
Yeah, I sort of was thinking about that in the context of the last few presentations and like tweet what I could possibly say toward that. And I think maybe you're the one who is saying, well, maybe we have to think carefully about, you know, carbon cycle PPEs and like how to use them best because they're so expensive. And I guess one thing that I think you could use SCMs for is to like define some questions that you're trying to answer through the carbon cycle PPEs, specifically driven by what parameters you're going to be tuning the ESMs, the SCMs to. So, you know, something like ocean circulation, for example, I think is a really important one. So if we specifically sample across realizations of those ocean trade-offs that we might, ocean-driven, you know, climate feedback trade-offs, I think that would be worthwhile. But given the constraints of the PPEs in general, I think looking across more SCMs would be necessary too, to like, as you can see that they have a lot of different structures that have different trade-offs. So it would require thoughtful consideration of like what the take homes are from those PPEs and how we're going to fit them to the SCMs. Yeah.
Thanks,
I was
Greta.
mostly just inspired by the previous presentations. Yeah.
All right, great. We have more time for discussion at the end, so we'll welcome our next speaker up, who is in person. Peter Lawrence is up next.
Yeah, thanks. Is there, yeah, that's good. Great, thanks. So what I'm going to do today is take you through an emission-driven configuration that we're using out of our growing convergence research climate interventions project. But this is the same configuration of the model that we're using for the flat 10, and also we're going to be using for the HOPE ensemble we want to run for SSP 119. I'm not going to go through all the climate interventions. I did that yesterday. I sort of went through that component. What I would really like to do today is go through and explore this configuration of the model, how it reproduces the carbon cycle, and its ability to do a lot of climate things. Okay, so one of the first things to think about is we're using CSM2, like 2.1.5. This is a well-established model. It's been used for the LENS2 project, the CMIP6 project. So it's a version of the model that we know pretty well, but what we're doing is we're trying to do it in a novel and new sort of configuration. One of those components is like we're putting it into this emission-driven space. So fossil fuel CO2, methane aerosol emissions are all prescribed to the model. And then we have on top of that, we have active fire aerosols from the fire model coming through, and we're having biogenic aerosols coming through from the Methane model as well. We're running this across the historical period and across 3 SSPs for our climate intervention work. There's a good overlap between SSP 119 with the HOPE project, so this is sort of a good way to set this up. There's a lot of things going on here. We've also got the new ocean biogeochemistry, which is Kristen Crumhart and I think Keith Lindsay has discussed at length, and this is the new marble model. It's nice because it has calcifying coccolithophores, and it also allows you to tie into the feisty fish model, which is like really exciting. There are 8 climate interventions that we're putting in on top of this model, but I'm not going to go through those today. But what I really wanted to do is say there's a lot of things going on in this model, and there's a lot of processes that are really valuable for us trying to explore in terms of the climate system. But we need to be able to assess them, be able to work out what they look like, to be able to have some sort of confidence in their usability. So one of the first things we're doing is like going through the historical period and looking at the model in both its CO2 concentration driven versus having this fully active CO2 and fire and biogenic aerosols. And what we can see is that we get the top 2 panels there show the GIST temperature and the best temperature. They're over different time periods, so the GIST temperature is from 1900 to 2022. But what we can see is that the 2 bottom panels on the left is with the concentrations given from CO2, from CMIP6 versus what happens when we run the model with a full coupled climate, carbon, and aerosols. And what we do is we get a reasonably good representation of the historical period. We can also see in terms of precipitation, compared to the NOAA GPCP product, we don't really have big differences between the models in terms of either the annual precipitation patterns nor the looking at the statistics in the model. So what I would like to do is just quickly, first of all, look at the aerosol component of it and explain what we've done to get active aerosols working. So there's a lot of plots here, but if you look at the bottom left-hand plot, this is looking at the aerosol optical depth. And the red line is where we've got fully active fire and biogenic aerosols from Megan. And the blue line is the prescribed CMIP6. And so what we did is we had to tune up the emission factors for both the fire model and the Megan, which we did to hit the CMIP6 targets. The reason why we did this is if we didn't hit the CMIP6 targets, the model is tuned up for these particular aerosols. And so in the default configuration, we had a model that just cooled very rapidly. So by changing the black carbon, secondary organic aerosols, the sulfates, and the particulate organic matter components to be able to better match the CMIP6, we were able to get a model that could actually reproduce the temperature record of the 20th century, the historical record. Next thing I'll do is move on to the carbon cycle, which has been really interesting. And so what you see here is the red line is with the fully coupled active model. The blue line is what happens when we prescribe CO2 concentrations. And then the black lines in the top left case is atmospheric CO2 as the CMIP6 forced value. The blue line is the tracer that was modeled in a concentration-driven run. And the red line is what happens when you've got a fully coupled carbon cycle. What we can see is that when we couple the model with the carbon cycle, we get a much better representation of CO2 growth through the historical period. The other plots, the bottom left plot shows the CMIP6 emissions, fossil fuel emissions in CO2 versus the Global Carbon Project. See that they actually match up really nicely, which is great. In the bottom right plot, we can see what happens with the ocean uptake and accumulated carbon uptake, CO2 uptake. We can see that going from the blue line, which is when we have concentration-driven runs, we actually miss the Global Carbon Project. But once we couple the model is now actually taking up more carbon, and and so negative here is an actual drawdown of carbon. We see that the model is actually doing a better job. If we took a look at the top right panel, we can see that the blue line was quite a lot more carbon coming out of the total land through the time period. And when we actually couple the red line now, actually brings us closer to the Global Carbon Project. Okay, so what's really going on here? Like, what can we see in terms of changes in both the CO2 concentration and the gross primary productivity? So we see that from the land model's perspective, this is all land carbon cycle. We can see that the higher CO2 that we had in the fully coupled carbon cycle model actually resulted in slightly higher gross primary productivity across the whole time period. If we look at the bottom right panel here, this is from the ILAM package, and the red line is showing the CO. Sorry, and unfortunately the colors are swapped here because this package is different to the other part of the package. So what we see is that the blue line, which is the fully coupled model, actually draws down more carbon through the period than the red line. But both are really close to that Global Carbon Project, Global Carbon Project's trajectory of carbon uptake by the land over the 1960 to 2014 period. When we look at these spatial plots, we can see where that extra carbon is coming again. So the blue areas represent where the fully coupled model is drawing down, and this is the bottom left map, sorry, just so you can see what it looks like. The bottom left part shows where the carbon is being taken up, and these blue areas are where the fully coupled carbon cycle is taking up more carbon than the prescribed concentration carbon. And see that's in the tropical forests and across the boreal forests. Is typically where we see the larger take-up of carbon. Okay, so going into the next part, what we can see is from the perspective of the land surface, this higher CO2 represents a slightly higher temperature in the land, which is the blue in the middle top plot. We can see the gross primary productivity represents a slight increase in the carbon photosynthetic rates. And then the bottom left-hand plot here shows that the total vegetation carbon is responding to this slightly elevated CO2 and sort of responds by having more carbon in the total vegetation carbon there. We see there are not large changes in terms of global hydrological cycles. We see latent heat flux. We see slightly more canopy evaporation with these slightly warmer temperatures at the end of the historical period. But that's basically it, the only changes there. Going on to look at different parts of the carbon cycle to try and think about, well, how is a fully coupled carbon cycle model look different to a concentration-driven run? So the top left-hand plot here shows the conversion flux. This is when we're doing land use and we're changing our plant functional types through time. And basically the red and the blue line lie on top of each other. So we don't have a big impact in terms of the land use, land cover change component of it. Our wood harvest, which is the middle top plot, that also lies directly on top of it itself. When we go to the right-hand plot, however, we see that the red plot, which is the concentration-driven CO2, actually has slightly higher net ecosystem production than our fully coupled cycle, which is interesting because, like we were thinking about, the GPP is higher in the fully coupled cycle. We see there's not really big differences in the fire carbon losses, and net primary productivity is pretty similar as well. So these big differences come out in heterotrophic respiration. So we have more carbon, and we're now losing more carbon through that process as well, with slightly warmer temperatures and the higher CO2 levels. Okay. So this is moving on to what we're doing next. So it's really interesting to look at the carbon cycle and the climate model and the climate components of this configuration of the model. But we know that one of the reasons why we're using this model is it has all these embedded impact components to it. So we can look at the crop model, we can look at the fisheries model, we can look at the urban model. And this is look at wildfires versus crops. We can look at water availability and irrigation demand, wood production and ecosystem health within this modeling framework. So that's why we're building up this fully coupled cycle. Because of where we are right now, we haven't done a lot of this analysis yet. This is the next stage of the analysis, to start looking at agricultural yields, looking at the fishery model, but this is a component that we're going to be looking at next. One of the key things that have come out of this is our collaborator, James Weber, who's now at Reading University, went through and looked at a reforestation scenario, which is part of our suite of climate interventions. And what we were doing is trying to work out like the ability to remove carbon dioxide by reforestation in these experiments. And so what was really of quite a large interest was the fact, yes, we can get a big carbon drawdown, but there are albedo responses, there are methane responses, and there are also aerosol responses. And so it's really important to have this complexity. And Dave put this slide up on Monday. This is one of the key reasons why we want to have a fully interactive, fully coupled climate carbon cycle aerosol model. Okay, just finally thinking about, like, so this is a CAM6 version, so it's a low top model, and a lot of our climate interventions, well, a number of our climate interventions are going to be around stratospheric aerosol injections, which require like a high top, fully resolved stratosphere. To do that, we are running Wacom configurations in line with what we're doing here with the fully coupled carbon cycle model. And what that allows us to do is we run, in this case here, we're running out the SSP 245 warming, and then we put stratospheric aerosol injections into the model, which is part of what's called the RISE. The RISE simulations only went to 2070, sorry. So what we're doing is extending out all of those RISE simulations. We take the aerosol forcing, the stratospheric aerosol forcings out of these Wacom models, and we're going to put it now into this fully coupled carbon climate version of the model. Okay, I'm gonna finish it there for questions, but it's an interesting configuration, and I'd like to discuss it a lot more with people.
Great. Thank you. We have time for questions.
Nikki says, thanks for all the work you're doing to ensure the success of this project. Things are looking great. Do you have a sense of the timeline for CESM HOPE now that the emissions-driven simulations appear to be working well in CESM 2.5 or 2.1.5?
Sure, and I'll maybe throw it back to Dave a little bit, but yes, we've got a lot of the simulations. We'd like to have them done by the end of the year. I think that would be a nice time frame. What would you think, Dave?
Yeah, I guess that seems reasonable. I mean, you didn't mention the fact that we still have to figure out this BECS issue.
Right.
And that's, you know, that's sort of the stumbling block. Otherwise, we could just do it right now, and it would just be turning the crank. But we have to figure out what to do with the carbon and make sure all the accounting for the BECS between the actual emissions coming from the IMs and what we're simulating the model are all lining up and not double counting. So that's a little uncertainty in this.
Yeah, maybe sometime in early 2025 then, maybe would be a better guess, hopefully. Okay, okay.
Dave says end of the year sounds good. I have a follow-on question to that, which is related to what Ben Sanderson put up earlier, that there's this larger discussion about whether Earth system models should be doing the BECS themselves or whether they should be taking the fluxes from the IAMs. Would you, Dave or Peter, want to comment on that?
We've thought about it at sort of length, and one of the things is you can do it either through negative emissions, like so you change the fossil fuel emissions to offset to do an offset of the total amount of liquid fuel that you're producing from the bioenergy. But it's complex because you don't know that before you start the runs. So we were thinking, we don't want to do a large amount of reworking of the model. We're trying to do as much of these scenarios with forcing files as we can. So if we're adding the Yanyon's bioenergy in there, there is no actual pools to draw carbon back out of the atmosphere right now or mechanisms to do that. So I think Dave and I have talked about it a number of times. We come up with multiple different answers. We haven't really come to a final conclusion how we're going to do it yet. But if people have guidance for that, we would be really interested to hear it. And it's also complex because there's the residues from the crops as well. So it's like if you have switchgrass or miscanthus, you're harvesting the crop, you're taking that carbon out of the cycle. Do you then re-release it, or do you use carbon capture and storage to like put it into some sort of long-term reservoir pool?
Right, yeah, what happens to the residue? Because it seems like our system model dealing with the photosynthesis and respiration parts of it makes a lot of sense to me, anyway. Great, thank you. We should move on to our next speaker, who is remote, I think. So can we switch back over? Moving on to Jiaming Lai. Just in the room, we're still working on getting your video up on the screen.
Can you see the screen?
Your slides are on the screen. We're still working on getting your video up there, but I think it's on our end. Great, there we go. Go ahead. Take it away, Jiaming.
Thank you. Hello everyone. I am Jiaming Lai, a PhD student in Cornell University. I'm very happy to be here and share my recent research related to the modeling of carbon-30 discrimination, and I focused on the impact of mesofield diffusion. Okay, so first is about the motivation part. As you know that the terrestrial water and carbon cycles are very important element in Earth system modeling because they have great effect and feedbacks to the climate change. And these two cycles are closely linked via the plants, because plant can regulate its stormwater conductance to control the trade-off between the carbon gains via photosynthesis and the water loss via the transpiration. So this leads to a variability in the leaf level water use efficiency in response to the environmental changes. For example, under historical increase in the CO2 concentration, plant will increase its leaf level water use efficiency. Also, when it faces some water or heat stresses, plant will also generally have a higher leaf level water use efficiency. So it is very important to understand the variability of the WE in response to environmental changes. Previous studies have used different approaches to achieve the understanding of WE. For example, some of them use satellite product of GBP or ET to derive that, or they can use site level flux measurement of carbon and water cycle, or use some field experiment like FACE to analyze the WE variabilities. However, those approaches, they have a common shortage that the data was only available at a relatively short temporal period. By contrast, we have another type of data, which is stable carbon isotope, C13. So C13 compared to the more common C12 is that it has one extra neutron. So it is heavier. And as a result, it could move and react more slowly than the carbon-12. So because of this slower movement and reaction, when plant uptake the CO2 from the atmosphere, it will selectively uptake the C12 while discriminate against the C13. So this phenomenon is known as carbon isotopic discrimination, or delta 13. And delta 13 can contain valuable information about the carbon and water cycles. So it is very important to understand the WE. And the largest advantage is that for the delta 13, we could have long-time series data to analyze it. For example, many studies have used the data embedded in the plant materials like tree ring records to infer the C13 to C12 ratio of plant materials and to infer the historical change of delta 13 and leaf level WE. We also have some data from the atmospheric side, which can help us to diagnose the C13 to C12 ratio in the air, and we can also use it to diagnose the delta 13 long-term change. For example, we can use some flask samples, which are available for recent decades, and we also have ice core data, which are available for a much longer temporal period to help us analyze it. So now let's move to the simulation part. If we want to represent the carbon isotopic discrimination in the models, we need to understand its underlying processes. So when we consider the pathway of CO2 from the air to be fixed in the plant cells, it can be composed into 4 different processes, like the gas diffusion across the leaf stomata, that across the mesophil and the carboxylation and photorespiration. So each of these 4 processes, they can undergo carbon-30 discrimination. So if we use an equation to represent the delta 13, we can use this equation, which can be also composed into 4 different components. Each component corresponds to one of these 4 processes. So this looks good. However, in most models, including the CLM5, they currently just use a simplified equation, like in this blue box. And you can see that this simplified equation only considers 2 of these 4 processes. Instead, they just ignore the effect from the mesophil and photorespiration. So there are reasons for ignoring these 2 parts. The first reason is that the GM, which is mesophil conductance in this equation, it is not explicitly simulated in models including CLM5. So this makes it very hard to explicitly implement this mesophil conductance part into this equation. And the other part related to the photorespiration. Some studies think that the effect from the photorespiration on the delta 13, this magnitude is very small, so it could be ignored. However, in 2017, one paper by Dr. Ralph Koenig used the atmospheric records to infer a long-term increase in the delta 13. And he used this theoretical equation to infer that the contribution from the mesophil conductance and the photorespiration part, which were ignored in current models, they actually are very important because they together can explain a very large proportion of this secular increase in the delta 13. So it may be not accurate to ignore this part in current model. So this estimate about this 70% contribution from mesophil and photorespiration is very important, but it has its limitations. First, this estimate was based on representative values of mesophil conductance and photorespiration, and they just assumed they are constant over space and time. And the second limitation, this estimation is based on atmospheric records, which may be less sensitive to the C4 plants, so they just ignore the C4 plants, which has a much smaller delta 13 magnitude and are continuously expanding their global distribution. So this led to the challenge that it still remains unclear what are the effects from a spatial temporal dynamic mesophil conductance, photorespiration, and C4 expansion on the delta 13 patterns. So in our research, we plan to update this original simplified equation in CLM5 related to the delta 13, and we replace it to this more complete equation. So we used a process-based model of mesophil conductance developed by Dr. In Sun in 2014, which has been applied to CLM 4.5. So we want to ask first size question is that what are the relative contribution of the C4 expansion, mesophil conductance, and photorespiration to the observed long-term growth in the photosynthesis discrimination, and what are the variability among different biomes? So our results to answer the first science question has identified a significant contribution from the mesophil conductance. So because mesophil conductance is also a key element in the gas exchanging system, we want to ask the second science question is that how an explicit mesophil conductance implementation can affect the response of WE to the environmental changes. So this is the result. First, we just compare the delta 13 trend from the original CLM5 equation denoted in this blue bar. And you can see that even with the original equation, we can get an increase in trend in delta 13. But the trend is much smaller than that inferred from the observation denoted in these gray bars. And if we add the effect from the photorespiration, the trend is increasing, but only slightly. Only if we also added the effect from the mesophil conductance, we could get a trend of delta 13 that is consistent or comparable to that inferred from the observation. So this validates our implementation of the new delta 13 equation. And what about the variabilities among different biomes? So you can see, although globally the contribution from the mesophil conductance could only be about 30%. But particularly in those natural ecosystems, you can see if using the original CM5 equation, we cannot obtain an increase in the delta 13. But only with our updated equation, we could got a kind of large or significant increase in the delta 13 that is reasonable. So next is about the effect from the C4 expansion. We analyze it by comparing the simulation with a constant land cover or with a transient land cover. We found if we consider a transient land cover, our simulated delta 30 trend will be decreased because there is a fast carbon-4 expansion, particularly in the 20th century. And the effect from this carbon-4 expansion can be comparable to that from the mesophyll conductance. So the carbon-4 expansion or the land cover changes, the effect could not be ignored. Finally, we also examined the effect from different consideration of the mesophyll conductance. Current models use an implicit consideration of mesophyll conductance, and we explicitly added this mesophyll conductance term in the model. And we found that with our explicit mesophyll conductance, the WE would be more sensitive not only to the CO2 increasement, but also to the variabilities in the VPD and temperature. So this means current models, it's very highly likely to underestimate the response of WE to environmental changes. So if we want to have a more accurate understanding of this part, we may need to have a more accurate understanding and implementation of the mesophyll conductance. So that's all of my presentation. Thanks for listening, and thanks all of my collaborators.
We have time for questions. I have a question for you, or maybe for the broader CLM group. Is there plans to include this mesophyll conductance representation going forward? Or is this the first time we're talking about it, maybe?
I think the default CM5, they consider the mesophyll conductance, but just via the tuning of the parameter of like Vcmax or Gmax to make it more consistent of the observation, but it do not explicitly add this term.
Sam says you should submit a pull request to add it to the code base. I was also wondering if you know how it changes the computational time for calculating photosynthesis and stomatal conductance.
You mean the time consuming?
In terms of computation time, is it similar? Is it more computational?
It's very similar.
Oh yeah.
Hi, thank you for your talk. That's really interesting. I have a quick question just regarding the background isotopic signature. Since anthropogenic carbon is isotopically lighter, if that would have any impact, that background signal, on your cap delta 13 calculations.
Which signal do you denote? You mean the atmospheric C13?
Fossil fuel consumption, that isotopic signature into the atmosphere is isotopically lighter. I just didn't know if that would transmit at the level that you're measuring or not.
Okay, so in our model, we just use the time series of the C13 in the atmosphere. So that data is observation based, provided by just used by CM5. So I think that already considered the part related to the fossil fuel emission.
Yeah, I think it would be in the observations, but from an emissions-driven perspective, it would be interesting to think about separating those two things out from one another, because I imagine it does matter.
Yes, I think in Dr. Rolf Killen's paper, he already considered that when he used that atmospheric records to infer the delta 13 magnitude. But because we only simulate the delta 13 discrimination, which is related to the photosynthesis part, I would say the fossil fuel emission, I don't think it will affect my simulation.
Great. Thank you. I think it's time we move on to our next speaker, who is also online. So you can go ahead and unshare your screen. And next up, we have Jun Yu. Your slides, but not yet in presentation mode. I mean, we don't yet hear you. I don't know if you're speaking. Trouble unmuting. Okay, you should have the ability to unmute. So okay, I'm wondering if we might want to switch the order of these next two talks. Would that be okay? You all right with that? So we could pull up our last set of slides, and Jen, you maybe can work on seeing if you can sort out the technical issues. Yes, and our next speaker will be Mia El-Kazan.
Okay.
Go ahead, Mia. We don't quite have
yeah.
your slides yet. Okay. There we go.
I'm shorter, sorry. Okay, my name is Mia El-Kazan. I'm a graduate student at Oregon State University. I work with my advisor, Andrea Schmittner, and Brian Haley, and today I'll be talking about a new approach to modeling neodymium. I'm testing the bottom-up hypothesis. This is kind of just an abbreviated title from what's on the thing. Okay. So I'm going to go over a little bit of background, just because in my experience, not a lot of people know that much about neodymium, so I want to provide some context, a little history of modeling neodymium in general, kind of set the stage of what I'm doing differently, our new approach and its setup, and then go over some results, and then if I have some time, I can show some exciting isotope results that are a little preliminary. Okay. So neodymium is a rare earth element. It's a decay of samarium, and its isotopes are used as an ocean circulation tracer. So a watered down explanation of some of the geochemistry, so sorry geochemists, you can think about the isotopic composition of neodymium as if it's very negative or unradiogenic as being like older rock material, and if it's positive or radiogenic, it would be younger material. So you can see, I'm gonna try to do the laser, okay, where we have this radiogenic material in the North Pacific and this unradiogenic material in the North Atlantic can be used to trace ocean circulation when you look at that thermohaline circulation overlaid on top of it. And why we might want to use isotopic composition of neodymium or epsilon neodymium as a tracer is there's negligible biological fractionation, a limited air-sea exchange, and it's quasi-conservative. So kind of how I alluded earlier, the figure on the right shows the isotopic composition of neodymium in different ocean basins, and then on the left we have the actual concentrations of elemental neodymium, which will be the main focus of my talk today. But basically you see that the isotopic compositions are well conserved in the water column, where the concentrations have a linearly increasing profile with depth. This is often referred to in the context of what's called the neodymium paradox, and just the short version of a long story can make it kind of difficult to model neodymium. So now I'm going to set the stage of the history of modeling neodymium a little bit to provide some context of what people have been doing and what I'll be doing differently. Originally, the modeling approaches for neodymium were based on work that was done with thorium. So Bacon and Anderson in the 80s looked at thorium and saw that it also had a linearly increasing concentration with depth. So they tested a couple of different model setups, both irreversible and reversible scavenging. Irreversible scavenging is you have dissolved thorium in the water column, it attaches onto particles and it stays attached to those particles. Reversible implies an exchange, which means that those particles would be attaching and detaching. And so the idea here was that they got a linearly increasing concentration of thorium with depth because of reversible scavenging, which allowed dissolved particles or dissolved thorium to detach from particles at depth. So their conclusions were essentially that the only way for you to achieve that increasing concentration with depth was to have a reversible scavenging model. And then I have a list of some of their assumptions. The two I really want to highlight is that when it came to thorium, there was constant production of thorium in the water column, and it also included high ratios of particulate and dissolved phase thorium, which are a little different to how neodymium works. So the approach that people took is they kind of took this work that Bacon and Anderson did with thorium and they applied it to neodymium, starting with a top-down approach. So the primary sources of neodymium in models was with river and dust fluxes and then reversible scavenging. And in this sense, reversible scavenging is achieved using an equilibrium scavenging coefficient. So there's an assumed ratio of particulate and dissolved phase neodymium in the ocean. When people did this, however, they found that there was a lot of missing neodymium in the ocean compared to observations, like on the order of around 90%. So they were definitely missing some source of neodymium. So then that introduced the idea of bringing in boundary exchange. So they're saying like, oh, well, there's probably exchange with the continental margin and having neodymium input there. And everything else was essentially the same, still sticking with this top-down approach with just additional source inputs. And while this improved things, it wasn't quite adding up with observations still. And then over the course of recent years, they found that through observations, there's actually high concentrations of neodymium in pore water at the seafloor, implying a benthic flux of neodymium as a source. So a few models have decided to incorporate that as well, but still including primary sources of river and dust fluxes. So this is still their top-down approach. So getting into this new approach, testing the bottom-up hypothesis, I'm focusing on thinking about that benthic source and thinking about it as our primary source of neodymium to the ocean. So we went back to basics and we kind of started with Bacon and Anderson's original work and wanted to keep things really as simple as possible and see how far that would take us. So in this approach, we're actually looking at an irreversible scavenging model and basically looking at just dissolved neodymium alone for now. Our model includes, didn't mean to do that. Diffusion, so vertical diffusivity, irreversible scavenging. You can think of this as a constant sink source, or constant sink term, sorry, and our benthic flux, which is our source. And in our initial setup, we kind of have what I like to think of as like a fish tank model or a bathtub model. This was just like a simple one-dimensional model setup to kind of test this equation out for us, where you have a benthic flux at the very, very bottom box. And when we do that, we get higher concentrations at depth, but you can see that they're obviously not linear. So we kind of wanted to move forward with this idea. Obviously, in the real world, the ocean doesn't have seafloor just at like the very, very bottom. There's a distribution of bathymetry. There's been a lot of talks this week that discuss the importance of bathymetry. So we decided to distribute that benthic flux based on like the relative bathymetry in the ocean. So this is kind of what that looks like when you distribute it. So you can think about us plugging basically this in to that benthic flux term. And when we do that, we get this orange line here, which makes it look a lot more linear. So we're getting that kind of increase in concentration with depth and also linearize our distribution. So in the dashed lines, those are our observations, and then there's one standard deviation. And even though we're not within that one standard deviation with our simple one-dimensional model, we're on the same order of magnitude. And at this point, we felt pretty satisfied moving forward and implementing this into a three-dimensional biogeochemically enabled model. So we plugged this into OSU's UVic Earth System Climate Model, and we tested a variety of benthic fluxes and absorption coefficients. For the sake of time, I just wanted to highlight one of them, and also here you're looking at longitudinally and latitudinally average vertical profiles for the global ocean, Atlantic, Southern, and Pacific Ocean. This dashed thicker line here is our Model 20, and the black line is our observations. And we moved forward with this thick dashed line, our benthic flux of 20 model as our best fit model. I can get into more details of how we established it was the best fit if there are questions. But we kind of move forward with this to further look at our results. So this is our longitudinally averaged results. You can see with our simple benthic flux model that only has 2 parameters, we're able to capture a lot of the features that we see in our observations. So the top rows are observations, the bottom row is our model. We capture the gradient of higher concentrations to lower concentrations in the surface waters pretty well. Our root mean squared error is comparable with other models that have a similar resolution. So especially I want to highlight the Pacific Ocean, which has historically been difficult for models to resolve. We have those higher concentrations in our model as well, but we do underestimate them in the deep ocean for the Pacific and overestimate them in the surface waters, and we have a slight challenge in the Atlantic that's the opposite, where we overestimate in the deep and underestimate at the surface. Part of this is just a byproduct of using a constant benthic flux everywhere. This is another way that you can visualize that, looking at different, swaths of the ocean. And just as an example, we see that underestimation in the Atlantic happening in surface waters where we would anticipate having dust fluxes. So this is mostly just a byproduct of considering that the primary source is at the very bottom. But overall, our model is doing a very good job for being so simple. And this is just something to highlight future work. We already started implementing this structure for our isotopes, which is pretty exciting. Our global average is really good. Surprisingly, we don't quite estimate the difference between the Pacific and Atlantic oceans as well as the observations do, but that's something we're working on. So yeah, I'll leave this up for some key points while we do questions, but basically the historical context was you can't get a linearly increasing concentration with depth without reversible scavenging, but when you use a bottom-up approach, you can, and that bathymetry, diffusion, and lateral transport have a big impact on that distribution. So yeah, thank you.
Great, we have time for questions. I was wondering, you mentioned that it looked like some of the discrepancies were in places where there would be large dust fluxes coming from the surface. Have you thought of putting that factor together with your bottom-up approach?
Yeah, we definitely want to consider including top sources as well. I think the idea was, let's see how far the primary source of a benthic flux can take us, and then there's room to tweak it later. And the hope is also to use some of this in a paleo context too, where we might not have great parameterization on those surface inputs as well.
I'm super excited to see this. And you probably mentioned this and I missed it, but for your bottom ocean lithology, are you representing different regions like the mid-ocean ridge versus Central Pacific and the different signals that would arise from those from your bottom-up approach?
So when it comes to elemental neodymium, the flux will be the same everywhere. But when we're implementing our isotopes, we do take into consideration the distribution, because when it comes to our isotopes, we do care about like that distribution in the different ocean basins differing from one another. But the bathymetry would reflect those features, but the actual value of the flux for elemental neodymium would be the same throughout. Does that answer your question? Okay.
Great. Thank you, Mia. We'll move on to our next presentation. I see Jungyoon is now on the video for Zoom. Great.
Yeah, can you hear me?
And we can hear you. Excellent.
Oh, great. Let me share my
So
screen.
we see your slides, but they're not yet in presentation mode. There we go. You are on the screen in presentation mode, so go ahead when you're ready.
So hi everyone, my name is Jun Yu. I'm a PhD student working with Professor Keith Moore in UCI. So today I'm going to introduce a new ecosystem model that we're developing on CSM2 marble, which includes 8 types of phytoplankton and 4 types of zooplankton. So we believe this is a next generation marine biogeochemistry model with the potential to simulate how ecosystems are affected by and feedback onto the climate change. So it can give us a better understanding of future changes in marine biogeochemical cycles. This is the latest published version of the ecosystem model on CSM2, which includes 4 types of phytoplankton and 1 type of zooplankton, which is the 4P1Z model. And based on this 4P1Z model, we expanded to 8 types of phytoplankton and 4 types of zooplankton, and we call it AP4Z model. So for the phytoplankton, this model includes picosize, nanosize, and microsize. So for picosize, we have Prococcus, Synechococcus, picokaryos, and small diazotroph. And for nanosize phytoplankton, we have Cacalysophorus, Phascisis, and the other generic nanophytoplankton. And for the microsize, we have the diatoms as the classic representative. And besides phytoplankton, we have 4 different types of zooplankton. So we have 2 types of microzooplankton, which are the main grazers for the picosize and nanosize phytoplankton. And we also have mesozooplankton and macrozooplankton, which are the main grazers on the nanosize and the diatoms, and also the large microzooplankton. So these larger zooplankton, they produce larger size, fast sinking fecal pellets, so they are critical for regulating the efficiency of the biological pump. And also you can see that macrozooplankton such as krill, they are the main food source for the higher trophic levels. So this model has the potential to provide insight for the future changes in fishery yields. And this slide shows the feeding strategy used in this AP4Z model. So the feeding strategy follows a modified hauling type 2 relationship. And we initially set up a decreasing maximum specific grazing rate with predator size. So this will in line with the observations. And we also introduced this DI as a dynamic density coefficient to represent the zooplankton adaptation in prey switching feeding strategy. For example, large zooplankton will exploit alternative phytoplankton and zooplankton prey by feeding on more abundant prey type. So by creating a refuge for the less abundant prey species, and also maintaining the diversity by the killing the winner effect. So this DI will contribute to stabilizing the model dynamics. And so here are some preliminary results. So first we are looking at is the model data comparison of the surface nutrient distribution. So as we can see, the model captured the general spatial patterns and also the magnitude of the surface nitrate, phosphorus, and silicate. And they're all showing a lower concentration in the subtropical gyres and also higher concentration in the subarctic regions and in the Southern Ocean. And the figure on the right shows the model performance of simulating iron at the surface ocean. So we can see that our model also did a good job with very low iron concentration in most of the ocean regions and higher iron concentration in the very dusty regions. Besides nutrients, it's very clear that this model can also reproduce the observed phytoplankton biomass, both for the pico-sized phytoplankton and also nano-sized and the diatom. So it shows that the Prochycoccus is the dominant group in the subtropical gyres, and also the nano-sized phytoplankton and also the diatom are co-dominating in the higher latitude. So we did notice that there are some mismatch between the model larger size phytoplankton and the MURDA dataset, and we like to point out that MURDA dataset has some uncertainties related to cell count and identified species and conversion of cell abundance to biomass. So the carbon conversion estimates from the MURDA dataset may be subject to some large errors. We here introduce some other constraints for model performance evaluation. Since we only have one generic type of diatom as the ocean acidifiers, so we can have a sense whether the simulated diatom and the biogenic acidic export are reasonable by comparing the simulated and observed silic acid concentrations. Like figure showing here. And also, similarly, the alkalinity concentration distribution can inform about the quality of the calculus for simulation by comparing, and also the magnitude and calcium carbonate export. So figure showing here shows the general agreement between the modeled alkalinity and observed alkalinity. Finally, we can also validate the performance of the diazotroph concentration by comparing the N-fixation. So this figure showing that the model total N-fixation is in line with the previous estimation from the inverse model study. So also give us confidence in the model performance of simulating the diazotroph dynamics. And so move up along the food chain. Here we are looking at the model performance of zooplankton biomass. So we can see model can both generally reproduce the annual mean biomass of the micro-sized zooplankton and meso-sized zooplankton and the macro-sized zooplankton compared with the observations. And but also we can the model can also reasonably simulate the seasonal dynamics of the mesozooplankton dynamics. So this figure indicates the model ability to capture the ecological dynamics besides the biogeochemical dynamics. And here we further evaluate the energy flow in the model to see whether the grazing relationship we initially assigned is reasonable. So as you can see, our model estimates that the microzooplankton in total consume about like 46% of total NPP with highest consumption, like which is about I think it's 90 to 70% in the subtropical gyre, and relatively lower in the subpolar regions. And this estimation is kind of close with the previous in situ dilution experiment, which showing like also highest in the tropical and subtropical and relatively lower in the polar and temperate oceans. And our model estimate that the mesozooplankton in total consume about like 20% of the NPP, which is slightly higher with the previous in situ study. And for the rest, the macrozooplankton consume in total like only about 5% of NPP, and in total, all the zooplankton consume about like 81% of the total NPP. And here we are looking at the model, the biogeochemical fluxes. So we can see the model can capture the spatial pattern and also the magnitude of global NPP compared with the satellite estimations, and also showing the picophytoplankton is the dominant source of ocean NPP, which is over the half of the ocean NPP. And the nano-sized phytoplankton and diatoms kind of split the rest and co-dominate in the higher latitude. And this figure shows the biogeochemical fluxes. So we can see that the model POC flux, calcium carbonate flux, XO ratio, and silica flux are all reasonable in terms of spatial pattern and also the magnitude compared with previous studies. Besides, we also compare the modeled sinking N2P at 150 meters. You can see that our modeled sinking N2P shows high consistency with previous estimation from inverse model, both in terms of the spatial pattern and also the magnitude. Finally, we want to ask, so what is the difference, right? So when we moving from a more simple ecosystem model to a more sophisticated ecosystem model, are there any improvements? So we defined one significant improvement, which is in terms of the seasonal variations. So as we can see from this figure, so the simple ecosystem model, which the 4P1Z here, although they can capture, it is good enough to capture the annual mean of the chlorophyll concentrations. But if we look at the seasonal variation, which is indicated by the standard deviation of the season, you can see there are large errors in the higher latitude compared with the AP4Z model. It's more. We see that there's a overestimated biomass in the high latitude, and we further split it into two boxes. One is in the northern boxes, one is in the southern, and then we evaluate the seasonal variation in these two boxes. So the black line is the satellite chlorophyll, and the red line is the AP4Z chlorophyll, and the green line is the 4P1Z chlorophyll. So we can see that the 4P1Z have overestimated spring bloom, both in the northern boxes and also in the southern box. So it's even more clear to see it in the global map. So we can see the AP4Z model have a dampened spring bloom compared with the compared with the 4P1Z. So these results indicate that the more complicated ecosystem model can better reproduce the seasonal variation in the ecosystem dynamics. Why is that? And we think it is because we improved the phytoplankton community composition. So we can see this figure is showing the satellite-derived percentages of the carbon biomass from the pico-sized phytoplankton and nano-sized phytoplankton and the micro-sized phytoplankton. In the middle is our AP4Z model estimation, and on the right is the 4P1Z model estimation. So we can see that the 4P1Z have the overly blooming diatom concentration compared with the satellite and also our AP4Z. So this indicates that the spring bloom is caused the bias in the spring bloom in the 4P1Z is caused by the overly blooming diatom. And because our model in the 4P1Z model of AP4Z model has more phytoplankton species to compete with the resource with diatom, and also because we have two larger zooplankton which are designed to target on grazing on diatom. So we have both bottom-up top-down control to dampen the diatom bloom in spring. So that's why in the more complicated ecosystem model, the seasonal variation is improved due to the improved phytoplankton community composition. So this is what I have for today. So for some key takeaways, we have three key points here. So first, we develop a next generation marine biogeochemical model with an expanded ecosystem in CESM2 marble, and it has the ability to model the key species which are observed and continually observed in the ocean. And also our model generally reproduced observed phytoplankton community composition and stoichiometry, which help to reasonably estimate the integrated biogeochemical fluxes. And finally, our model improves the spring bloom compared with a simplified ecosystem model, which is benefiting from a better representation of a bottom-up control and top-down controls. Thank you.
Great, thank you. Should we move on and open a few minutes of discussion with all of our speakers? So we can take questions for Jenyu there as well. Can we go ahead and get the videos of the online speakers up? And so we'll have a few minutes of discussion of all of the session today, or particularly the second part. Does anybody want to start us off with a question?
I guess this is maybe a little bit contentious, but what is the plans for CSM3 in terms of, in terms of CMIP for having the fully coupled emission-driven runs going? Are there major sort of stopping points to that, or do you think we'll be able to transition in the next 8 to 12 months?
Is this a question for Dave or a question for me? So the question is, what are the plans for CESM3 emissions-driven over sort of before the release of CESM3, I guess?
Yeah, no, we're planning to do emissions-driven, and there's a few technical things we are working on, Keith largely. And as I sort of said in my overview presentation, as long as the carbon cycles are not so out of whack that we're getting something really weird, and hopefully we'll be able to figure that out. We have tuning capabilities now better than we had before, so I'm kind of confident we can do that. So yeah, I think it's going to be, we want to be part of that conversation. There's going to be discussion about releases and CMIP versions and stuff. I think some of those details still have to be worked out. So what we're going to support in a release versus what we're going to do for CMIP may not line up 100% in the first instance, but those are things we're going to work out over the next few months.
I'll just add, I'm glad to hear that that's still the plan, and I hope that we can make it happen, because I think being getting a number of the modeling centers to do this is definitely a goal of mine. I think we'll learn a lot from it, and I think, Greta, I was wondering if you might want to comment on, what we need out of the fully coupled carbon cycle or system models in order to be able to make these simple model projections of the future.
Yeah, I feel like it's, I think the things that I look forward to seeing are like different flux outputs so that we're able to connect to other processes across the Earth system, I guess. And I think especially this work that we're seeing with the simple models is showing that having multiple realizations of different processes in the Earth system that are realistic or that correspond to our observations is going to be really vital, because then we can see different versions of our internal variability that we're then able to reproduce with simple models. So that's what we've shown is that this can happen in the ocean really elegantly, but then also for land carbon, I think we're going to see similar trade-offs with climate feedbacks and carbon feedbacks. So I think that's why having at least a few different versions of the carbon cycle would be useful.
I want to add, there's a lot to analyze as well, just in the emissions-driven runs. So in Greta's work, we noticed that all of the simple climate models, there's no connection between heat and carbon, and partly because of how they're structured, they're not able to connect those things, but we're getting a very different answer when those processes are connected. So I think we need to learn a lot from the Earth system models about what are the necessary connections between things like heat and carbon that we do need the simple climate models to have a structure that's capable of representing, sort of as a minimum, to use those models going forward. Because if that connection is missing, we're getting the wrong distribution of behavior out of that simple model. I think we saw that in some of Ben Sanderson's plots earlier as well, that the simple models are sort of falling outside of the distribution of behavior of the Earth system models. And the more of the emissions-driven models and the more different parameter combinations or climate sensitivities within those emissions-driven runs will give us more sampling of that space that we can use to evaluate the simple models.
this is I don't know if this is getting into the weeds about the simple models. This is a question for Greta. In talking about the feedbacks that are or are not present in those simple models, you were talking about circulation representations that were not there. Does the volume of the mixed layer shrink in the simple models to represent a more stratified ocean? Because that's an important physical effect that comes to mind to me, and it wasn't clear from your presentation if that effect is being included.
Yeah, I guess the heat capacity of the mixed layer is a parameter that can be tuned, and it's not. I didn't see that or like jump out as a response, but maybe I could look closer and see. But the strongest response was the climate feedback parameter, and I guess it's like a function of like the ranges that we give these parameters, you know, when we set up the PPE. But and the climate feedback parameter just has like this really wide range that it's allowed to move within, whereas the mixed layer depth might not have as large of a range. That's a good question.
We also do have in the model that Greta implemented, there is a change in circulation for a change in buoyancy term, and that was in the parameters, but wasn't as important as just the circulation rate. But, you know, each of these oceans could be structured differently. But I think it's figuring out what are the essential features that from our system models that we think need to be able to be captured in the simple models. Other questions?
This is kind of a question for June, but I'm always floored by the elegance of and complexity of ocean biogeochemistry. It's so cool. I'm curious, is this 8P4Z scheme slated for CESM 3, or is it still kind of in the works?
I mean, thank you for your interest. But the question for Keith.
There's a PR from the Irvine group that includes a number of updates to Marble, including the 8P4Z set configuration. We haven't evaluated it yet in MOM, and so I think I don't know the answer to that at this point. I think a priori one concern would be the computational cost, but since we don't have it in MOM yet, it's hard to do that, hard to make a definitive statement, but there's a concern about cost.
But it sounds like it's making its way into, finding its way into the main branch, so that could be evaluated later.
In available configuration.
Yeah, or a separate configuration that could be run for some things. Great, yeah, so maybe it would be an option, if not the main choice for the default. Any other questions? Okay, well, I want to thank all of our speakers again from both the second half of the session as well as the first half of the session. Thanks for participating in the BGC working group. I was wondering in the back, could we put this last slide up from my presentation really quickly, just in case anybody else wants to join the mailing list? It's got the QR code on it. So thank you all. Thanks for participating.
welcome. This is interesting. You can only see short people half in this setup, if any. All right, well, welcome. It's too high, but whatever. Welcome everybody to our Chemistry Climate Working Group session. I'm Simone Tilmes. I'm the Chemistry Climate Co-Chair, and I also acknowledge Rafa, who is probably online, our other co-chair. Then we have Rebecca Buchholz, our science liaison, and Sean Honomigel, who's also online, who is really helping a lot as a liaison for technical questions and other things. And Francis Witt is our software engineer. Yeah. So I don't know. How do we continue here? Oh, this one. Okay, so Chemistry Climate Working Group, we're working on various chemistry realizations in the model, and this plot I showed at the last Winter Working Group meeting. So here on the right, you just see the different model tops that are available with CESM. The high top model is the WECM model. The 80 kilometer is now our workhorse model, and this is basically the ChemChem model. And then also we have that low top option. And for WECM, we have different chemistry realizations. We have that was also, and it's not updated from CMIP 6, is the troposphere, stratosphere, mesosphere, lower thermosphere chemistry, which covers stratosphere. I mean, it's really the full representation of the whole atmosphere chemistry, quite comprehensive. We have the middle atmosphere chemistry for WECM, that's mostly focusing on the stratospheric part, and then also specified chemistry option for the pointers, if you're mostly interested in dynamics. But for chemistry, and so for our workhorse model, we have different things we're working with, and we divided it into the air quality chemistry, which is really our TropStrat chemistry that we have been using for a long time, the TS1 mechanism. But then we have several others, and there is a TS2, there's a TS3, with alkyne oxidation is represented more in this one. So it's really more for improved and enhanced simulation for air quality. We have the short-lived halogen chemistry, and Rafa will talk about this later in this set of presentation. And that's really the most comprehensive representation also of greenhouse gases. So, but the more, of course, you see that this is increasing in traces and getting more expensive. So for our purposes, like for CMIP 7, we wanted a more simpler model, and that's we call the chemistry climate model, and Luisa Amens has worked on it a lot to really reduce the tropospheric chemistry a bit. And I have a plot in the next slide, a plot that shows this in more detail. And then we, of course, also have the greenhouse gas chemistry that is basically the chem model that people use. Next is, this is a plot that Luisa provided, and it really shows the components of Mozart, so the tropospheric mechanism. And with time, with the years and the computers getting bigger, we increase the chemical mechanism, and this is now the TS, or the T1 for the troposphere. So you see that has a lot of more complex chemical species. But again, for the chemistry climate, for long-term climate simulations, we may not need all that. And so Luisa put an effort into get a new mechanism that I pointed out before that's fairly similar to this Mozart 2 mechanism. And we'll see in a few slides how this performs now in the context of our model development. So we also dealing with aerosols in our working group. So this is a working group for chemistry and aerosols. And the standard model what we are looking at is the MEM4 version. But now for the new model development, we are using actually a MEM5 option when we have stratospheric chemistry included. And that just includes a new course mode for stratospheric sulfate, which is more comprehensively representing volcanoes. We're also working on Karma, a sectional aerosol model that is in the development version right now, and we're trying to merge that eventually into the main code. This will be not available yet for upcoming releases, but it is an ongoing effort to improve our aerosols in the model and an interface that we have exchangeable aerosol models that can be used in different configurations. And so the other thing we are working on is a new updates to the ADF, to the atmospheric diagnostics framework that has been developed mostly for chem now. So we're really working on getting the chemistry into this framework, which is really important because we do need to evaluate our model. We need to develop diagnostics. And in the past, we had an atmospheric diagnostics evaluation tool that was based on NCL that we simply cannot use anymore. So especially Sean Honemekel and Justin Riechling have worked a lot, and Rebecca, on working towards many more plots that will be soon standard in our ADF scheme. And so for now, we already included ozone climatologies, comparison of chemistry and aerosols like zonal mean and other comparisons shown here on the right. And also we're working on comparison to aerosol optical depth with observation, CO, MOPID observation, and so on. So people will have a much easier time soon again to benchmark their models and evaluate them. So now coming quickly to some simulations that I did with the recent model code to see where are we right now in the model development. We want to make sure that the chemistry is actually working as we expect. And so we have run some short simulation at this point. This is only 5 years. But once the model is more complete, we will run longer term simulations. And just running the TS1 and the current new CSM development framework, our performance right now is 25K per year, but this is only a throughput of 2 years. If we run the new chemistry climate setup, we have 19K per year, which is 4 years a day. So that's much more feasible model simulation now to be used. It will be still, of course, set up and improved so that we have even a better throughput probably. But how does it look like? So we ran it through the ADF diagnostic set for comparison. And this is comparison with the ozone zones. 2 just examples, 2 regions that we're comparing to. This is the Northern Hemisphere Polar West region at different altitudes, as you can see, 50 hectopascal all the way to the surface. And what we can see is that both the climate chemistry and TS1 version perform as we hoped to be expected. It is interesting that there is even seemingly a little improvement in the chemistry climate, but I did not have time to understand why, especially in the stratosphere. So that's something, it may be also due to this short time frame. So we'll have to look into that more. The other thing is like West Europe, I mean, we have a very excellent comparison. So I think we are quite happy with the current performance. And of course, we are always strongly dependent on what the chem model provides in terms of dynamics and other things. We did look at here MOPID CO comparison. This is only the chemistry climate comparison right now. We still see that this is a difference between the model and the MOPID data. It actually shows seasonal differences here in this plot. This is going to be like produced by the ADF at the moment, and we still see this underestimation in CO. That was always there, so no surprises here. Still have to look into that. In terms of now looking at how well, or how do we compare when we compare the chemistry climate model to the chem model in terms of aerosol forcing. And what I didn't say before, what people probably know, so we need to run the chemistry in order to provide oxidants to run the prescribed chemistry in chem. So it's important that we basically get about a similar forcing, because if we run the chemistry climate model for tuning purposes and then use the oxidant in chem, we want to not have to retune too much, right? So, however, when we look at the rest of them, there's still a little bit of an offset there. This is the TS1 version, this is the chemistry climate, and this is the chem model with prescribed oxidants. And I mean, looking at things like secondary organic aerosols, which is something that is a bit different in those model versions, we do not see a large difference. We actually see a little bit of a reduction in the chemistry climate model compared to the more comprehensive chemistry version. But the main difference is probably still in the sulfate burden. And this is what we had discovered for a long time already, that if you run with prescribed oxidants, with monthly oxidants, you just can't get the formation of sulfate the same way as when you do it when you have a fully interactive model. So there's still some work to be done to think about OH imposing a diurnal cycle and things like that, which we still haven't done yet. But there will be some differences. But besides that, I think we are pretty close, at least closer than we were with the forcing, with our updates. I did look a little bit at the visible AOD in comparison to MODIS with the two simulations. And so here on the left, you see the MODIS AOD. This is an average, however, again, it's a little bit different time frame. But we can see this distribution. Then we have MERA from the same time frame. And, you know, models will have a hard time to get exactly the same values. But usually we tune for a number of about 0.13, which seems to be, and this is also just an example of July, so in the global average. Looking at our models, though, when we look at chem as well as the climate chemistry version, we do see some differences. And one big difference is certainly effects of the dust. And so this model version still doesn't have a new dust scheme, emission scheme in that Danny had developed. And so we are waiting for that before we can actually, we're hoping that we get some improvements that way. The other thing that we notice is that there is more the increase in the regions probably with enhanced sea salt. So that's something that we should pay attention to. Because one thing is if you have a stronger AOD in the, back here. Yeah, if you have more AOD, a higher AOD in the southern hemisphere than the northern hemisphere, that can cause differences in the rainfall and shifts in climate things as well. So I think that's one diagnostic we should start looking at is also the south-north gradient of the AOD for future evaluation, especially in terms of climate. And then this was a timeline. We have an ambitious timeline for the CMIP7 or for CSM3. And one thing we are very close to is to implement the new dust emission scheme. It's probably already implemented. I don't know if it's in the final version, not yet, very close. We want soil NOx emissions. That would be a very great interaction with the land, especially for chemistry, as well as a new TOV photolysis scheme that Doug is working on. And we're hoping that we may be a little bit late to the deadline of the code freeze, but we hope that this will be definitely available in some versions of CSM3. Sorry, too fast. And then other things, gravity wave tuning is very important for us as well, since we want to get the chemistry in the stratosphere reasonable well. I had looked at it, so ozone looks reasonable well, but we hadn't had a long-term simulation yet to evaluate it. This is all coming in the next half year, hopefully, where we have then a more improved atmospheric model to then base our chemistry on it. And so just as a last point here, we do work, you know, for people that work on the Red Show, it's just an announcement that we are moving some input data around. So if you're a user that runs on the Red Show and has certain things, points their ComSat to certain emissions or metadata or other things, we have been changing already some locations of those, and there will be more changes coming, more permanent changes to the location of some input data. So if you have any questions, please ask Rebecca. Or Rebecca, maybe you want to say something more, but it's just a heads up for people that changes in location for input data will come and will be happening by the end of the summer. With that, I want to stop, and if there are any questions, please go ahead. If not, we can start our session. And this was just an overview talk, and I'm glad that many of you made it here, by the way, as well as online. So we start with our first scientific talk by Louisa Emmons, which you introduce your title yourself.
Okay, thanks. Yeah, I'm going to talk about a grid that I created as part of a regionally refined grid that has refinement over 3 continents. I only put my name here because I couldn't possibly remember everybody I should thank who've contributed to this, but I'll try to mention them as I go along. So the motivation for creating this grid is that there's now a geostationary satellite, or the start to a constellation of geostationary satellites. So the GEMS satellite over Asia has been up for a couple of years now and gets hourly observations of NO2 and formaldehyde and ozone over Asia. And TEMPO was launched just last year and goes covers all of North America. There's just a zoom in picture of Northeast US from their first data. And the satellite will be launched over Europe, I think, next year. So these diurnal variations observations are going to be really valuable for improving our predictions of air quality. So as part of an accelerated science discovery proposal grant allocation that I got just as derecho became available, I designed this grid. And so we finally started doing some runs when derecho was turned on last summer. And it's been a slow process to get this running, but many thanks to Jim Edwards and Adam Harrington for helping with that. So I've made a grid that has 12-kilometer grid over North America, Europe, and Asia. I also made a version with a quarter degree, 25-kilometer resolution that's a little bit cheaper. So this ended up being almost 500,000 grid points, and I'm running with the full chemistry, and with that configuration it costs about 2 million core hours a year. So I've been running with nudged meteorology from Meritu, but you can also run with free-running climate. So here's just some examples of the differences between a standard 1-kilometer grid and a 1-degree grid and the refined grids. For, on the left, zoomed into Northeast US, so you can clearly see we're resolving a lot more cities in the finer grid. And similarly for Europe, 1 degree on the top and 1/8 degree on the bottom, and for Asia. So clearly we can now resolve cities, we can resolve ship tracks, you can almost see roads in Asia with this grid. So here are just some examples of some simulation results. So those were NO emissions to highlight the differences in the grid. So we have over East Asia, the simulated NOx at the 1 degree on the left and the 1/8 degree on the right. And we can clearly resolve cities in China as well as in Korea. And this results in rather different ozone, at least close to these urban regions. So you can see the depleted ozone over cities in Asia, as well in China, as well as over Seoul and the southeast coast of Korea. So this is a monthly mean for May 2016 with the time period of the Chorus AQ campaign, which I'll be looking at later. I haven't fully analyzed all these results. So similarly for the Northeast US, so it's kind of surprising how little shows up in the 1 degree that you can now see, like Boston doesn't even show up in this scale, or Chicago or Detroit. So the finer grid will definitely be valuable for air quality, and similarly for Europe, where we can't even really see London in the 1 degree, but it clearly shows up in the 1/8 degree and other cities as well. So in the middle of trying to analyze all these results, I got involved with the Asia AQ experiment, which was in February, March this year. And this 3-region grid, at least the fine region over Asia, is really valuable for helping with this campaign. So it's a NASA-led campaign. It included 2 NASA planes as well as several airplanes in Korea that helped out in the Korea part. And it started out with 2 2 weeks in Manila, overflights of Taiwan, 4 weeks in Seoul, Korea, and then 2 weeks in Bangkok. And the goal of the experiment is really to look at air quality in these urban regions and help validate GEMS satellite observations, which are a GEMS map is shown in the background here. So you can see that these 4 regions are really very different. Manila and Bangkok are very far south, so there'll be, even in February, March, there's a lot of sort of solar radiation and high ozone, as opposed to the Korea segment is more wintry. And so the goal is to look at local versus transported pollution. So we decided for this campaign to do the same flights in each region, same flight track. So part of our decision-making during the campaign was just whether or not to fly. We didn't have to figure out where we were going to fly. So the flights included in-situ measurements along a track like these white lines, and then a remote sensing instrument measured NO2 columns over the urban regions. So this is over Manila, along the coast, south and west coast of Taiwan, over Seoul, and then over Bangkok. And in Bangkok, we also, the DC-8 flew farther up north, which was much closer to biogenic emissions and biomass burning. And in Seoul, we were looking at what might be coming in from the west towards Seoul, as well as the outflow from Seoul, which often was off to the southeast. So we produced chemical forecasts during this campaign using this grid, and we've been running forecasts for a long time that just run daily. We calculate fire emissions with the FIN model. We now have versions 1 and 2.5 running to produce daily fire emissions. We run WACM every day with a 10-day global forecast. We should say we. Sean Hanemichael runs WACM with both the FIN fire emissions and the QFED fire emissions. And then Gabby Pfister and Rajesh Kumar run a WRF Chem simulation that uses the WACM output as lateral boundary conditions for the regional WRF Chem. And so we ran a configuration of CAM where I added CO tags, so it was just simulating aerosols, not the full chemistry, for chemical forecasts during the Asia AQ campaign with that grid. So some of the CO tags that we included were, for the Philippines section, we included a tracer of anthropogenic emissions from Philippines, so we could see the plume from Manila as well as the industrial region to the north. For this day, clearly showing a plume off to the west over the ocean. We kept track of pollution from different parts of China. This is at 1.5 kilometers, so we see pollution aloft flowing towards the Philippines, and also a tracer of biomass burning. So there were some local fires in the northern part of the Philippines. So NO2 was measured. These are maps of NO2 from GEMS, averaged over a whole day, for 3 of the days that we flew the DC-8. And there are clearly differences in these NO2 concentrations. So there weren't very many flights, but we clearly saw some different conditions during these flights. And so for those same 3 days, these are the Musica simulations. The top row is CO, and the bottom row is ozone. So the DC-8, the NASA airplane flights were just within this region between these arrows here. So on the 6th, February 6th, we clearly saw a plume of ozone from Manila out over the ocean. It's a little bit less on the 7th. And then on the 11th, there was clearly much more pollution being transported from the north and impacting the background conditions. So there's a lot more to do to really analyze these results. And the observations are still being analyzed, so I can't yet show you an evaluation with the observations, but that's what we'll be doing this summer. So similarly in Korea, there were very different conditions depending on which way the wind was blowing. For example, on February 17th, the wind was from the south, and so it was relatively clean background. But then other days, there's flow from the north that's clearly affecting the pollution levels around Seoul. So there are days that we'll be able to really quantify how much was local pollution in Seoul and what might be contributed from elsewhere. And in Thailand, there were there was far more biomass burning, which is these bottom plots shows the tracer of CO from biomass burning. So influence from the north, but also from Cambodia, wafting over Bangkok. So that'll be very interesting to analyze further. So I just want to take a couple minutes to talk about a couple other things. So I think this grid will be very applicable to this project called HTAP. For those of you who don't know, it's a part of a UN convention on long-range transboundary air pollution and really looks at the impact of pollution being transported across the northern hemisphere between continents. And they have a mandate to quantify the influence and also come up with guidance for improving air quality. But the current legislation isn't sufficient to meet these long-term goals, so they're starting a new round of HTAP simulation. So it's really a modeling study, it's a multi-model comparison, and they'll be looking at, as they have before, always looking at the impact of intra-regional and extra-regional sources to local air pollution. But they'll also be looking at future emission scenarios and the impacts of ground-level ozone on vegetation, the effects of methane on ground-level ozone, the effect of wildfires on long-range air pollution, which is in connection with also with an IGAC activity that Rebecca's helping lead called BURNED, and deposition. And they also want free-running simulations, future simulations with chemistry climate models. So I think it's really important that we contribute to this, and I'm willing to help run these simulations, but I would really love to have some people, other people get involved. So if you're at all interested in helping look at these results and contribute, maybe lead a paper on some of these, just let me know, and we'll start a group working on how we can contribute ChemChem and Musica to this activity. And finally, for those of you who don't know, we've been working on a detailed chemistry atmosphere model observations framework. It's slightly different from the ADF because it really matches the precise time and location of chemistry, atmospheric chemistry observations to the model. And Rebecca's been helping a lot with that too. We're going to have a tutorial here in October. I'll stop there. If you have any more questions, I'm happy to help answer them. Thanks.
So you showed one figure, I think it was the Philippines, or depending on where the wind's blowing, a lot of ozone was in the Philippines or not, basically coming from China. So is this, is there going to be policy-related issues over this? Or, I mean, because it seems like local pollution in the Philippines isn't going to be the issue, right?
I think in Manila, actually, there were 12 kilometers is still a little bit coarse to look at Manila. But I think within the city, there will be quite a bit that they can do, that it's not quite on this scale. Wenfu will be working on that with the 3-kilometer Musica V1. Yeah, I'm not sure they'll try to get China to not blow pollution around. It's actually very clean background. Most of the time, there's very clean air. It's only occasionally that pollution comes out from China and then gets pushed south. But.
Oh yeah, the questions online? No? I think they will let us know. Okay, then the next speaker is Wen Futang.
Hello, everyone. I'm Wen Futang. I work at Atmospheric Chemistry Observations and Modeling Laboratory here at NCAR. Today, we will talk about a very special type of fire, the wildland-urban interface fire, and its impact on air quality and health. Let's see. So before we start, the question is, what is a wildland-urban interface, or WUI for short? So WUI is a geographic area where anthropogenic urban land use and wildland vegetation come into contact. The technical definition of WUI varies depending on the regions and purposes. However, here I put a widely used WUI technical definition here in the United States. By this definition, WUI includes intermix and interface, and they have very detailed definition as listed here. So why do we care about fires in WUI? Here I listed a few reasons. First of all, in WUI, fire risk could be higher than other places due to human activities and human ignition. And second, WUI fires are closer to humans and properties, so they have the potential to cause more damages and losses. And also, fire emissions from WUI fires can be more harmful due to the possible involvement of structure burning and vehicle burning and other materials. And lastly, it has been said that WUI fires will become even more important in the future. So because of these reasons, fires in WUI is very important, and currently there's not enough understanding and knowledge on that, so it requires more research. So to understand the trend of the global WUI, we use machine learning approach to develop a multi-year global data set of WUI area fraction, and it's called a Worldwide Unified Wildland Urban Interface, WUI for short. So this figure here shows the change from 2001 to 2020, the change of WUI area fraction. As we can see, it has been increased significantly. And here is another look by different continents, and for more years from 2001 to 2020. If you look at all these continents and look at the global average, you can see that the WUI fires, WUI area fraction has been increasing in all these populated continents, and it was about 4 to 5% of the land area, global average speaking. And so this is the change of WUI. What does the WUI fire change look like? So here I'm showing the fire count on the left and the burn area on the right. They are both from MODIS. So here I'm showing the fraction of fire count within WUI and fraction of burn area within WUI on this slide. So if you look at the global average here and here, you can see that the fraction of fire count and burn area in WUI, they both increased from 2005 and 2020. And this is the case for most of these continents. Also, we found that the global total fire counts and burn area have been decreased in the same period. So now we know that WUI area and WUI fire fraction, they have been both increased in the past 20 years. We want to know the impact on air quality and health from the WUI fire. So to do that, we run a few musical simulations. Simone and Luisa have done a very good job introducing the Musica version 0 model, so I don't need to go through that. But here I'm showing the default configuration of Musica version 0, which is the Corners refinement. So outside the resolution is 1 degree. Inside the refined region, the resolution is 14 kilometer. So for this study, we look at the global scale, but meanwhile, we have a focus over the continental US. So to understand the impact of WUI fire relative to wildland fire, we run 4 Musica simulations. And they are no fire, wildland fire only, WUI fire only, and all fires. The all fires is the real world scenario and is also the control case. So we did simulations for the whole year of 2020. Here I'm showing the impact of WUI fires on air quality. So these figures shows the 2020 annual average of global CO, NO2, PM2.5, and ozone at the surface due to the WUI fires in 2020. So to calculate this, it's calculated by using the all fires scenario minus the wildland fire only scenario. And the top panel is for the global look, and the bottom panel is the same but zoomed in over continental US. So as we can see, WUI fires have a notable impact on the surface concentration of these key air pollutants. And now let's look at the health impact of WUI fires based on the Musica simulation results. So we calculated the annual total premature death, APD, attributable to PM2.5 and ozone exposure. And by we here, I mean Yao Xianhuang and Debatoche from Wayne State University. They are the health experts here. But long story short, for PM2.5, we calculate APD due to all these listed diseases, and for ozone, we calculate APD for attributable to COPD. And I will pause here for 20 minutes so you can read the slides yourself. And if you have any questions, please, regarding this part, please email them because I will not answer. Okay. And here is the results. This slide have a lot of details, and I will explain. So the top panel shows the fraction of WUI fire to all fires, and the blue is blue bars are for emissions. So it basically shows the WUI fire emission ratio to all fire emissions. And the pink bars are the same, but for APD, you can consider it as the WUI fire health impact relative to all fire health impact. So if you look at, and it's also shown by different continents. So if you look, if you look at all these bars here, you can see that the global health impact of WUI fire, which is the pink bar, is disproportionately large comparing to the emission ratio of WUI, emissions fraction of WUI fire, which is the blue bar. This is primarily because WUI fires are closer to human settlement. And at the global scale, the fraction of WUI fire cost APD to all fire cost APD is about 3.5 times larger of the fraction of their emission fraction. So this is 3.5 times is a very large difference. And the bottom panel shows the, it basically shows the same thing as the pink bar here. It shows the APD due to WUI fire relative to all APD due to all fires. But I calculate them by region. So the blue bars are for, I calculate the fraction over WUI. And for green bar, I calculate the fraction for urban. And the yellow shows the remote area. So as we can see, in almost all the continents, WUI fires have a relatively larger impact on WUI area and urban comparing to its impact over remote area. This is also reasonable and straightforward because WUI fires are within WUI area and they are usually closer to urban area. But the implication is that to understand urban air quality, it's very important to understand, to account for WUI fires and its emissions. And with that, I'll stop here with the take-home messages. I think I have time, so I will just read this. Fire in the WUI area is very important and will become more important in the future. And we developed a data set called WUI, and please check it out. It's available on the Zenodo website. And also here we use music version 0 model to show the significant impacts of WUI fire on air quality and health. And also most importantly, thank you for listening.
You mentioned at the start, that maybe these fires are maybe even more concerning because instead of burning a forest, you're burning houses and cars. In your model, does what's being released change based on whether you're burning a settled neighborhood or just a forest?
That is a great question. So in this study, we didn't. We only separate fires to WUI fire and wildland fire by its location. However, in our future study, we do want to address the different emissions involving structure burning and vehicle burning. It's challenging because not every WUI fire involves structure burning or vehicle burning. Sometimes it's just the wildland part of WUI that was burned. Thank you.
Hello, everybody. My name is Noribet Mariscal, and I'm a PhD candidate from Wayne State University in Detroit, Michigan. Today, I will be discussing the impact of horizontal resolution on ozone atmospheric chemistry in Southeast Michigan during the Moose campaign. Before getting started, I'd like to thank my advisors, my co-authors here, the ACOM scientists, and the Moose science teams for all of their support and data throughout this project. So. Is this a pointer? So ozone in Southeast Michigan. Ozone in Southeast Michigan often exceeds national ambient air quality standards set by the U.S. EPA, likely due to the various anthropogenic emissions that come from Monroe, Michigan, mobile and anthropogenic sources in Detroit, industrial emissions in East China, Michigan, and potential impacts from Sarnia's Chemical Valley in Ontario, Canada, as well as various other impacts from being surrounded by two of the Great Lakes, as well as Lake St. Clair, meteorology, and long-range transport. So in order to better understand the ozone chemistry in the region, I used Musica version 0's regional refinement capabilities to create a custom grid over the region. So here I created a 1/16 of a degree resolution over the state of Michigan, which is approximately 7 kilometers, which then transitions into about 14 kilometers over the remainder of EPA Region 5, and then 1 degree over the rest of the globe. For my simulations, I based myself on the Michigan-Ontario ozone experiment, whose goal was to define potential attainment strategies and understand why ozone is being exceeded in the region. The field campaign happened in 2 phases. So phase 1 was in the summer of 21, and then phase 2 in the summer of 2022, and included various high-resolution measurements such as vertical column densities from NASA Gulfstream 3 aircraft, as well as Pandora spectrometers, various chemical species from the Aerodyne Mobile Lab, as well as measurements from stationary sites all across the region. So for my particular study, I focus on the summer of 2021, or phase 1. I've run a total of 4 different simulations using 2 different resolutions. So the first resolution I used was the 14-kilometer CONUS grid that Wenfu mentioned in her previous presentation, and then my custom grid of 7 kilometers over the state of Michigan. In addition to that, I also implemented a diurnal cycle for nitric oxide anthropogenic emissions in CAMS. I used identical chemistry and nudging settings using the Mozart TS2 chemical mechanism, which includes comprehensive stratospheric and tropospheric chemistry with updated isoprene and terpene gas phase chemistry. Meteorology was using the MERA2 reanalysis data, and then emissions from CAMS and QFED here. So the plot I show up here is just the surface NO emissions relevant to the different grid resolution. So the NE30/8 or 14 kilometers on the left here, and then the 7 kilometer grid is on the right here. So this is shown relative to 2 sites. So in these 2 sites, one is a very urban site, so the Trinity site, and then the Allen Park site is more of a suburban area here. So in the coarser resolution, they're both in the same grid box, but kind of moving into the finer resolution helps apportion those sources a little bit better there. So I do want to emphasize the importance of diurnal cycles in the model. So I did mention at the beginning that I'm going to be discussing mainly the differences in resolution, but diurnal variations for anthropogenic emissions are currently not generally considered in CSM2. And when looking at the entire state of Michigan relative to Southeast Michigan, the energy and residential sectors made up 30% and 47% of total emissions within the state, with the transportation sectors not falling far behind here. For the implementation of the diurnal cycle, I used the sector and country-specific temporal profiles from Kripa et al., published in 2020, and these hourly profiles were based on the downscaling of annual emissions to hourly emissions per grid cell. So as you can see from the figure on the bottom left here, the diurnal cycle does change depending on the various emission sectors. To the right here, I show the NO2 and ozone surface concentrations from the 4 simulations that I ran compared to observations. So in the figure here, the black line represents the observations. I think that's green would be the coarser resolution, and then the blue would be the finer resolution. So here we can clearly see that there is definitely an improvement in NO2 simulation, especially during these peak times when adding the diurnal cycle at both regional refinement grids. There are also improvements in ozone bias during the same time frame as a result of this better NO2 simulation. And I just want to note as well that there is little to no change during these peak ozone times when adding the diurnal cycle, but it's still important to note that there is a significant improvement during these peak times here. So moving on, I do want to also emphasize that there are a lot of meteorological consistencies between my simulations that I ran. So for my study, I did not nudge within this state of Michigan region, and that's because the MERA2 reanalysis data is coarser than the actual spectral element grid that I used, but I did nudge within the rest of the globe. And the figures to the left here show temperature, relative humidity, planetary boundary layer height, and cloud total, compared along the Aerodyne mobile lab track with observations available for temperature and relative humidity. And it clearly shows that there are generally consistencies in all of the music assimilations, but they could potentially vary depending on the source or their proximity to different sources here. So moving on to the actual differences between grid resolution. So here I have carbon monoxide concentrations at the surface. So I'm going to move forward to this slide. But the first slide here is the NE30/8 coarser grid over the Southeast Michigan region. The middle plot shows the concentrations in the 7-kilometer grid. And then the last plot shows the regridded NE30/16 concentration subtracted by the coarser resolution. Here, the carbon monoxide fine-scale features are captured in both regional refinement grids, with point sources being better resolved in the NE30/16 or 7-kilometer resolution. Because CO is relatively chemically inactive, there's low chemistry effects due to this horizontal resolution. And here I show the ozone concentrations at the surface. Again, coarser resolution is the first plot. The middle plot is the NE30/16 fine resolution, and then the last one is the regridded NE30/16 subtracted by the coarser resolution. And here, it just generally, what I'm trying to say here is that the NE30/16 grid does capture more of the NOx titration, specifically over the urban source regions due to less artificial mixing of NOx in these areas, and that generally, regridding the output does not always reproduce similar results. So it's important, especially for more local scale studies, to look at these regional refinement grids. There are also changes in ozone here. So here I show NO emissions, ozone, nitric oxide, and nitrogen dioxide at an urban reference site. So I'm purely focusing on the models with the incorporated diurnal variation, where the green would be the coarser resolution, and then the blue would be the finer resolution. And here, the emissions can vary at specific locations, and this can ultimately result in changes or differences in ozone. So just by purely changing the resolution, we get changes in ozone of up to 10 parts per billion during the nighttime here. And then when we have this higher NO2 due to the higher resolution, this is likely a result of the more resolved emission plumes. I also want to show the impacts to biogenic VOCs, which are also dependent on grid resolution. So biogenic VOCs in Musica version 0 are calculated online via the Megan version 2.1 algorithm in the community land model. The first figure up on the top left corner is just a monthly average over June of isoprene, where the NE30/8 is on the left, and then the NE30/16 is to the right here. You can clearly show that although isoprene concentrations aren't tremendously enormous, there are very significant differences, and this is because these biogenics can be impacted by differences in the meteorological fields that result from the changing grid resolutions. So to the right of this heat map here, I show the isoprene time series again at an urban reference site, and the differences between the finer resolution on the bottom here can be 3 times a change. I also want to note in the bottom I have the hydroxyl radical at this particular location, which does not see many changes as a result of isoprene, and again, this is because the amount is not tremendously huge, but there are some differences when we're looking at formaldehyde. So now that I've discussed some of the general differences, I want to talk a little bit about the evaluation with the Moose campaign data sets. So right here, I show my model evaluation with the Aerodyne mobile lab. So this is hourly binned ozone and NO2 concentrations along the track, which was from the May 24th, 21 to June 30th of 2021, where the gray box represents the AML observations. The blue box represents the coarser NE30 by 8, and then the green or yellow box shows the NE30 by 16 here. So I want to note that both ozone and NO2 are generally well represented in both regional refinement grids, with ozone in the NE30 by 16 performing slightly best during these peak times here. I also compared the simulations, which in this case I only show the ones where I applied the diurnal cycle with the Pandora spectrometers. So I have NO2 and formaldehyde vertical column densities calculated up to about 3.4 kilometers at 2 sites in the region. So the Southwest Detroit and Dearborn, Michigan sites are relatively very near roads in very, very industrial areas here. And I want to note that the NO2 vertical column density model calculations generally performed well compared to the NO2 vertical column densities from Pandora, where we see a bit of a better reproduction in the model for formaldehyde vertical column densities by the NE30 by 16. And I note the normalized root mean squared error for the data sets in the top corner here. So there's an improvement when looking at the finer resolution. So in summary, I used Musica version 0 and its regional refinement capabilities to create this custom grid over Michigan. I applied the diurnal cycle for CAMS version 5.1 NO anthropogenic emissions, which improved the simulation of NO2 and ozone during peak NO2 times with little to no change in peak ozone. I also discussed changes due to grid resolution as a result from the artificial mixing and the misclassification of sources. And then finally, I discussed the similar performance, but slightly better representation in the NE30 by 16 during peak ozone times. So for my particular study, the regional refinement is important, but I think the diurnal cycle ended up being more important and necessary in this case. But yeah, thank you. If you have any questions, happy to answer.
Thank you for a great talk. So I'm wondering, NO2 and ozone is affected by resolution a lot, but the OH radical is quite insensitive to resolutions. So can you explain why?
In terms of the OH radical, so at this urban reference site, it didn't look like, so to be honest, I haven't looked at it too deeply, but because the concentrations of isoprene weren't too big, I'm assuming there was little titration there, but something that I plan to look at in the future. Thank you.
Yeah, really nice talk. So it seems like that the 7 kilometer is really doing better than if you have the higher resolution. Do you have any feeling for if you go even further to higher resolution, if that would make even a better comparison? And the other question also, have you looked even at the 1 degree, just for, seeing how worse it gets? So how much overestimation do we actually get in cities like that when we have our coarse resolution model?
To answer the first question, I would definitely like to try a finer resolution. I have not really thought about that yet. In terms of the coarser resolution, I myself have not looked at it, but I know Dusong looked at it over Korea, and there was a lot of, again, very source. The sources were distributed more evenly. It would be nice to see roads in Southeast Michigan at some point, though.
And therefore, you would even more overestimate the ozone, probably, right?
Right, yeah.
Okay, great. Any other questions? Stephanie, do you hear us? We don't hear you yet.
Hello.
Now we hear you and we see your slides.
Excellent.
Please go ahead.
Amazing.
Thank you.
Woohoo. Okay. Thanks everybody for hanging in there in the afternoon and joining remotely from New Hampshire. So I'm Denny Murray. I'm a PhD candidate at the University of New Hampshire. And as part of NCAR's graduate visitor program, I've been collaborating with Rebecca Buckles and others to validate the modeled atmospheric deposition time series with observed long-term records from across the US. So atmospheric deposition is a main mechanism for the loss of aerosols and chemicals that are in the atmosphere to come back down to the land surface. And this can occur via either wet deposition, via rain, or dust or dry deposition. But wet deposition in particular has consequences for ecosystem biogeochemical cycles, such as stream chemistry, which is shown in this graph of wet deposition in organic nitrogen on the x-axis and stream nitrate concentrations on the y-axis from sites across the US, and showing a very strong positive relationship. So this parameter has real ecosystem consequences and also has importance for my own dissertation research questions, which deals with how important wet deposition is to large-scale ecosystem biogeochemical cycles. Wet deposition chemistry has been monitored by the National Atmospheric Deposition Program at a weekly scale for 390 sites across the US. So this map shows each of those sites with the color of points showing the length of site operation. And at each of these sites, wet deposition is collected using the exact same protocol, which I have a video of here. So rain is collected via a bucket that has a lid that only opens when it's actively raining. The bucket is left out for multiple days at a time, usually about a week. And then it's brought back to the lab where the sample is filtered and analyzed for a suite of solutes. Very importantly to understand is that the concentrations in the bucket reflect a composite sample of any number of rain events that occurred within that sampling window, which very much varies through time and space. And then also this method is only measuring wet deposition, so no dry deposition or dust are considered in these measurements. Wet deposition chemistry and flux of many types of aerosol and chemical species are also modeled in CESM. So here's a schematic of the components of CESM, which I'm sure you're all very familiar with, where wet deposition, scavenging, and flux are parameterized within the atmospheric model CAM6. And then within the model, there are, sort of four main primary drivers of wet deposition. Of course, landscape emissions, the transport of these chemicals and aerosols in the atmosphere, the chemical forcings acting upon these species in the atmosphere, and then finally, whether or not these ions get deposited back to the landscape is determined by the specific deposition parameterization in the model. And this parameterization considers both in-cloud and below-cloud scavenging rates and solubility factors of both aerosol and chemical species, where wet removal is generally modeled based on a simple first-order loss process and the effective Henry law. So wet removal is roughly equal to your solubility factor of a species, scaled by its scavenging coefficient, and scaled by precipitation rate. The solubility of a gas is determined by Henry's law, and this varies based on particle size as well. So in this study, we are really focusing on the wet deposition of three species, sulfate, nitrate, and ammonium. Previous validation of these wet deposition solutes and the wet deposition parameterization as a whole has been limited, and we're really interested in expanding on this. So the objective of this project was to assess the accuracy of CAM6 modeled wet deposition over the continental US. And we approached this objective by pairing the CAM-CHEM modeled and the National Atmospheric Deposition Program observed wet deposition records of sulfate, nitrate, and ammonium from 2002 to 2022. And then after we paired the point and gridded data, we are focusing on two primary analyses, at least for this talk. So the first is identifying potential sources of error between our modeled and observed solutes. And then also, where is our model deposition parameters performing within an acceptable range? So we conducted a global model run of CESM 2.2 and CAM6 using full chemistry from 2002 to 2022 at the 1 degree resolution with 32 levels. We used Mozart T1 chemistry and MERA2 nudged at 10%. Our anthropogenic emissions were based off of TAMS, our fire emissions based off of QFED, and our biogenic emissions based off the online Megan scheme. And then ultimately, we output our wet deposition parameters and other variables that we thought might be useful in our data interpretation at the daily average scale. So after running the model, we performed a series of steps to merge the modeled and the observed wet. So the very first thing that we had to do was get our units to be the same. So we're
Denny, just a second. Denny, do you hear me? Hello? She doesn't. Can we stop her somehow?
Denny, can you hear us? Denny, hold on. We've lost your audio in the room. Give us one moment, please.
Okay.
Maybe she starts again with that slide. Can you ask her to start with the slide again?
Can you hear me now?
Not only online, not inside the room. But can you go back a slide?
This one?
Yes, now we can hear you. You're back. You're back.
Okay, great. Let me know if that happens again.
Okay, we'll do.
Okay, great. So I'll just start from the top here. So sort of to address our research question, which was
sorry, Denny. Go back one slide. We lost you for 30 seconds. Oh, forward. Sorry. One more. Good. That's good.
Okay, great. Then I think it only cut out for like a very brief moment. So the main point I'm trying to convey here is that we need to get our units to be the same. Our desired unit is an areal flux. This is easy for the model. We just have to convert to a smaller gram size. And then for our observed data, we multiply by the co-reported precipitation depth of that given chemistry sample. Then the next thing that we did was we selected the nearest grid cell to our observed site latitude and longitude, and then extracted that modeled point data from the grid cell. So as I mentioned, the modeled point data was at a daily scale. But if you recall, we actually have observed data that's collected at very irregular intervals. And this is because it's human error, like people are going out and collecting these samples. And so one sample could be reflective of 5 days and another sample could be reflective of 2 weeks. So for each site, we had to assign the daily modeled data a unique identification number that corresponds to our observed sampling interval of date on and date off. And then we summed these daily modeled values that were within that observed sampling window so that our observed and modeled are representative of the same time period. So after doing all of these steps, this ultimately resulted in a merged data frame that contained paired observations from 333 sites across the US, with on average 585 observations per site and over 180,000 observations per solute. So with this initial data frame, the first thing we did was calculate the percent error between each paired data point of modeled and observed wet deposition. And then the graphs that you're looking at here are just a frequency distribution of the percent error for each solute, with sulfate on the top left, nitrate on the top right, and then ammonium on the bottom left, and precipitation on the bottom right. You can see that most of the data for percent error is lying within that 0 to 100% error range, which is to the left of that red dashed line, and is also within about 1 order of magnitude of one another. And if we break down this percent error by month for each solute, which is again organized in a grid in the same way, that red dashed line is still sitting at 100%. We do see some seasonal variability in how well that model is predicting those observed data points, with sulfate and precipitation showing higher percent error or more inaccurate values in the summer months. Nitrate tends to perform relatively well. Most of our data is sitting below that 100% threshold, and ammonium has a very large range of a percent error. And then also it has that summer elevation, but it also has some winter elevation as well. And we're really interested in what are some of the potential sources of error between our modeled and observed solutes. So we decided to filter our data on precipitation accuracy. This is a scalar variable for both the modeled and observed data set. So if the model is not accurately predicting this variable, the deposition flux will be off regardless of accuracy of emissions or chemistry. And so to clean our data set for points that had relatively accurate precipitation data, we removed data that had a percent error for precipitation depth that was greater than 100%. So in the end, this only eliminated 2 total sites, and on average reduced our total observations and average observations per site by about 25%. And if we now again bin that remaining percent error after filtering on precipitation that varies seasonally, we see that for sulfate, nitrate, and precipitation, we don't see that strong seasonal signal any longer. However, it does still remain for ammonium. And we can actually take some interesting takeaways away just from the simple exercise of data cleaning. For example, after we clean on precipitation, we can learn that like inaccurate precipitation depth may be a large source of error for the sulfate and nitrate wet deposition parameters, but it didn't really do that much for ammonium, indicating that there's another source of major error for that solute, which could be emissions or chemistry. And then I'll also mention here that ammonium deposition scavenging is under an older version than the other solutes, so this could be also playing a larger role in its error relative to the others. So to reduce any remaining outliers in the data set before moving on to a spatial assessment of model performance, we performed one other data filter where we filtered on the percent error threshold of first our precipitation, and then any remaining data points we also filtered on percent error of our chemistry. And so overall, this spatially retained all of our sites, but we had an additional 20% reduction in our data frame. And using this final sort of quote unquote clean data frame, we can start to really answer the question of where do modeled wet deposition parameters perform acceptably. And the reason why we're filtering our data and we're really trying to figure out these certain spots where the model's doing well is that this is sort of a first step for us in a further study to understand drivers of wet deposition. And so we need to sort of understand first where the model is even predicting wet deposition well. And so we assessed model performance for each site using a clean Gupta efficiency metric, which essentially combines correlation, bias, and variability. So your R squared, your Rs, your RMSD, your slopes, to provide a comprehensive assessment of the model's ability to reproduce the observed variability. So again, we calculated this metric 1 per site to understand spatial variability. And if you're not familiar with this metric, the main thing you need to focus on is that KGEs above 0.4 are what we consider an acceptable model performance. This is a very conservative value. This number ranges from -infinity to 1. So that 0.4 to 1 range is really we're focusing on when our model and where our model has those values. So here I'll show you a series of histograms and maps of the KGE distribution for that merged data frame that was filtered for 100% error on precipitation and then 100% error on chemistry. This first graph is for sulfate. The top graph is the frequency distribution of those KGE values, again, 1 per site. That red dashed line represents the 0.4 threshold that we're using as acceptable. And so you can see we have a lot of sites that are above that 0.4 line, and that's quite clearly conveyed in our map here as well, with the color of those points ranging from acceptable at 5 or 0.4 to excellent. Our highest score was, I think, a 0.9. The open circles are unacceptable. So those sites had KGE values below that 0.4 range, and so we did not include it sort of in this final data set, but I wanted to show you where those sites were. So one thing that we can take away is some regional variability. We see that in the Great Basin particularly, we have a lot of sites that are not performing well. This could be, this is a very arid region. So again, highlighting the fact that precipitation accuracy is really important. We may have also removed lots of data from here, which does result, of course, in like less statistical power. So we're still exploring, what's going on with these error sources as well. So for nitrate, we see a very different story. We have far fewer sites that perform acceptably. We have about 50-50 sites above that 0.4 and below that 0.4 threshold. And some very obvious gaps here as well in the Rocky Mountains. Again, a very arid region, but then we also have a large gap in the southeast where it's very wet. And I'm not showing this data here, but that most of these errors, or most of these sites are inflated error in the summer. So this is when we have high chances of precipitation, potentially high rainfall events, at least for the southeast or monsoonal and the Rocky Mountains. So we have some investigating to do there as well. And then finally, for ammonium, even though we had to filter a lot of data here, we actually found that what the remaining data points performed extremely well, with most of our most of our sites having a very good to excellent KGE score, with only about 5 sites having no not acceptable data. So just some final key points to leave you all with. You know, one of our major results suggests that a large source of error for wet deposition of sulfate and nitrate may be inaccurate precipitation depth, but the error for ammonium may be more closely linked to errors in emissions or chemistry. And then the second is that the model has more acceptable spatial performance for sulfate and ammonium, while nitrate performs poorly in regions that may be experiencing precipitation extremes. This work is very much still a work in progress. We have a lot of next steps to execute, such as continuing to evaluate those error sources and ultimately developing a best practice for using the CAM-CHEM wet deposition data. We'd like to include the validation of organic carbon and black carbon wet deposition solutes. And finally, as we've heard from a lot of the talks already today, the resolution matters, so assess differences in wet deposition accuracy between the global model and then the Musica regionally refined over CONUS for a selected time period. Thank you to all of our funders, my advisor at UNH, Rebecca, for being a wonderful advisor, all the people who have developed code and resources online, and for the advanced student program fellowship. So if I have time, I can take questions. Thank you.
Thank you very much. Okay, are there questions for Danny? There's one online, okay. Do you want to, oh, yeah.
Do you hear me?
Yeah. Yes, I can hear you.
Okay, great. So really nice talk. Actually, when you talk about I mean, I'm most interested in the model results. So you use the new wet depth routine for all of these results. I fight a lot with that routine for halogens deposition, wet deposition. And first thing, we found that there is a real big difference when you compute the deposition for a nudging configuration or a free running, which I could not understand why. And it might be due to these precipitation differences and the errors that you were showing. So that's really interesting for me. I was wondering if you have performed free running simulations. You mentioned you use only nudge. And the other question was if you ever consider ice uptake for any of these species, which is some other of the parameters that can be done in that routine.
Yeah, thanks for that question. So no to the first one, we have not done the free running simulations. We've just done the nudged. And Rebecca and I can chat about that, what that sort of implies. But thank you for that suggestion. And then for your second question, yes, the ice uptake, is particularly for ammonium, is relevant. However, spatially, where our studies confined, we're not as considering that as much. But I do want to explore, you know, how there, because of that seasonal variability, like how if the precipitation was rain versus snow, that might also be like factoring into how well the model is performing. So thank you.
Okay, thank you.
Okay, thanks. There's another long question online. I don't know if you can see the chat. Maybe you want to answer it in the chat and we move on, unless you want to address it now.
Yeah, so the question's about field methods for collecting precipitation. And I encourage everyone to look up the National Atmospheric Deposition Program's protocols. They're highly robust. They are, the question is concerned with sort of residual chemistry that might be there when the bucket is being changed out. These buckets are changed every week, so it's not the same bucket being used. We are very aware, we are measuring trace elements in a lot of ways. And so this program is hyper-focused on accuracy of chemistry. So we, for example, change the bucket out every time we go out. When the new bucket's in the lab, it's being soaked in deionized water. these samples are filtered almost immediately. So certainly there is potential for gaseous loss in the bucket, even though it's sealed. But in terms of like contamination within the bucket itself, that's likely very minimal.
Okay, great. Thank you very much. If there's no other questions, the next speaker is Ben Gobert.
Good afternoon, everyone. I'm Ben from NCAR ECOM, and most of the work has been done by Amin, who is in the room from University of Arizona under a NOAA grant. And we are grateful for people sharing the data, and Rafa Fernandez for sharing the SLH chemistry code. It doesn't. Yeah, there we go. So there are many science questions. How do we assess methane removal technologies if they have any impact on methane concentration? There is a surge in methane emissions from wetlands over the recent years that further accelerate the methane growth rate in the atmosphere, as you can see here on the methane NOAA concentration curve. And we don't even know if there is a feedback loop or a tipping point that is already happening, and we have no way to estimate this with current CESM framework. On the further acceleration in recent years, we know that it's climate, weather, emission, two-way feedback related with consecutive El Niñas, for instance. And we know that the role of chemistry during COVID might have been important, but really we cannot really assess those questions with current CSM. And there is a reason for that. The main reason is that we tend to overestimate the OH distribution, and so we, so if you look to the right here, that if you input an OH from a CMIP6 model into a emission inversion system, you will end up with an overestimation of emissions, which means that there is a direct relationship between a methane sink due to OH and the methane emissions, which you need to balance in order to get the concentration right. And so this is a demonstration that CMIP6 models are inadequate to represent methane. The trends of OH are estimated, and the global OH is usually estimated from methichloroform observations, and the CMIP6 models from the modeling, and those two estimates disagree. As shown here, the chapter 6 of the latest IPCC report on the short-lived climate forces, where you can see that they don't even agree on the trend of OH over the last 30 years. And last, also using methichloroform, there is interhemispheric parity that that fits the inversions of methichloroform. And the CMIP6 models tend to have more OH in the northern hemisphere. And so that's another disagreement here. So this is the reason why CMIP6 protocol is using a concentration-driven methane simulation, where you prescribe using observations and then scenarios for future years. But we represent the OH chemistry the best we can, and we take into account the water cycle, clouds, and photochemistry that are important. And then we obtain very detailed OH fields. That's what you get in a CMIP6. So here I'm trying to advocate for emission-driven methane simulation, where I'm trying to take into account those emission, chemistry, climate feedback. Then you can evaluate the impact of chemistry and chemistry change on the methane growth rate. You could include the chemical feedback, and and later on, we hope to also include those climate feedbacks through soil and wetlands response to climate and weather. And so here is an example of using the carbon tracker Methane from NOAA, input fluxes and running the system. And so you can see that concentrations are not that different compared to CMIP6, and then you finally get some longitudinal gradients in methane. So what we did is to use a CSM 2.2 at 1 degree. And we used 3 different methane emission inventories. So they're actually top-down inversions using surface methane and surface isotopes in situ measurements of, to optimize prior fluxes. And so the 2 from the GCP and with 1 including actually satellite GOSAT inversions and 1 from carbon tracker from NOAA. And then we did 2 different chemistry scenarios, one with the Mozart 1.2 and one with the SLH. So that's, you get a great combination of simulations that I'm showing here. I'm also using the CAMS 5.3 and FIN 2.5 to drive the chemistry. So we know from the updated SLH chemistry in, so I should say representation, because it's not just chemistry, there are also emissions of natural and anthropogenic halogen compounds, and some update to other chemical, such as chemical processes, such as aerosol uptake of some reactions. And so we know the OH is the dominant methane loss, and the net impact of adding this SLH representation is a reduction in OH and an increase in methane lifetime. So here are all the simulations. I don't know how the colors are, yeah. I tried to keep a color code because there is a lot of them, but I'm trying to contrast TS 1.2 versus TS 1.2 with halogen, and prescribed CMIP6 versus GCP surface, GCP GOSAT inversions, carbon tracker methane inversions. And then we had additional inversions of CO to provide the impact of CO in an emission-driven methane simulation. So here's like the main results in 3 slides. So that if I don't have time to keep going, at least you can remember this. So if you're using, this is a prescribed, so it's kind of something that should reflect what I show on the first slide, which is the NOAA methane global concentrations. This is actually for the Northern Hemisphere, but it can be considered as the truth here. And you can see that you start in 2014. After some years, you don't even have a positive methane growth rate. So it's not even realistic when you use the default chemistry. And those are 3 different emission-driven simulations. With this one from the carbon tracker has higher emissions, so you get higher methane concentrations. When you use the SLH representation, the blue line doesn't change because the methane is prescribed. But the overall, the 3 different emission-driven simulations, not only they're much closer with a positive growth rate to the blue line, but they also bracket what we actually get into the concentrations. So they provide a nice uncertainty estimate on the methane concentrations over those 5 years. And then we did 2 other additional simulations where I used the posterior CO simulation instead of CAMS CO. And one where we reduce the deposition for this simulation. So yeah, the SLH chemistry allows us to get a pretty good grip on methane. The main reason being the methane loss. It's around 600 teragrams per year. So this is the tropospheric global methane loss per year, but that includes all the chemical loss, so OH, chlorine, mainly relevant in the troposphere. And we get a value of around 600 in current Mozart chemistry, and having a value of around 560, 540 teragrams gives you a nicer range of methane concentrations. So yeah, now we can dig a little bit more into the interesting aspect of when you do such thing. So here we do it in CSM 2.2. So here is the impact of SLH in prescribed simulations. And this is the total column of methane, CO, and ozone, and this is the differences between halogen minus standard. And those are the seasonal differences. So the methane doesn't change because it's prescribed at the surface. You can see some convection patterns, maybe some nonlinear feedback, but that's very minimal because we're prescribing the methane. And it's well known from previously representation of halogen papers in different models that when you introduce the halogen, you get a catalytic destruction of ozone, especially in the spring of the high latitudes. And this reduction in ozone is usually reducing OH, and then you have an increase in CO. So this is due to the chemistry, because the emissions are the same. So now if I do the same differences in emission-driven, so you will have the same impact of chemistry on ozone that impacts on CO, but now this would feed back to methane because methane is allowed to evolve freely. And so if I do the difference between those two experiments, this should normally be 0, but because we introduce the CO to methane feedback, we actually increase CO, and that increase in CO then feed back to methane, and so you get an increase in methane due solely to the chemical feedback. And so this means that if you do if you want to evaluate the impact of chemistry representation, if you do a concentration-driven, you will have a different result than if you have an emission-driven. So now I will go through the observations to verify. ATOM is very nice because you get a wide range of latitude over 2 different ocean basins and vertical profiles. As you can see here for ATOM 3, so lots of vertical profiles. It's important for validating models. So I try to use the same color scheme. So it's a bit, there's a lot here because we have a lot of simulations, but it's again the same results than what you see with the time series. The TS1.2 are overestimating OH. So then when you compare here for methane in the northern extratropics, ATOM 1 in the summer, ATOM 2 in February, ATOM 3 in the fall, and ATOM 4 in the spring, you would see those 3 lines underestimating methane after only a few years of simulation, with the blue line being the prescribed. And then the dashed lines here and to the right of the observations are also bracketing the observations the same way than we saw with the time series. So this is particularly true for the northern extratropics, where it is known to we overestimate OH. And but for the tropics, we're doing also pretty well. With now the dashed lines are pretty close to the observations. So here's for CO. So as Simon mentioned, we have this overestimation of OH in the northern extratropics have been lasting for as long as we measure CO in the northern extratropics. And so now we're getting very close by having an increase due to chemistry, and then if you're using the posterior CO emissions, you're now almost to the right of the observations, but by only a few ppbs. And so for ozone, this is where things are a bit more complicated to analyze because you get different biases in different seasons and different regions of the world. But most of the time, we reduce ozone in the dashed, so SLH simulations. When the solid lines, we tend to overestimate ozone. So it's a bit of a mixed bag where sometimes it performs better, sometimes it is worse. And there might be some more balance between the light inox sources of ozone in the tropics also. That might have an impact. But overall, we used to overestimate ozone, so it still goes in the right direction. CO from MOPIT, a bit a similar story where the prescribed were doing pretty well in the southern hemisphere. And FIN is overestimating the tropical emissions with a lot of spread from the fire emissions. But here you can see that this gray area is from the observations, spatial standard deviation. It's not the uncertainties. So we don't even match the mean MOPIT within the observational variation within the northern extratropics region. So if you look at the time series, the same thing, we now even overestimate the CO by a little bit, especially in April. But overall, the new simulations perform much better, which is an indication. Also, if you look at the differences compared to the black curve, you can see that it's pretty much an offset over time, which suggests that it's mainly due to OH biases and not to emissions. And so by improving our representation of OH, we improve our CO. And then we use the NDAC observations that allows to measure at the same time methane and CO and other species. And so here's an example of scatter plot of simulated versus observed methane observations. And you can see that there is overall RMSE of around 40 ppb when you're using the prescribed methane. So that's kind of a reference here. So when you use the carbon tracker methane, so it's just one example here because this one is higher. This one has higher emissions and higher methane concentrations. Then you end up overestimating methane and having around 50 ppb. So it's a bit larger errors than the prescribed, but still we're now in the same range, which means that it's much more reasonable. And then when you add the CO, it's even higher. But those are not the right example because we are still within the error bars on the emissions and the deposition of methane. But then we end up here with more methane. But the main message being that the RMSE values are similar to the one that are prescribed, at least by CMIP6 scenarios for this period. But what's interesting is running with the methane emission-driven simulations actually improve CO. And that's because we enable those feedback. And then when you're using posterior CO and reduced bias of methane, you actually reduce the CO errors by quite a lot. So there are really synergies between CO and methane when you're using an emission-driven simulation. So yeah, in summary, we use 3 different observation data sets, aircraft observations, satellite CO, and NDAC, ground-based remote sensing of methane and CO, that all show that we can reduce the CO bias when using the SLH representation and with emission-driven methane simulation. And then we can appreciate the chemical feedback. So this is just the beginning. We want to do many of those studies. But yeah, this is part of a larger vision where we want to be able to represent the feedback between methane concentration, climate change, and the feedback to emissions, where wetlands, and it's actually also coupled with the water cycle, and all of these would feed back to chemistry in one way or the other. And it's very important to represent those emission chemistry climate feedback, especially that it's could be a tipping point that it might already be happening according to some studies. Yeah. So that's all I have. Thank you.
Yeah, very nice talk, thank you. So, I mean, it looks like the emission-driven configuration for methane is performing pretty well. Is this a candidate for inclusion in your CSM3 model, or what are your plans in that space?
Yeah, we will keep working on it. So the main development would be to include the feedback with the wetland emissions from CLM, and I don't think this is going to be part of CSM3. But we hope to get it done on the side, yeah. Maybe not for, but we just want to do it before CMIP 8. Yeah, yeah.
Since the next talk is cancelled, if I'm correct, we have plenty of time for the last presentation for Christopher Brunette. Please, come ahead.
Hi, everyone. My name is Chris Brunet. I'm a graduate researcher at the University of Iowa, and today I'm going to talk about this class of chemicals called volatile methyl siloxanes. So volatile methyl siloxanes, or VMS, are these synthetic compounds that are widely found in consumer items and in particularly in personal care products. So if you go and look at the back of your deodorant or skin lotion or anything like that, you'll find at least one of these. And as you might imagine from the name, these chemicals are highly volatile, and because of the fact that they're included in these products, we lose almost all of the VMS that are put in production every year into the atmosphere, where they then undergo oxidation by hydroxyl and chlorine radicals. So these compounds have gained a lot of attention in the past 2 decades, primarily because of their relatively long atmospheric lifetimes and because of a number of chamber studies showing their ability to form secondary organic aerosols. And so that's created the attention of a lot of regulatory communities who are interested in the potential health impacts, and from researchers as well who see them as potential tracer compounds for other VOCs that form secondary organic aerosols. So I am not a modeler by trade. I'm primarily an analytical chemist and a field researcher. So when we wanted to figure out what was happening with these things, the first thing that we did was to go and look for them in the environment. So this is work that was just recently published from a field campaign that we did in New York City, and a number of other groups have gone out and measured these things in the environment. You can see on the right here the locations where we have previous field studies with measurements of at least one of these compounds. But after all of this work, there's still a lot of questions that we have that we can only really get at with atmospheric modeling, which is what leads me here today. So we're not the first people to try and add these compounds to atmospheric models. A little over a decade ago, folks started trying to add them to these hemispheric models, and then more recently, people have started adding them to the community multi-scale air quality models, CPAC. But those models still have a lot of limitations that make it difficult to answer the questions that we want to get at. To start, many of them had very limited geographical domains, focusing only on the continental United States, or even when they went up to hemispheric scale, they did so at very poor spatial resolution. In addition, the per capita emissions that have been published in the literature for these compounds and that went into these models vary all over the place. And so you can imagine that if you pick that first number or that sixth number to use in your model, you get a very different result. And then perhaps most importantly, the chemical mechanisms in these models didn't capture what we fully know today about the oxidation of these compounds. So what we know is that these compounds oxidize with both hydroxyl and chlorine radicals, that those reactions are temperature dependent, and that their oxidized byproducts go on to form these SOA. And most of the models to date have basically only used this non-temperature dependent hydroxyl radical oxidation. So I'm going to talk now a little bit about the temperature and the chlorine, and then a little later you'll hear from Saide about the aerosols. So our goal was to take CESM and create a global atmospheric model of 3 of these compounds, D4, D5, and D6, and use it to answer a couple of questions. In particular, how adding temperature dependence to the model influences the concentrations and lifetimes of these compounds. Next, how adding chlorine oxidation affects the same things. And then third, to see if we can roughly predict a range of concentrations that we see globally, using population density as the only predictive factor. And today I'm really primarily going to focus just on this first one. So this is our model setup. I'm not going to spend a lot of time here because I think most of these things are pretty routine. You know, we add our emissions, we update the chemical mechanism for our compounds and add wet and dry deposition. One thing I want to highlight is we're working on adding the updated halogen chemistry that you heard a little bit about and that I think you're going to hear a little bit more about at the end of the session. So thank you to everyone working on that, because obviously it's hard to look at the effect of chlorine if your chlorine concentrations are not right. And then we add initial conditions for everything except our compounds of interest. We spin up the model and we do our core model runs. So the main model runs are sort of the heart of our experiment. So we do 4 core runs. One sort of control where we mimic what previous models have done, a run where we add temperature dependence, a run where we add chlorine oxidation, and then a run where we did both. As I said, today I'm really going to focus on the contrast of just these first 2. So I'm not, as I said, I'm not going to talk a lot about this, but one thing I want to focus on is how we create these emissions files. So I mentioned previously that the per capita emissions rates that people have come up with for these compounds vary all over the place. And so we kind of had to pick a place to start. And sort of our first hint for that was in the New York study, the New York field study that I mentioned previously. And so when we had gathered our data from that study, we wanted to see how some of these previous models had done at predicting those concentrations. So this here is the concentration on the y-axis of our 3 compounds, D4, D5, and D6 for New York City in July. And then from that previous CMAQ model, and then our measurements on the right. And this is really important for the per capita emissions, because near a major emission source like New York City, the emissions rather than the chemistry are sort of the primary driving factor. And so this agreement looked pretty remarkably good to us, and so we took their number for the US as sort of a starting point. But then we had to figure out the rest of the world. And so what we did was we took that number for the US and we extrapolated it to the rest of the world based on country-specific per capita personal care product sales revenue, figuring that the more personal care products you're buying and using, the more of these compounds that you're releasing. We then combined those emission rates with population density data at a 1 by 1 kilometer resolution, and that gave us sort of our gridded emissions. And then we just scaled that up to create an emissions file for the model. And you can see that this looks roughly like what you would expect. we get very high. Are you seeing the colors weird, or is that my angle? Okay. Okay. What? It's just the color scheme. Okay, never mind. Okay, so the very dark green regions here you can see are generally where people live. So the west coast of the United States, the east coast of the United States, Europe, Japan, East China. So this looks like what we would expect. Okay, so I'm going to show you some very initial, and I've been asked to stress to you, very preliminary results. We're in the early days of this. But here is sort of the base model map of the surface concentrations of D5 in February of 2020. And you can see, again, that this is what we would expect. The high concentrations are near areas where people live, and the peak concentrations that we're seeing, which are in the range of 300 to 400 nanograms per meter cubed, are pretty comparable to what we see in field studies. And you can also see this thing where there's very little hemispheric exchange on the time scale of the lifetime of these compounds. And so because most of the emissions are concentrated in the northern hemisphere, even away from those emission sources, you get a much higher background in the northern hemisphere than the southern hemisphere. So that's kind of the base model, similar to what previously people have done. The question then is, what happens when you add temperature dependence? So this is various regions of the world and their relative D5 surface concentrations normalized sort of the base model with no changes. So you can see the percent difference. And you can see that this is winter. We're below standard temperature. The oxidation is slowing down. And so across the board, we're getting an increase in the surface concentrations. But you'll see that the effect becomes a lot more profound the further that you move away from the emission source and the more time there is for these compounds to oxidize and for the sort of differential to occur. So, you know, China, the continental United States, and Europe, these are 5 to 10% increases. But as we start to get into the Arctic and the Antarctic, we're seeing increases on the order of 20 to 100%. And globally, adding this temperature dependence increases the atmospheric lifetimes of these compounds by over 2 days. This is kind of a similar comparison, but shown as a differential map. So the areas in blue here are where adding temperature dependence causes the concentrations to be higher in the model, and then the sort of dark green is where they're lower in the temperature dependent model. And you see a similar thing. Most of the changes are occurring away from the emission sources where a lot of oxidation has had time to occur. So in the Antarctic, oxidation is slowing down, the concentrations are increasing, and then you can see this sort of hot spot in the Indian Ocean where we're getting emissions probably from East Asia that have time to transport through a very hot region where oxidation is faster, and there's a lot of OH there for them to oxidize, and that causes the temperature dependent model to actually predict lower concentrations. One final thing that you might sort of think about looking at this is why the Antarctic is so much more affected than the Arctic. And so what I would point out is that this is February. It's winter in the northern hemisphere, and so we have relatively less oxidation going on during that transport, especially in the colder regions. So we expect that the regions that are being impacted are probably going to change significantly as you look at different times of the year. So this is the early days. We're going to do some longer model runs to look at those seasonal changes, finish those updates to the halogen chemistry and look at chlorine oxidation, and then do a more rigorous comparison of our model results to the concentrations that we've seen in field campaigns. I want to thank everyone who has helped make this possible, especially our funders, the NIH and the NSF, and I would be happy to take any comments or suggestions you have. Thanks.
So the lifetime of the big ring molecule was 9 days to 11 days, something like that?
Yeah.
How about the byproducts? Do you know the whole mechanism, how it degrades, and are there any issues there?
There are people studying the full mechanism, but I would not say that we really have a good handle on what the reaction rates and lifetimes are for those yet. It's in progress.
There's no forever chemical.
No, the SOA production is really the big concern. Yeah. And sorry, I'll say one other thing to that, which is that the byproducts are much less volatile than the parent compounds, and so wet and dry deposition is probably, and the incorporation of aerosols is probably more of the important removal mechanism there than the further chemical oxidation.
All right, people are just filtering in through the doors for the afternoon session of the Chemistry Climate Working Group session, and we'll get started. So our first speaker is Ren Smith. He'll be talking about some evaluation with ACLIP campaign.
Oh yeah, how does this work? Everybody seems to be confused. Okay, and that's the laser pointer, and that's, oh, look at that. All right. Okay. Good afternoon, everybody. My name is Ren Smith. I'm a project scientist here at ACOM and NCAR. Hi, Simone. Sorry. What? Oh, yeah, no, I didn't just introduce myself. No, Rebecca covered me. We're good. Okay, so anyway, yeah, I'm Ren Smith. I'm a project scientist here at the ACOM lab at NCAR. I'm going to be looking at some preliminary evaluation of CESM Karma with a couple of Asian monsoon airborne field campaign. I want to emphasize this is kind of preliminary and ongoing work that we're doing right now. Of course, acknowledge Simone as well as Yunchen Zhu for helpful comments and insights as we go along with this. So I always like to start out by talking about why actually I wonder if this is going to play. I always like to start out by talking about why the Asian monsoon is an important thing worth studying. There we go. And so this is actually a 3D rendering from the NCAR Musica model of carbon monoxide during the summer 2022 season. And you can see actually the pronounced amount of CO in the boundary layer that's being lofted into the upper troposphere and lower stratosphere by deep convection, sort of spiraling around in a large-scale anticyclone at that level, and then being redistributed throughout the global atmosphere that you can see in this animation here. And so this, I think, provides some context for why the Asian monsoon is worth studying to understand sort of how these boundary layer constituents are sort of redistributed in the role that they can have on the climate system. From an aerosol standpoint, the Asian monsoon UTLS is associated with an enhanced aerosol concentration. This is known as the ATAL. That's the Asian tropopause aerosol layer. And so you can see an example of this in this schematic. I think the reds on the projector might be out again, but so that might be interesting in some of my later plots. But you can see actually that species that are lofted here, at least in the schematic, as the air masses rise and spiral around in the Asian monsoon anticyclone, as they rise, you get particle growth and processing, and you end up with this sort of pronounced layer near the tropopause, something like 380, 390 K potential temperature. You see that maximum in organics, nitrates, ammonium, and an enhancement in sulfate as well. And so this is, of course, important for things like the radiative budget. And so being able to model these, being able to model this process accurately is certainly important. So I mentioned we got a couple of Asian monsoon focused campaigns. I'm showing here just a little highlight from the recent ACLIP campaign. That's the Asian Summer Monsoon Chemical and Climate Impact Project. This took place over with a base near Seoul, South Korea, and we had two research aircraft, the NSF NCAR Gulfstream 5, as well as the NASA WB-57, and I'll show on the next slide, these two planes were sort of intended to sample different altitude and horizontal sort of spaces with each other. And I'm not going to talk about all of the instruments that are on board, but I'll just say that the two aircraft had a really comprehensive suite of chemical and aerosol sampling instrumentation as well that allows us to do some model evaluation. And I'll also just quickly note, without actually talking about it really at all in this presentation, there was also quite a bit of ground-based component as well, and we do actually want to add that into our evaluation as well. You can see the great sort of collaboration that we had with teams throughout the Western Pacific to help constrain that from a ground-based and, I should say, balloon-borne, a lot of balloon-borne observations as well. Some of them are aerosol instruments, and so that might be something that we can do going in the future. So I just mentioned the ACLIP campaign. We also show some results from another campaign that was called Stratoclim. That's shown in the top panels. And Stratoclim sampled over the southern flank of the Tibetan Plateau that was based in Nepal. And that's sort of, if you remember that animation all the way back at the beginning, that's sort of one of the primary uplift regions for boundary layer air masses to enter into the UTLS. And then, of course, the ACLIP campaign is sort of, so we have the uplift region, and then we have sort of an export region, and that was the whole sort of premise behind the ACLIP campaign. And so you see the flight tracks for the two different campaigns here in the different regions, as well as sort of the different altitude samplings. And I mentioned the two aircraft in ACLIP that had the two different sort of sampling regimes. You can see the two aircrafts kind of broken down there in the vertical as well. And the two different, I'll just briefly mention a note about the model simulations that we're looking at here. I'm not going to dive too much into the details here, but I think the main sort of thing that I want to emphasize is that the main primary difference between two different model configurations is that we're looking at the Karma aerosol model versus that's the community aerosol model for atmospheres, and then the MAM4 modal atmosphere or modal aerosol model configurations that we're looking at there. And this plot, actually, Simone showed this earlier, but this is from one of her papers recently evaluating against airborne observations. So Karma and MAM4 overall doing a good job, and so we want to essentially take this and apply it to the Asian monsoon region. Okay, so I've introduced this enough. I can start showing some results here. So I'm leading off with a comparison of black carbon, and this is in sort of a profile space here. We're looking at black carbon mass mixing ratio in terms of altitude, and we have a blue. It does still look as blue. That's good. We have Karma in blue and the MAM4 model in orange, and you can see right away that the Karma model is representing an improvement in the representation of black carbon compared to MAM4. So this is actually really good to see. And by the way, I didn't mention this on the aerosol or on the airborne slide, but I just want to say there's a whole bunch of airborne research teams or instrumentation teams. I try to credit them on these slides, but of course I need to acknowledge them for all of the hard work that they did to gather these observations as well. And then I also wanted to throw out there from a sensitivity run that we did looking at a convective removal scheme. I'm adding a third plot here for an old, this is a third profile here that is in sort of the light blue cyan color, and this is actually using an old convective removal scheme, and so you can, and for Karma, and so you can actually see the pretty substantial difference that convective removal scheme is making, and of course a nice victory to see that the current and newer sort of version of the convective removal scheme is actually allowing this black carbon representation to look as good as it does. So certainly something good. Switching gears to sulfate, not nearly as pretty as the black carbon plot that I showed before, but on the left is results from the Stratoclim campaign, and on the right is results from the ACLIP campaign. And in both of these campaigns, actually in the free troposphere, we see quite a bit of high bias actually in the models in both Karma and MAM4. On the right panel, I left that the old convective removal plot on there just to show you that doesn't explain the same differences that it did for black carbon. And so this is something that warrants sort of further investigation. I think that, or that's what I'm going to continue to do here. But in the lowermost stratosphere during Stratoclim, we actually aren't doing too bad of a job. I think that's worth mentioning. But the free troposphere is something we want to look at. And so it's worth noting, especially for ACLIP, we sampled a large amount of outflow from over China. And SO2 emissions in China have been rapidly declining in recent years. And so you actually see that there's a very wide range of variability in terms of the different emission inventories that are available. And the ones that we use in our study are probably a lot higher than is realistic. And so from this standpoint and sort of the leveraging the high bias that we saw on the last slide, we ran a couple of sensitivity studies, 50% anthropogenic SO2 and a 10% anthropogenic SO2, just to kind of give some kind of an idea if we really tamp down the SO2 emissions, can we do a better job with sulfate? And looking at SO2 first, just to give some context for sort of the emissions reduction here. First of all, you can see that the Karma and MAM4 simulations were in fact a little bit too high in SO2 compared to the airborne observations, which are the black dots. And applying this 50% and this 10% sort of threshold to the global anthropogenic SO2 measurements does in fact bring us into a much more sort of reasonable range with the SO2 observations. And then that there in turn can give us a more reasonable answer with sulfate. And so this is maybe not the most, this is sort of just a test run at this point. It's not maybe the correct answer to the problem, and that's that we would want to implement some more accurate emissions over China rather than just sort of artificially reducing them globally. But nonetheless, we think that this is giving us some evidence that the emissions bias is at least playing a considerable role in this sulfate bias that we saw, or that we are seeing. One other quick note, we also have a WACM simulation that was available for 2017. We recently did a model evaluation study for looking actually at the gas phase. I don't have plots for that here. I'm trying to keep this focused on aerosol, but we have a model evaluation that we recently did, and so we have this a WACM run, and WACM is using the MAM4 aerosol model. But it has, of course, a much more fine vertical resolution. It's got about a 500-meter vertical resolution in the UTLS and has a much higher model top. And you can see, actually, looking at the SO2 plot again, that WACM is actually doing a reasonably good job at representing the SO2. But it's strange because the entry value you can see at the very bottom of the plot would suggest that the emissions are basically the same. And so it's a little bit bizarre to us why WACM is showing an improvement, or showing actually not even just an improvement, but WACM is showing any differences compared to the other two sort of 32-level lower top models. And so that's something that we'll definitely look at. And here's the same plot for sulfate. Of course, if our SO2 emissions are a little bit lower, the sulfate concentrations are also going to be a little bit lower as well. On the right plot, I've actually got both of the airborne campaigns on there, ACLIP and Stratoclim, even though the models are valid for 2017. So this is something that we're going to continue to look at and see if there's any sensitivity to model top or vertical resolution as far as the convective lofting goes. And the very last thing I want to show, and this is a very early look at something we're doing with size distribution. So this is something else that we want to do to evaluate how the model is doing. Karma has 2 different groups with 20 bins each, and so it's with all of this information that we have about the aerosol size distribution, we would like to do some evaluation there as well. And we have an NMAS instrument that was on both of the aircraft during ACLIP that can give us some information about this. And so this is a very preliminary plot looking at the upper troposphere during ACLIP, and the black dots are the observations from the G5, and the blue and red are showing the 2 different groups of mixed aerosol and pure sulfate that are from Karma. And so you can see, overall the models are within the range of variability of the observations. This is a 10 to 90th percentile. So we're within the range of variability, but we're maybe a little bit low. And there were a large number of new particle formation events that we sampled during ACLIP that may or may not be totally represented. And it looks like the colors went away, but at least they look different enough, so that's good. Okay, so I'll wrap up here. So first I showed that Karma has an excellent agreement with black carbon. This is constituting an improvement compared to MAM4, and also worth noting that the current convective removal scheme is enabling this representation to be proper compared to the observations. There is a high bias in tropospheric sulfate, but we looked at sensitivity to SO2 emissions, which have been declining over China, and that likely contributes to the problem. As future work will be reducing the emissions bias or trying to implement more reasonable emissions. We also want to look, I mentioned, sensitivity to vertical resolution and model top, and seeing if that has any bearing on the results. I didn't mention anything about this, but there's some other things that we want to look at as well, not just the bias and the emissions, but things like the sulfur cycle, adding nitrate to these configurations, and also improving aqueous phase chemistry. This may lead to further improvement, getting the right answer for the right reasons as well. As a very last thing I said was that we may not represent the large quantity of new particle formation events observed in the Asian monsoon convective outflow, and so this is also something that we'll be taking a look at in more detail. And I think the future work will also expand to some other campaigns, some different emission and transport regimes, and then also the balloon-borne observations that we have from extensively over the Western Pacific during ACLIP specifically. So with that, I will stop and take any questions. Thanks.
Are there any questions?
Wow, that's an impressive talk and really exciting work. comparing the data to the model. What version of the model are you using? Are you using spectral element model with CamDev physics, or, you know? Oh, okay, so finite volume?
0.2.
Okay. Okay.
Mm-hmm.
Then I won't ask that question. When you looked at the black carbon, and you say it looks good for karma, but when you looked at the top, there was a lot of scatter. And why is that? Are you sampling along the track, or?
Back. No, that's a great question, actually. So we're not sampling the model along the track. That's one thing I actually failed to mention here is we're actually, so there's a couple of gray boxes for each of these airborne campaigns. We're using the gray boxes as a loose sort of subset for the general regime that was sampled during the month of each campaign. And so the model variability, but actually the model variability is a lot tighter there than the observations. I don't have. I think maybe a conversation with Shuka might be in order, actually, to try to understand that big spread. There were a lot of, or maybe even looking at the different, maybe trying to subsample to the different transport regimes. You know, we have a backward trajectory product that might help us understand the different things contributing to the different sort of modes of that.
Yeah, I think that'd be really useful.
Great talk. I just wanted to ask a similar question. It seems that the model captures the measurements, but I was wondering it can kind of see the shape, vertical profile shape of the atoll aerosols or not.
Yeah, not so. That's something else, actually, that we want to look at that with organics as well as with nitrates. We don't have nitrates in the model at this point. You do see a bit of a shape with that in the right plot, especially. You can kind of see a little bit of a rise in both of the models. It's maybe not quite the slope that we were expecting, but that's kind of why we wanted to look in the general regime. And to the answer to Doug's question being the general domain question is we wanted to see if in the vertical we see that sort of enhancement, that nose, if you will. Okay, thanks.
Let's move on. Thanks, Ren. Let's move on to the second presenter in this session, Sadie Mohammadi, who will be talking about secondary organic aerosol formation from the volatile chemical products.
Oh, okay. Okay. Hello, everyone. I'm Saida, graduate student from University of Iowa. And today I'm gonna present a part of my research, modeling oxidation products and aerosol formation from cyclic volatile methyl siloxane using Musica framework. First of all, I wanna acknowledge my advisor, Charles Stanier, and our collaborator, that this work was not possible without them. And also our collaborator from University of Colorado at Boulder, and scientists here at NCAR, Dr. Imons, Dr. Tilmes, Dr. Tang, and Dr. Zhou. So since Chris already explained about the CVMS, I'm not gonna go through the all the introduction, but as a summary, volatile methyl siloxane are widely used human-made VCP. So in the ingredient list of personal care products like deodorant, hair conditioner, and antiperspirant, you can find this name in the list, which represent the siloxane. And this structure at the bottom is D5. So the siloxane are found in cyclic and linear structure with different silicon numbers in their structure. So D5 represents the cyclic with 5 silicon in it. And this is the most abundant and ubiquitous VMS in the atmosphere. These are highly volatile. When you go out with your personal care product on, they can evaporate and go to the atmosphere, and then subsequently react with oxidant. Their lifetime in the atmosphere is 4 to 10 days. And a global D5 emissions of 0.153 teragram per year, comparing to the benzene, which is about 3%, are measured over major urban centers. But what happened for this compound when they reach to the atmosphere is that 95% react with hydroxyl radical and about 5% react with chlorine radical. So this is one of the main oxidation product when one methyl group attached to the silicon are replaced with hydroxyl radical. They're known as the siloxanol or D4TOH, and there is also other minor products. But the partitioning to the aerosol phase is still uncertain. To date, some groups have studied the SOA formation in different ways, starting from 1998 with chamber experiment, and also field. There are some field measurements and oxidation flow reactor measurements, but the most recent published work, which is the experimental work with oxidation flow reactor and also field measurement, is from Mipage et al. 2024, that I'm one of the co-author of this paper. The result indicated the first generation, second, third, and fourth generation oxidation product are present in particle samples collected from New York City during the 2022. So the research goal in my work is the SOA characterization, establishing yields and chemical composition of VMS-derived aerosol in OFR experiment, and also comparison to the real ambient aerosol. And then I'm gonna model the fate of the CVMS from personal care product upon oxidation over the US and rest of the world. So the team science work is, you can see in the picture, this is the OFR when I'm working on SOA characterization in University of Iowa with our Stanier group and also the collaborator from Stone group. The other work is that the field campaign during the summer 2022 in New York City, where we study the parent compound concentration and also gas phase oxidation product and aerosol formation. And recently, we conducted the chamber experiment in CU Boulder in 20 cubic meter Teflon chamber, which much more atmospherically relevant condition with brown group. So as a continued interest in global distribution of parent and oxidation product due to persistent bioaccumulative and toxic status, and also because the gas and particle concentration are present and available in our research to compare against in New York City 2022. And also these compounds are proposed as a tracer of PCP. So we need to know their fate and distribution. The modeling of CVMS and its SOA in musical makes sense. So in the modeling, I'm gonna use the musical model with CAM-Chem components with comprehensive chemistry and SOA added to the model. As Chris explained, we're gonna use the VMS emission from Brune et al. As described schematically, where we use the sales data and using per capita emissions from Janicic et al. 2070 and times to the population density, we're gonna get the VMS emission. And this figure shows the D5 emission distribution all over the board. So SOA formation in the CAM-Chem is based on the volatility basis set scheme where each VOC oxidized with oxidant and the gas phase oxidation product are categorized in different volatility bins, in 5 bins based on their volatility and which they are in equilibrium with aerosol phase based on their saturation concentration ranging from 0.01 to 100 microgram per cubic meter. So the reaction of aerosol formation of D5, D4, D6, 3 different siloxane would be as these reactions. And the alpha at the beside of SOAGs, which represent the volatility bins, represent the molar yield for each bins. So these molar yields comes from the experimental work that we are using this 6 period studies result, that each points and color represent different studies in chamber and OFR, and the figure represent the SOI yield versus OH exposure. As you can see, there is a very huge range and variability in each studies because of the different condition in each studies. So we're gonna take these results from the SOI yield of D5 and calculate the molar yield in SOI formation. So you can see the lower troposphere organic aerosol region is highlighted here, which very few points, data points are in this region, showing that most of these experiments was not conducted in environmentally relevant condition. But these are all we have, and we started the very first stage of our modeling with these data. This is another figure, the same data points, same result, but different way to show it, like SOI yield versus D5 reacted. And also the highlighted region represent the atmospherically relevant condition with few points. And for estimated molar yield, each of these experiments can be simulated to give aerosol mass concentration and also aerosol yield. This figure shows the model fit in blue line to get the alpha values and then fitting the model based on the alpha values. And the figures at the right-hand side shows the alpha values that we calculated based on these data points. So this fit is not good. Actually, it is horrible because there is a high variability between data points, but we're going to come back later to this figure. So these are the preliminary results from the simulation of D4, D5, D6, and oxidation product globally. So this July 13 to August 6, 2022 coincides with New York City field campaign. As you can see, the D5 concentration is higher than D4 and then D6. And mostly those are concentrated over the populated city as we were expecting, but the oxidation product are more dispersed all over the northern hemisphere. So when we zoom in a CONUS, this is the same figure, but focus on the continental United States. D4, D5, D6, and OD4, OD5, OD6. As you can see in the New York City, like the most populated city, like LA, New York City, the parent compounds are with high concentration, but the oxidation product are more dispersed. As a comparison to previous study, when we take a look at the D5 concentration over the CONUS in the Musica in the left-hand side, and the simulation using the regional model, the CMAC with 36 kilometer resolution. So the results are consistent. If you take a look at the July, I don't know how can I use the pointer. Okay, when you take a look at this figure, these are, this looks similar, and the values of the maximum D5 concentration in CMAC modeling, which is about 30 ppd or 430 nanogram per cubic meter in urban areas, are consistent with the Musica model. This is the diurnal variation of period of the simulation of D5 and OD5 concentration. So I have a problem with the pointer. So, okay. And so this figure shows the D5 concentration, and the bottom is for oxidation product. As you can see, we took 4 cities. The bottom one, the top one is Los Angeles, and then New York City, Chicago, and Boulder. So we were expecting to see, based on the field measurements and also available data, we were expecting to see the highest concentration over the LA, and also comparing to the Brune et al. New York City field measurement, the value for New York City in the Musica simulation are consistent with the real field measurement. So if you take a look at, so the shaded area represents the nighttime, 6 p.m. to 6 a.m. So the D5 peak in the early morning and OD5 peak in the early afternoon, which is consistent, which is connected to a hydroxyl radical diurnal pattern and also the boundary layer, as we were expecting. So with SOA formation of D5 added to the model, so these reactions are the D4, D5, D6 oxidation reaction added to the model. And the bottom one is the SOA formation from D5. And the simulation here shows the focus on the cones. So we had one base case to compare with the one with SOA, with D5 derived SOA added to the model. So this figure indicates the total SOA in a case with D5 gas phase and aerosol phase added to the model. And this one is with only gas phase oxidation product. So when we subtracted these two simulation, this is how the SOA formation from D5 looks like, which it's not what we were expecting. And this is the what you can see over the cones. That seems mostly like the noise with some increase and decrease in the SOA concentration. So there is a lot of work to be done. And we are in a very first stage of doing the modeling. So I just wanted to show you the preliminary result and take feedback and suggestion. And as a future direction, the research outcomes from the OFR and field campaign and chamber experiment with much more environmentally relevant condition are gonna use for Musica simulation in near future, and also multi-generational aging like first and second generation oxidation product, as we observed in real field particle samples collected from New York City, as it's shown in the picture, are gonna take into account in Musica modeling. And also we're gonna take more consideration of a reaction partner in low NOx and high NOx condition. Thank you. I would be happy to take any question.
Our next speaker is online, Rafael Pedro Fernandez. We'll be talking about short-lived halogen chemicals.
Hi, do you hear me well? Sorry, can you hear me?
Can, yes.
Okay, thank you. So thanks a lot. My name is Rafael Fernandez from the CONICET in Argentina. I'm presenting some results of short-lived halogen chemistry developments in CSM. All these developments have been led by Alfonso Saiz Lopez in Madrid with all his team and some of my students here in Argentina, and with valuable help from Doug Kinnison and Francis Pitt. So my presentation will be basically split in 3 sections. So first is just a brief introduction of short-lived halogen chemistry for those persons that are not familiar with. Then I will mostly focus on some of the technical description of the release of the CESM2 SLH version or branch version of the model. Presented some summary of name list options and chemical reactions, concepts and configurations. And then at the end, some evaluation or important evaluations or checks that must be performed whenever a user wants to do these halogen chemistry tests or simulations. So first, short-lived halogens are mostly emitted from the ocean, but also from anthropogenic sources. They have lifetimes of from a few minutes to 3 to 5 to 6 months, smaller than 6 months, that's the definition. And they are very reactive, so once in the atmosphere, they are break down and release chlorine, bromine, or iodine atoms that can react with ozone, and then they participate in ozone depletion. They can react with NO2, with OH. They change the partitioning of all these oxidation species, and so they can affect many climate forces in the Earth system. So that's why this reactive transport of these short-lived species is really important. So compared to long-lived halogens like CFCs, which were supposed to be unreactive until they reach the stratosphere, these short-lived species, short-lived halogens, can break down in the boundary layer or in the free troposphere, where there are additional non-stoichiometric reactions. Some of them are sources, like the sea salt dehalogenation occurring in the marine boundary layer, but also some of them can be removal process occurring on liquid droplets, on ice crystals, etc. So after many years of developing all this chemistry, basically in CSM1, that's all we've done. We have quantified, and the net effect of halogens, of short-lived halogens on ozone, is about 50% on the global average. On the right, you can see the contribution of iodine, bromine, and some other of the OX and HOX loss rates on ozone. And iodine is the dominant species in the troposphere, but with an important contribution of bromine in the upper troposphere and also in the lower stratosphere. So in other studies, we have also shown the influence of biogenic bromine in the Antarctic ozone hole formation, for example, where we showed that 5 ppts of natural bromine was enhancing the size of the ozone hole area by about 40%. And that's on the left, sorry. And on the right, more recently, we also showed that the injection of approximately 0.7 ppts of iodine also has an influence on the Antarctic ozone hole area and on the beginning and the closing dates of the ozone hole, which is equivalent to approximately 3 to 4 ppts of the natural bromine. Another interesting study that I'd like to put into context is that short-lived halogens affect methane lifetime. So we expect to increase the methane loss by adding additional chlorine radicals. But then at the same time, the bromine and the iodine that is released at the same time in the system, they impact and they indirectly decrease OH. So if you decrease ozone, you decrease OH, and if you decrease OH, you enhance you increase the methane lifetime. We found out that during the 21st century, this increase in the global methane lifetime was of about 6 to 9%. And for this study in particular, I will return to this at the end, we developed an emission, these were emission-driven simulations with methane. So now I will just talk about the release of this CSM2 short-lived halogen version. So we have a new branch, which we call it CSM2.2 ASD branch _ SLH. So we've been working with CamChem and CSM for many years already, but we never used GitHub in the past. So I really appreciate all the help from Francis Beat and Jim Edwards mainly on how to make all these repositories connected and on all the checkout externals that need to be done. So now this fork version is at the moment in my personal GitHub, but we hope to have it soon on the CSM complete repository. You can clone it from from this path. And basically, the CSM2 short-lived halogen scheme has two different chemical schemes. I mean, the halogen scheme is exactly the same, and we implemented it on the Mozart TS 1.2 versions for CamChem, and also on the TSM LT1 for WACAM. And all of this was performed last year when I was at NCAR, these final connections with these mechanisms. And there are many photochemical reactions. So basically there are an additional like 40 total new species considering halocarbons and inorganic chlorine, bromine, and iodine species. There are photochemical reactions of many of them affecting both chlorine and bromine or both bromine and iodine species. We also added more than 20 reactions of these halocarbons with OH or chlorine atoms in the chemical mechanism. We basically developed the complete odd iodine chemistry in the scheme and updated with some expressions the odd bromine and odd chlorine reactions, and also developed additional or implemented additional heterogeneous reactions. The most important ones that I will focus today are those processes that are included at the end of the chemical mechanism, which represent additional sources or sinks, which were necessary to reproduce the vertical profiles and compare with observations of these species. So the new concepts that we've developed are based on the original concept on CSM 2.2. So these are the FC Nudge and the FC Hist SLH versions that we have it. For each of these concepts, whenever you select them, you will get a new and updated name list file, including the emission and the deposition of species. All these variables I will show in the next slides are updated. We have also developed FC 2000 CLIMO and FCSD concepts, but we have not really tested them that much as the other ones. For WACAM, we are basically working with the FWHIS BGC SLH concept setup. And just one important notice is that we are usually, most of the time, mostly for CamChem, the 2 degrees times 2 degrees and 32 levels vertical resolution. So going to the name list, important information for the new users willing to use it. So there are like 3 blocks of emissions. The first block here on the top is pointing to the Ordonez inventory of oceanic emissions of bromine and iodine halocarbons. The Hosseini and Claxton inventory for anthropogenic emissions, which is the second red box here. And then the third one is for iodine emissions, which is just a placeholder because these emissions are actually computed online, but we need to keep track of these emissions, so we implement it also in the name list. So it is also important to recognize that lower boundary conditions for a couple of halocarbons must also be included, and also remember to remove the bromoform and dibromomethane that in the standard setup of simulation are also included as 6 ppts of lower boundary conditions. And all this information, including some NC data for initial conditions, are actually hosted in this place. As Simone explained on the overview talk, this needs to be moved into the Musica folder at some point, so all the people can directly point to those paths. Regarding the position of this species, so there is a complete new, there are addition of all the halogen species on the dry deposition list. And for the case of the wet deposition, there is an ice uptake variable that is basically fixed in the name routine, which we have now included as a list into the name list because now the halogen species are not mapped any longer to nitric acid, but they have their own Henry coefficients and washout efficiencies computed online. And finally, because some of these heterogeneous processes that we have in the chemical mechanism, which are represented here on the bottom, for example, for the sea salt dehalogenation, they depend a lot on the specific sea salt fields or ice crystal field that change between model configurations. So to avoid modifying these recycling efficiencies in the routines, we develop a new name list section, we call the SLH name list section, with some scaling factor efficiencies that are something similar to what is done for the lightning NOx production factor or the dust emission factor that must be changed when shifting between one configuration or the others, and users should, the default values are set into 1. So with current values, with the proper configuration or the standard configuration we are using, those should work well. So finally, just some tests that we've been doing. And this is the first one. And I really need to catch up with you, Ben, on some of these things. So we use the same methane emission inventory for methane, and we couldn't reproduce the results in CSM2 for long simulations. So we first thought there was an error on the implementations on the emission between CSM1 and CSM2 that are shown here on the left, but we recognized that that was not a problem. So the model was properly reading the emissions. And the lower boundary conditions, even if they change between CSM1 and CSM2, they show basically the same trend. But whenever we use emission of methane and perform simulations longer than 10 years, we start to see a decrease on the trend. We cannot sustain the trend on the lower boundary conditions that we obtain when we use the lower boundary conditions. And we really need to understand what is going on here. I don't know exactly what is it, but the final setup that we have just put out in the branch is using lower boundary conditions to avoid this unrealistic trend whenever we perform long simulations. So an additional check that needs to be done is to be sure not to inject too much bromine to the stratosphere from this comprehensive bromine chemistry in the troposphere. So for doing this, we need to compute at the TTL. This is the tropical mean, the vertical profile on the left, and this is the trend of that tropical mean at 100, between 100 and 85 hectopascals. And there is a total of 5 ppts of inorganic bromine being injected for the different sensitivities. If we modify the scaling factor for the ice washout of bromine, then this can affect a little bit, and we need to be sure not to have too much injection of bromine on those configurations for any users willing to perform this. And finally, for iodine, we have also performed the same, some sensitivity tests, more focused on the washout in the boundary layer, which also depends basically on HOI removal. So we make sure that the total injection does not surpass the 0.75 ppts of iodine in the stratosphere, but also we need to check that the results, the abundance of iodine in the surface and in the boundary layer is between the expected values from we got originally in System 1. So that's all. This is just a final slide comparing a halogen versus a no halogen simulation. On the left, there are some allowance for ozone and surface below, and on the right for OH. So all the results that we are getting are completely in line with our previous studies using CSM1. And in any case, the impact of this halogen chemistry is a little bit smaller. That's to be cautious with this implementation. So thanks a lot to everyone, and I'm happy to take questions. And this is the new branch name for your consideration. Thank you.
Yeah, we have time for one quick question.
Rafa, for a great talk, and thank you for making this all available. I would be very careful if people using versions of the model that are not tested out here with the halogens. So if you have a configuration where you've created a comp set, it's fair game to use. But if it hasn't been created and you haven't had a chance to really look at the tuning in there, people could get in trouble, don't you think?
Yes, you are right, Doug. So your recommendation would be not to have those comp set allowed. I mean, just comment all those places. So, and until we have all these tuning factor for all these configurations tuned. I mean, actually, what we really need is to test all of them for different projects, which requires different configurations. And we basically replicating the standard configurations we were using in CSM1 and making sure for the 3 ones that were in bold italics in the presentation, those values are consistent already.
Be careful, because if you could really have bad representation of halogens in the troposphere and in the stratosphere if you're not careful.
Okay, yeah, you're right. Thank you for the comment.
Beirut's Rosetta Lab will continue the conversation on short-lived halogens.
Choose to think you wanted to listen to my talk, not are waiting for the wrap-up session. Okay. I don't see anything here. Yeah, so I want to talk about a new emission inventory for oceanic sources of bromine halogens, brominated halogens that we are working on. And first I wanted to thank my co-authors and our group that are listed here, and also Francis and Ben, who helped us a lot in running the model. Okay. Yeah, so Rafa mentioned, kind of covered the VSLS, but I like to also talk about that. So halogens, we mostly know about the long-lived species, the CFCs that are released to the atmosphere, and okay, it doesn't work. And but they are currently being controlled based on the Montreal Protocol. So now the impact of the other compounds are becoming much more important. And they are called VSLS, or short-lived halogens, or very short-lived substances. Yeah. And they have different sources. And in this talk, I will talk about 2 of them that are brominated, this bromoform and dibromo, that are primarily emitted from oceans. And there are some anthropogenic sources that people are trying to constrain, but they are primarily emitted from oceans. And we want to estimate their emissions. The reason for that is because there is a statement in the WMO report on the ozone assessment that says that the future changes in climate change and anthropogenic emissions can also potentially affect these natural sources. So we want to investigate that. And we have been in these ocean sessions during the last few days, and we have seen that there are a lot of uncertainties in the oceans. And and there are a lot of work in progress to mechanistically estimate the emissions of these compounds from the sources, the oceanic sources. But for now, we want to try to find a connection between the oceanic concentrations and the atmospheric flux of these compounds. But as I said, we still don't know, we do not have like the full picture of their emissions in the water, so we have to estimate their oceanic concentrations. And there are a few measurements, there are not a few measurements, but there are some measurements happened around the years that they have measured the concentration of these compounds in the ocean. But we want to kind of get the map of that. And for that purpose, we kind of developed a machine learning framework, which we try to find a connection between these measurements that has been gathered over the world and the oceanic variables from the ocean model. And based on that, we develop a model, a machine learning model that we could kind of estimate their sea surface or oceanic concentrations. And here I'm showing like the measurements that are available for these compounds, for example, here for bromoform. And they are all compiled in a data set, called HaloCat. So we tried to, we tuned and trained and tested our machine learning framework. And here I'm just showing like a sample for bromoform sea surface concentrations that we developed using our model. So, you see that there are like some hotspots over the coastal areas, and there are some like larger values over the Arctic and polar regions that are kind of, cannot go here, that are kind of, cannot go here? Okay, yeah, that are kind of matching like the measurements that has been collected in these regions. So the next part is that, okay, we now have the sea surface concentrations, but we want to get the flux and we want to get the atmospheric concentrations. So we have a new module in the CSM. It's called OSIS, or the Online Air-Sea Interface for Soluble Species, that has been implemented in the released version of CSM 2.2. That you can, so it basically reads an input file in the name list for these oceanic concentrations and the sea surface temperature data and salinity, ocean salinity data as inputs. And then during the runtime, it calculates the flux based on this main equation, which requires the Henry's constant, the gas and liquid equilibrium ratio, and also the transfer velocity in ocean or in the atmosphere. And so this is like basically the framework that we now we can work on, that to estimate the oceanic flux of these compounds and also get the atmospheric concentration. So it's kind of a runtime cycle that happens when the model is running. And here again, I'm showing like the sample for the emissions that we calculate based on the sea surface concentration and based on this framework. And we see that, again, we see higher concentration, higher emissions over the coastal regions, specifically in the Western Pacific and over the coastal regions. And we have like a more, it seems like it has more features compared to the other data sets, and I will show you that. So here I'm showing like the annual mean emissions for bromoform on top and dibromo on the bottom. And in the parentheses, I have like the total flux emission of bromine for each of these compounds. And as a comparison, this is like a very common emission inventory developed in 2012 that Rafa was showing some of the results based on this emission inventory. And so this inventory is kind of a top-down inventory. They try to estimate the priori flux based on the satellite and chlorophyll data, and then use the atmospheric measurements kind of to constrain the emissions. But we see like they are very different in terms of like the magnitudes, and you see like we are like about 4 times lower in terms of bromophore. And since they were using like based on satellite data, you see that they don't have a lot of information in these regions that satellite doesn't frequently have data for. And another example that these emissions are very uncertain. I have listed like the range of reported fluxes in the WMO report for each of these compounds. And we see that we are very close to the lower range of these values. So in simple words, there are a lot of data sets, but which one can be used? And we think that this emission inventory is kind of getting old. It's kind of 12 years old. So we are thinking that we should update that. So to validate the data and see what's happening, we looked at the atmospheric concentrations, and we specifically looked at the 3 campaigns. The ACLIP that Ren talked about in 2022 in the Western Pacific, the ATOM campaign that was happened on 4 circuits, 4 sections in 2 years, and the ORCAS that happened in 2016 in the Southern Ocean. And we used our measurements made by the TOGA TOF instrument, which I show like the image of that here. It's kind of a powerful instrument that can measures about 120 VOCs with 2-minute interval during the flight. So here I'm showing the results for each of these campaigns, the vertical profiles. The very small dots are individual measurements. The black circle dots are the median of the measurements. And so the blue line is the Ardonia's emissions, and the other line is our estimates for each of these compounds. And the top is for bromoform, and on the bottom is for dibromo. So we see that there are sometimes that we are low, but there are sometimes that we are kind of close together. But in general, it seems that the Ardonia's emissions are kind of overestimating the emissions, and we are underestimating the emissions. So we wanted to scale our data. So what we did is that we kind of looked at the first kilometer data to be representative of the emissions only, not like the atmospheric chemistry. And we found a scaling factor to kind of scale our sea surface concentrations. And here I'm showing like the scaling factor results for our data. And we see that we kind of are now improved. So we kind of match the low altitude concentrations very well, but we are still like kind of have problems in the high altitudes that we are working on. But yeah, but in general, again, we now think that we have the framework that we can estimate the oceanic concentrations and the oceanic fluxes and then atmospheric concentrations. And we think now we can try to answer this WMO question and run the model to the future and see what's happening. So here I'm showing some of our results for this oceanic concentrations based on the RCP 8.5 scenario. And here I'm showing, it's easier here. I'm showing the present day concentrations for bromoform here, and here I'm showing the changes at the end of the century. And we see, at least our estimates are showing about a doubling of oceanic concentrations in the Western Pacific. And this is an important place because we have Asian summer monsoon, so if we increase the emissions in this region, then we can probably increase our stratospheric injection. And on the bottom, I'm showing the same plot for dibromo, and we see kind of a similar trend, but with lower values. And so what we are trying to do is to run CSM using the OSIS, using these sea surface concentrations until the end of the century, and then look at the impact. And then we are going to look at two different scenarios, the RCP 8.5 and RCP 4.5. And here I'm showing like the very like the overall 80 percentile trend of these two different scenarios and basically two different data sets that we have. And we see that there are, at some points, there is a deflection between these two scenarios. So we want to try and do some tests on that and see the impact. And yeah, this is a summary, and just on the right, I'm showing our framework, and as a summary, we have now a framework that we can estimate the sea surface concentrations, and we did a test, and we tried to adjust our oceanic concentrations and oceanic fluxes, and now we are in a place that we can go forward and look at the impact at the end of the century. And with that, I thank you, and I'm happy to answer your questions.
So we're out of time, and I know we're probably missing the wrap-up discussion, but please come and see Peruz and chat to him if you have questions. Yep. And the wrap-up is in the middle. It's in the middle day. So that started at 4:30 apparently. Let's also thank all the other speakers from this section.